Okay. So, welcome. Practical Deep Learning for Coders, Lesson 1. It's kind of Lesson 2 because there's a Lesson 0, and Lesson 0 is why do you need a GPU and how do you get it set up. So if you haven't got a GPU running yet, then go back and do that. Make sure that you can access a Jupyter notebook and then you're ready to start the real Lesson 1. So if you're ready, you will be able to see something like this. In particular, hopefully you have gone to Notebook Tutorial. It's at the top. That's why I put a 00 here. As this grows, you'll see more and more files, but we'll keep Notebook Tutorial at the top. And you will have used your Jupyter notebook to add 1 and 1 together, getting the expected result. Let's make that a bit bigger. And hopefully you've learnt these 4 keyboard shortcuts. So the basic idea is that your Jupyter notebook has prose in it. It can have pictures in it. It can have charts in it. And most importantly, it can have code in it. Okay. So the code is in Python. How many people have used Python before? So nearly all of you. That's great. If you haven't used Python, that's totally okay. Right? It's a pretty easy language to pick up. But if you haven't used Python, this will feel a little bit more intimidating because the code that you're seeing will be unfamiliar to you. Yes, Rachel?
I was going to say, for people in the room, it's okay if they don't have to keep going, right?
Oh, yeah. No, because I'm trying to keep them moves separate.
Sorry.
Yeah. Okay, well, now that we're here, I'll edit this bit out. So, as I say, there are things like this where people in the room, in person, this is one of those bits where it's like this is really for the MOOC audience, not for you. I think this will be the only time like this in the lesson where we've assumed you've got this set up. Thanks for the reminder. Okay. All right. So yeah, for those of you in the room or on FastAI Live, you can go back after this and make sure that you can get this running using the information in course v3.fast.ai. Okay. Great. Okay, so a Jupyter notebook is a really interesting device for a data scientist because it kind of lets you run interactive experiments and it lets us give you not just a static piece of information, but it lets us give you something that you can actually interactively experiment with. So let me explain how we think works well to use these notebooks and to use this material. And this is based on the kind of last 3 years of experience we've had with the students who have gone through this course. First of all, it works pretty well just to watch a lesson end to end. Right? Don't try and follow along because it's not really designed to go at a speed where you can follow along. It's designed to be something where you just take in the information, you get a general sense of all of the pieces, how it all fits together. Right? And then you can go back and go through it more slowly, pausing in the video and trying things out, making sure that you can do the things that I'm doing, and that you can try and extend them to do things in your own way. Okay, so don't worry if things are zipping along faster than you can do them. That's normal. Also, don't try and stop and understand everything the first time. If you do understand everything the first time, good for you. But most people don't, particularly as the lessons go on. They get faster and they get more difficult. Okay. So at this point, we've got our notebooks going. We're ready to start doing deep learning. And so the main thing that hopefully you're going to agree at the end of this is that you can do deep learning, regardless of who you are. And we don't just mean do, we mean do at a very high level. We mean world-class practitioner level deep learning. Okay. So your main place to be looking for things is course v3.fast.ai. where you can find out how to get a GPU, other information, and you can also access our forums. Oopsie daisy. You can also access our forums, and on our forums you'll find things like how do you build a deep learning box yourself, and that's something that you can do after, later on once you've kind of got going. Who am I? So why should you listen to me? Well, maybe you shouldn't, but I'll try and justify why you should listen to me. I've been doing stuff with machine learning for over 25 years. I started out in management consulting, where actually initially I was, I think, McKinsey & Company's first analytical specialist, and went into general consulting. Ran a number of startups for a long time. Eventually became the president of Kaggle. But actually the thing I'm probably most proud of in my life is that I got to be the #1 ranked contestant in Kaggle competitions globally. So I think that's a good kind of practical, like, can you actually train a predictive model that predicts things? Pretty important aspect of data science. I then founded a company called Analytic, which was the first kind of medical deep learning company. Nowadays, I'm on the faculty at University of San Francisco and also co-founder with Rachel of FastAI. So I've used machine learning throughout that time, and I guess I'm not really, although I am at USF at a university, I'm not really an academic type. I'm much more interested in using this tool to do useful things. Specifically, through FastAI, we are trying to help people use deep learning to do useful things through creating software to make deep learning easier to use at a very high level, through education, such as the thing you're watching now, through research, which is where we spend a very large amount of our time, which is researching to figure out how can you make deep learning easier to use at a very high level, which ends up in, as you'll see, in the software and the education, and by helping to build a community, which is mainly through the forums, so that practitioners can find each other and work together. So that's what we're doing. So this lesson, Practical Deep Learning for Coders, is kind of the starting point in this journey. It contains 7 lessons, each one's about 2 hours long. We're then expecting you to do about 8 to 10 hours of homework during the week. So it'll end up being something around 70 or 80 hours of work. I will say it varies a lot as to how much people put into this. I know a lot of people who work full-time on FastAI. Some folks who do the 2 parts can spend a whole year doing it really intensively. I know some folks watch the videos on double speed and never do any homework and come out the end of it with, a general sense of what's going on. So there's lots of different ways you can do this. But if you follow along with this kind of 10 hours a week or so approach for the 7 weeks, by the end, you will be able to build an image classification model on pictures that you choose that will work at a world-class level. You'll be able to classify text, again, using whatever data sets you're interested in. You'll be able to make predictions of kind of commercial applications like sales. You'll be able to build recommendation systems, such as the one used by Netflix. Not toy examples of any of these, but actually things that can come top 10 in Kaggle competitions, that can beat everything that's in the academic community, very, very high-level versions of these things. So that might surprise you, that the prerequisite here is literally 1 year of coding and high school math, but we have thousands of students now who have done this and shown it to be true. You will probably hear a lot of naysayers, less now than a couple of years ago than we started, but a lot of naysayers telling you that you can't do it, or that you shouldn't be doing it, or that deep learning's got all these problems. It's not perfect, but these are all things that people claim about deep learning, which are either pointless or untrue. It's not a black box. As you'll see, it's really great for interpreting what's going on. It does not need much data for most practical applications. You certainly don't need a PhD. Rachel has one, so it doesn't actually stop you from doing deep learning if you have a PhD. I certainly don't. I have a philosophy degree and nothing else. It can be used very widely for lots of different applications, not just for vision, which is where it's most well known. You don't need lots of hardware. You know, that 36 cent an hour server is more than enough to get world-class results for most problems. It's true that maybe this is not going to help you to build a sentient brain, but that's not our focus. Okay, so for all the people who say deep learning is not interesting because it's not really AI, not really a conversation that I'm interested in. We're focused on solving interesting real-world problems. What are you going to be able to do by the end of lesson 1? Well, this was an example from Nikhil, who's actually in the audience now because he was in last year's course as well. This is an example of something he did, which is he downloaded 30 images of people playing cricket and people playing baseball and ran the code you'll see today and built a nearly perfect classifier of which is which. So it's kind of stuff that you can build with some fun hobby examples like this, or you can try stuff, as we'll see, in the workplace that could be of direct commercial value. So this is the idea of where we're going to get to by the end of lesson 1. We're going to start by looking at code, which is very different to many of the academic courses. So for those of you who have a kind of an engineering or math or computer science background, this is very different to the approach where you start with lots and lots of theory, and then eventually you get to a postgraduate degree and you finally are at the point where you can build something useful. We're going to learn to build the useful thing today. Okay. Now that means that at the end of today, you won't know all the theory. Okay. There will be lots of aspects of what we do that you don't know why or how it works. That's okay. You will learn why and how it works over the next 7 weeks. But for now, we've found that what works really well is to actually get your hands dirty coding, not focusing on theory, because there's still a lot of artisanship in deep learning, unfortunately. It's still a situation where people who are good practitioners have a really good feel for how to work with the code and how to work with the data, and you can only get that through experience. And so the best way to get that feel of how to get good models is to create lots of models, do lots of coding, and study them carefully. And Jupyter Notebook provides a really great way to study them. So let's try that. Let's try getting started. So to get started, you will open your Jupyter Notebook and you'll click on Lesson 1. Lesson 1, Pets. And it will pop open looking something like this. And so here it is. So you can run a cell in a Jupyter Notebook by clicking on it and pressing Run. But if you do so, everybody will know that you're not a real deep learning practitioner, because real deep learning practitioners know the keyboard shortcuts. And the keyboard shortcut is Shift-Enter. Given how often you have to run a cell, don't be going all the way up here, finding it, clicking it, just Shift-Enter. Okay, so type, Shift-Enter, type, Shift-Enter. Up and down to move around, to pick something to run, Shift-Enter to run it. Okay. So we're going to go through this quickly, and then later on, we're going to go back over it more carefully. So here's the quick version to get a sense of what's going on. So here we are in Lesson 1, and these 3 lines is what we start every notebook with. These things starting with % are special directives to Jupyter Notebook itself. They're not Python code. They're called magics, which is kind of a cool name. And these 3 directives, the details aren't very important, but basically it says, hey, if somebody changes the underlying library code while I'm running this, please reload it automatically. If somebody asks to plot something, then please plot it here in this Jupyter Notebook. So just put those 3 lines at the top of everything. The next 2 lines load up the FastAI library. What is the FastAI library? So it's a little bit confusing. FastAI with no dot is the name of our software, and then fast.ai with the dot is the name of our organization. So if you go to docs.fast.ai, this is the FastAI library. Okay, we'll learn more about it in a moment, but for now, just realize everything we are going to do is going to be using basically either FastAI or the thing that FastAI sits on top of, which is PyTorch. PyTorch is one of the most popular libraries for deep learning in the world. It's a bit newer than TensorFlow, so in a lot of ways it's more modern than TensorFlow. It's extremely fast-growing, extremely popular, and we use it because, we used to use TensorFlow a couple of years ago, and we found we can just do a lot more quickly with PyTorch. And then we have this software that sits on top of PyTorch and lets you do far more things, far more easily than you can with PyTorch alone. So it's a good combination. We'll be talking a lot about it. But for now, just know that you can use FastAI by doing two things. Importing star from FastAI, and then importing star from FastAI.something, where something is the application you want. And currently FastAI supports 4 applications: computer vision, natural language text, tabular data, and collaborative filtering. Okay? And we're going to see lots of examples of all of those during the 7 weeks. So we're going to be doing some computer vision. At this point, if you are a Python software engineer, you are probably feeling sick because you've seen me go import star, which is something that you've all been told to never ever do. Okay? And there's very good reasons to not use import star in standard production code with most libraries. But you might have also seen, for those of you that have used something like MATLAB, it's kind of the opposite. Everything's there for you all the time. You don't even have to import things a lot of the time. It's kind of funny. We've got these two extremes of like, how do I code? You've got the scientific programming community that has one way, and then you've got the software engineering community that has the other. Both have really good reasons for doing things, and with the FastAI library, we actually support both approaches. In a Jupyter notebook, where you want to be able to quickly, interactively try stuff out, you don't want to be constantly going back up to the top and importing more stuff and trying to figure out where things are. You want to be able to use lots of tab complete, be very experimental, so import star is great. Then when you're building stuff in production, you can do the normal PEP 8 style, proper software engineering practices. So don't worry when you see me doing stuff which at your workplace is frowned upon. Okay, this is a different style of coding. It's not that there are no rules in data science programming, it's that the rules are different, right? When you're training models, the most important thing is to be able to interactively experiment quickly. Okay, so you'll see we use a lot of very different processes, styles, and stuff to what you're used to, but they're there for a reason, and you'll learn about them over time. You can choose to use a similar approach or not. It's entirely up to you. The other thing to mention is that the FastAI libraries designed in a very interesting modular way, and you'll find over time that when you do use import star, there's far less clobbering of things than you might expect. It's all explicitly designed to allow you to pull in things and use them quickly without having problems. Okay, so we're going to look at some data. And there's 2 main places that we'll be tending to get data from for the course. One is from academic data sets. Academic data sets are really important, they're really interesting. They're things where academics spend a lot of time curating and gathering a data set so that they can show how well different kinds of approaches work with that data. And the idea is they try to design data sets that are challenging in some way and require some kind of breakthrough to do them well. So we're going to be starting with an academic data set called the PET data set. The other kind of data set we'll be using during the course is data sets from the Kaggle competitions platform. Both academic data sets and Kaggle data sets are interesting for us, particularly because they provide strong baselines. That is to say, you want to know if you're doing a good job. So with Kaggle data sets that have come from a competition, you can actually submit your results to Kaggle and see how well would you have gone in that competition. And if you can get in about the top 10%, then I'd say you're doing pretty well. For academic data sets, academics write down in papers what the state of the art is. So how well did they go with using models on that data set? Okay. So this is what we're going to do. We're going to try and create models that get right up towards the top of Kaggle competitions, preferably actually in the top 10, not just the top 10%, or that meet or exceed academic state-of-the-art published results. When you use an academic data set, it's important to cite it. So you'll see here there's a link to the paper that it's from. You definitely don't need to read that paper right now, but if you're interested in learning more about it and why it was created and how it was created, all the details are there. So in this case, this is a pretty difficult challenge. The PET data set is going to ask us to distinguish between 37 different categories of dog breed and cat breed. So that's really hard. In fact, every course until this one, we've used a different data set, which is one where you just have to decide is something a dog or is it a cat. So you've got a 50-50 chance right away, right? And dogs and cats look really different, whereas lots of dog breeds and cat breeds look pretty much the same. So why have we changed our data set? We've got to the point now where deep learning is so fast and so easy that the dogs versus cats problem, which a few years ago was considered extremely difficult, 80% accuracy was the state of the art, it's now too easy. Our models were basically getting everything right all the time without any tuning, and so there weren't really a lot of opportunities for me to show you how to do more sophisticated stuff. So we've picked a harder problem this year. So this is the first class where we're going to be learning how to do this difficult problem. And this kind of thing where you have to distinguish between similar categories is called, in the academic context, it's called fine-grained classification. So we're going to do the fine-grained classification task of figuring out a particular kind of PET. And so the first thing we have to do is download and extract the data that we want. We're going to be using this function called untar data, which will download it automatically and will untar it automatically. AWS has been kind enough to give us lots of space and bandwidth for these data sets, so they'll download super quickly for you. And so the first question then would be, how do I know what untar data does? So you can just type help, and you will find out what module did it come from, because since we imported star, we don't necessarily know that. What does it do? And something you might not have seen before, even if you're an experienced programmer, is what exactly do you pass to it? You're probably used to seeing the names, URL, file name, destination, but you might not be used to seeing these bits. These bits are types, okay? And if you've used a type programming language, you'll be used to seeing them, but Python programmers are less used to it. But if you think about it, you don't actually know how to use a function unless you know what type each thing is that you're providing it. So we make sure that we give you that type information directly here in the help. So in this case, the URL is a string, and the file name is either, union means either a path or a string, and it defaults to nothing. And the destination is either a path or a string, and it defaults to nothing. So we'll learn more shortly about how to get more documentation about the details of this. But for now, we can see we don't have to pass in a file name or a destination. It'll figure them out for us from the URL. So, and for all the data sets we'll be using in the course, we already have constants defined for all of them, right? So in this URLs module, or class actually, you can see that's where it's going to grab it from. Okay, so it's going to download that to some convenient path and untar it for us, and will then return the value of path. Okay, and then in Jupyter Notebook, it's kind of handy. You can just write a variable on its own, right? And semicolon is just an end of statement marker in Python, so it's the same as doing this. You can write it on its own, and it prints it. You can also say print, right? But again, we're trying to do everything fast and interactively. Just write it, and here is the path where it's given us our data. Next time you run this, since you've already downloaded it, it won't download it again. Since you've already untarred it, it won't untar it again. So everything's kind of designed to be pretty automatic, pretty easy. There are some things in Python that are less convenient for interactive use than they should be. For example, when you do have a path object, seeing what's in it actually takes a lot more typing than I would like. So sometimes we add functionality into existing Python stuff. One of the things we do is we add an ls method to paths. So if you go path.ls, here is what's inside this path. So that's what we just downloaded. So when you try this yourself, you wait a couple of minutes for it to download, unzip, and then you can see what's in there. If you're an experienced Python programmer, you may not be familiar with this approach of using a slash like this. This is a really convenient function that's part of Python 3. It's functionality from something called pathlib. These are path objects. Path objects are much better to use than strings. That lets you basically create subpaths like this. Doesn't matter if you're on Windows, Linux, Mac, it's always going to work exactly the same way. So here's a path to the images in that data set. All right, so if you're starting with a brand new data set, trying to do some deep learning on it, what do? Well, the first thing you would want to do is probably see what's in there. So we found that these are the directories that are in there. So what's in this? Images. There's a lot of functions in FastAI for you. There's one called getImageFiles that will just grab an array of all of the image files based on extension in a path. And so here you can see we've got lots of different files. Okay, so this is a pretty common way for computer vision data sets to get passed around, is that there's just one folder with a whole bunch of files in. So the interesting bit then is, how do we get the labels? So in machine learning, the labels refer to the thing we're trying to predict. And if we just eyeball this, we can immediately see that the labels are actually part of the file name. You see that, right? It's kind of like path/label_number extension. So we need to somehow get a list of these bits of each file name, and that will give us our labels. Because that's all you need to build a deep learning model. You need some pictures, so files containing the images, and you need some labels. So in FastAI, this is made really easy. There's a object called ImageDataBunch, and an ImageDataBunch represents all of the data you need to build a model. And there's basically some factory methods which try to make it really easy for you to create that data bunch. We'll talk more about this shortly, but a training set and a validation set with images and labels for you. Now in this case, we can see we need to extract the labels from the names. Okay, so we're going to use from name RE. So for those of you that use Python, you'll know RE is the module in Python that does regular expressions, things that's really useful for extracting text. I just went ahead and created the regular expression that would extract the label from this text. Okay, so those of you who are not familiar with regular expressions, super useful tool. It'd be very useful to spend some time figuring out how and why that particular regular expression is going to extract the label from this text. Okay. So with this factory method, we can basically say, okay, I've got this path containing images. This is a list of file names. Remember, I got them back here. This is the regular expression pattern that is going to be used to extract the label from the file name. We'll talk about transforms later. And then you also need to say, what size images do you want to work with? So that might seem weird. Why do I need to say what size images I want to work with? Because the images have a size. We can see what size the images are. And I guess, honestly, this is a shortcoming of current deep learning technology, which is that a GPU has to apply the exact same instruction to a whole bunch of things at the same time in order to be fast. And so if the images are different shapes and sizes, it can't do that. Right? So we actually have to make all of the images the same shape and size. In part one of the course, we're always going to be making images square shapes. In part two, we'll learn how to use rectangles as well. It turns out to be surprisingly nuanced. Right? But pretty much everybody in pretty much all computer vision modeling, nearly all of it, uses this approach of square. And 224 by 224, for reasons we'll learn about, is an extremely common size that most models tend to use. So if you just use size equals 224, you're probably going to get pretty good results most of the time. And this is kind of the little bits of artisanship that I want to teach you folks, which is like what generally just works. Okay, so if you just use size equals 224, that'll generally just work for most things most of the time. So this is going to return a data bunch object. And in FastAI, everything you model with is going to be a data bunch object. We're going to learn all about them and what's in them and how do we look at them and so forth. But basically, a data bunch object contains 2 or 3 data sets. It contains your training data. We'll learn about this shortly. It'll contain your validation data, and optionally, it contains your test data. And for each of those, it contains your your images and your labels, or your texts and your labels, or your tabular data and your labels, or so forth. And that all sits there in this one place. Something we'll learn more about a little bit is normalization, but generally in nearly all machine learning tasks, you have to make all of your data about the same size, specifically about the same mean and about the same standard deviation. So there's a normalize function that we can use to normalize our data bunch in that way.
Getting a question.
Okay, Rachel, come and ask the question. Come over here. Thanks.
What does the function do if the image size is not 224?
Great. So this is what we're going to learn about shortly. Basically, this thing called transforms is used to do a number of things, and one of the things it does is to make something size 224. Let's take a look at a few pictures. Here are a few pictures of things from my data bunch. So you can see data.showBatch can be used to show me the contents of some of the contents in my data bunch. So this is going to be 3 by 3. And you can see roughly what's happened is that they all seem to have been kind of zoomed and cropped in a reasonably nice way. So basically what it'll do is something called, by default, center cropping, which means it'll kind of grab the middle bit and it'll also resize it. So we'll talk more about the details of this because it turns out to actually be quite important. But basically a combination of cropping and resizing is used. Something else we'll learn about is we also use this to do something called data augmentation. So there's actually some randomization in how much and where it crops and stuff like that. Okay, but that's the basic idea, is some cropping and some resizing. Often we also do some padding. So there's all kinds of different ways, and it depends on data augmentation, which we're going to learn about shortly.
And what does it mean to normalize the images?
So normalizing the images we're going to be learning more about later in the course, but in short it means that the pixel values, and we're going to be learning more about pixel values, the pixel values start out from 0 to 255, and some pixel values might tend to be really, well, I should say some channels, because there's red, green, and blue. So some channels might tend to be really bright, and some might tend to be really not bright at all, and some might vary a lot, and some might not vary much at all. It really helps train a deep learning model if each one of those red, green, and blue channels has a mean of 0 and a standard deviation of 1. Okay? We'll learn more about that. If you haven't studied or don't remember means and standard deviations, we'll get back to some of that later. But that's the basic idea. That's what normalization does. If your data, and again, we'll learn much more about the details, but if your data is not normalized, it can be quite difficult for your model to train well. So if you do have trouble training a model, one thing to check is that you've normalized it.
As GPU mem will be in power of 2, doesn't size 256 sound more practical, considering GPU utilization?
So we're going to be getting into that shortly, but the brief answer is that the models are designed so that the final layer is of size 7 by 7. So we actually want something where if you go 7 times 2 a bunch of times, then you end up with something that's a good size. Yeah, all of these details we are going to get to, but the key thing is I wanted to get you training a model as quickly as possible. But one of the most important things to be a really good practitioner is to be able to look at your data. Okay, so it's really important to remember to go data.showBatch and take a look. It's surprising how often when you actually look at the data set you've been given that you realize it's got weird black borders on it, or some of the things have text covering up some of it, or some of it's rotated in odd ways. So make sure you take a look. Okay. And then the other thing we want to do is not just look at the pictures, but also look at the labels. And so all of the possible label names are called your classes. Right? So in the data bunch, you can print out your data.classes, and so here they are. That's all of the possible labels that we found by using that regular expression on the file names. And we learned earlier on in that prose I wrote at the top that there are 37 possible categories, and so just checking length data.classes, it is indeed 37. A data bunch will always have a property called C, and that property called C, the technical details we'll kind of get to later, but for now you can kind of think of it as being the number of classes. For things like regression problems and multi-label classification and stuff, that's not exactly accurate, but it'll do for now. It's important to know that data.c is a really important piece of information that is something like, or at least for classification problems, it is the number of classes. All right, believe it or not, we're now ready to train a model. And so a model is trained in FastAI using something called a learner. And just like a data bunch is a general FastAI concept for your data, and from there are subclasses for particular applications, like image data bunch. A learner is a general concept for things that can learn to fit a model, and from that there are various subclasses to make things easier. And in particular, there's one called conv learner, which is something that will create a convolutional neural network for you. And we'll be learning a lot about that over the next few lessons. But for now, just know that to create a learner for a convolutional neural network, you just have to tell it two things. The first is, what's your data? And not surprisingly, it takes a data bunch. And the second thing you need to tell it is, what's your model? Or what's your architecture? So as we'll learn, there are lots of different ways of constructing a convolutional neural network. But for now, the most important thing for you to know is that there's a particular kind of model called a ResNet, which works extremely well nearly all the time. And so for a while at least, you really only need to be choosing between two things, which is what size ResNet do you want? Okay, just basically, how big is it? And we'll learn all about the details of what that means. But there's one called a ResNet 34, and there's one called a ResNet 50. And so when we're getting started with something, I'll pick the smaller one because it'll train faster. So that's kind of it. That's as much as you need to know to be a pretty good practitioner about architectures for now, which is that there's two architectures, or two variants of one architecture that work pretty well, ResNet 34 and ResNet 50. Start with the smaller one and see if it's good enough. So that is all the information we need to create a convolutional neural network learner. There's one other thing I'm going to give it though, which is a list of metrics. Metrics are literally just things that get printed out as it's training. So I'm saying I would like you to print out the error rate, please. Now you can see the first time I ran this on a newly installed box, it downloaded something. What's it downloading? It's downloading the ResNet 34 pre-trained weights. Now what this means is that this particular model has actually already been trained for a particular task. And that particular task is that it was trained on looking at about 1.5 million pictures of all kinds of different things, 1,000 different categories of things, using a data set called ImageNet. And so we can download those pre-trained weights so that we don't start with a model that knows nothing about anything, but we actually start with a model that knows how to recognize the 1,000 categories of things in ImageNet. Now, I'm not sure, but I don't think all of these 37 categories of pet were in ImageNet, but there were certainly some kinds of dog, and there were certainly some kinds of cat. So this pre-trained model already knows quite a little bit about what pets look like, and it certainly knows quite a lot about what animals look like and what photos look like. So the idea is that we don't start with a model that knows nothing at all, but we start by downloading a model that knows something about recognizing images already. So it downloads for us automatically the first time we use it, a pre-trained model. And then from now on, it won't need to download it again. It'll just use the one we've got. This is really important. We're going to learn a lot about this. It's kind of the focus of the whole course, which is how to do, this is called transfer learning. How to take a model that already knows how to do something pretty well and make it so that it can do your thing really well. We take a pre-trained model and then we fit it so that instead of predicting the 1,000 categories of ImageNet with the ImageNet data, it predicts the 37 categories of pets using your pet data. And it turns out that by doing this, you can train models in 1/100th or less of the time of regular model training with 1/100th or less of the data of regular model training. In fact, potentially many thousands of times less. Remember I showed you the slide of Nikhil's Lesson 1 project from last year? He used 30 images. And there's not cricket and baseball images in ImageNet, right? But it just turns out that ImageNet's already so good at recognizing things in the world that just 30 examples of people playing baseball and cricket was enough to build a nearly perfect classifier. Okay. Now, you would naturally be potentially saying, well, wait a minute, how do you know that it can actually recognize pictures of people playing cricket versus baseball in general? Maybe it just learned to recognize those 30. Maybe it's just cheating, right? And that's called overfitting. We'll be talking a lot about that during this course, right? But overfitting is where you don't learn to recognize pictures of, say, cricket versus baseball, but just these particular cricketers and these particular photos and these particular baseball players and these particular photos. We have to make sure that we don't overfit. And so the way we do that is using something called a validation set. A validation set is a set of images that your model does not get to look at. And so these metrics, like in this case error rate, get printed out automatically using the validation set, a set of images that our model never got to see. When we created our data bunch, it automatically created a validation set for us. Okay? And we'll learn lots of ways of creating and using validation sets, but because we try to bake in all of the best practices, we actually make it nearly impossible for you not to use a validation set. Because if you're not using a validation set, you don't know if you're overfitting. Okay? So we always print out the metrics on a validation set, we always hold it out, we always make sure that the model doesn't touch it. That's all done for you. Okay? And that's all built into this data bunch object. So now that we have a conv learner, we can fit it. You can just use a method called fit, but in practice, you should nearly always use a method called fit one cycle. We'll learn more about this during the course, but in short, one cycle learning is a paper that was released, I'm trying to think, a few months ago, less than a year ago.
March?
So a few months ago, and it turned out to be dramatically better, both more accurate and faster than any previous approach. So again, I don't want to teach you how to do 2017 deep learning. Right? In 2018, the best way to fit models is to use something called one cycle. We'll learn all about it, but for now, just know you should probably type learn.fit one cycle. Right? If you forget how to type it, you can start typing a few letters and hit tab, okay, and you'll get a list of potential options. Right? And then if you forget what to pass it, you can press Shift tab, and it'll show you exactly what to pass it. So you don't actually have to type help. And again, this is kind of nice that we have all the types here because we can see cycle length, we'll learn more about what that is shortly, is an integer, and then max learning rate could either be a float or a collection or whatever, and so forth. And you can see that momentums will default to this tuple, so on and so forth. Okay, so for now, just know that this number 4 basically decides how many times do we go through the entire data set? How many times do we show the data set to the model so that it can learn from it? Each time it sees a picture, it's going to get a little bit better, but it's going to take time, and it means it could overfit. If it sees the same picture too many times, it'll just learn to recognize that picture, not pets in general. We'll learn all about how to tune this number during the next couple of lessons, but starting out with 4 is a pretty good start, just to see how it goes. And you can actually see after 4 epochs, or 4 cycles, we've got an error rate of 6%. So a natural question is, how long did that take? That took 1 minute and 56 seconds. Right. So we're paying, 60 cents an hour. We just paid for 2 minutes of time. I mean, we actually pay for the whole time that it's on and running, but we use 2 minutes of compute time. And we got an error rate of 6%. So 94% of the time, we correctly picked the exact right one of those 94 dog and cat breeds, which feels pretty good to me. But to get a sense of how good it is, maybe we should go back and look at the paper. Just remember, I said the nice thing about using academic papers or Kaggle data sets is we can compare our solution to whatever the best people in Kaggle did or whatever the academics did. So this particular data set of pet breeds is from 2012. And if I scroll through the paper, you'll generally find in any academic paper there'll be a section called experiments about 2/3 of the way through. And if you find the section on experiments, then you can find the section on accuracy. And they've got lots of different models. And their models, as you'll read about in the paper, are extremely kind of pet specific. They learn something about how pet heads look and how pet bodies look and pet images in general look, and they combine them all together. And once they use all of this complex code and math, they got an accuracy of 59%. Okay, so in 2012, this highly pet-specific analysis got an accuracy of 59%. These were the top researchers from Oxford University. Today, in 2018, with basically, if you go back and look at actually how much code we just wrote, it's about 3 lines of code. The other stuff is just printing out things to see what we're doing. We got 94%, so 6% error. So like that gives you a sense of, how far we've come with deep learning, and particularly with PyTorch and FastAI, how easy things are. Yeah. So before we take a break, I just want to check to see if we've got any. And just remember, if you're in the audience and you see a question that you want asked, please click the love heart next to it so that Rachel knows that you want to hear about it. Also, if there is something with 6 likes and Rachel didn't notice it, which is quite possible, just quote it in a reply and say, hey, Rachel, this one's got 6 likes. Okay, so what we're going to do is we're going to take a 8-minute break. So we'll come back at 8:05. So where we got to was we just trained a model. We don't exactly know what that involved or how it happened, but we do know that with 3 or 4 lines of code, we built something which smashed the accuracy of the state-of-the-art of 2012. 6% error certainly sounds like pretty impressive for something that can recognize different dog breeds and cat breeds. But we don't really know why it works, but we will. That's okay. Right? And in terms of getting the most out of this course, we very, very regularly hear after the course is finished the same basic feedback, which this is literally copy and pasted from the forum. I fell into the habit of watching the lectures too much and Googling too much about concepts without running the code. At first I thought I should just read it and then research the theory. Okay? And we keep hearing people saying, my number one regret is I just spent 70 hours doing that. And at the very end, I started running the code, and it turned out I learned a lot more. So please, run the code. Really run the code. I should have spent the majority of my time on the actual code in the notebooks, running it, seeing what goes in, and seeing what comes out. So your most important skills to practice are learning, and we're going to show you how to do this in a lot more detail, but understanding what goes in and what goes out. So we've already seen an example of looking at what goes in, which is data.showBatch. And that's going to show you examples of labels and images. And so next we're going to be seeing how to look at what came out. Right? So that's the most important thing to study. As I said, the reason we've been able to do this so quickly is heavily because of the FastAI library. Now, the FastAI library is pretty new, but it's already getting an extraordinary amount of traction. As you've seen, all of the major cloud providers either support it or are about to support it. A lot of researchers are starting to use it. It's making a lot of things a lot easier, but it's also making new things possible. And so really understanding the FastAI software is something which is going to take you a long way. And the best way to really understand the FastAI software well is by using the FastAI documentation. And we'll be learning more about the FastAI documentation shortly. So how does it compare? I mean, there's really only one major other piece of software like FastAI that is something that tries to make deep learning easy to use. and that's Keras. Keras is a really terrific piece of software. We actually used it for the previous courses until we switched to FastAI. It runs on top of TensorFlow. It was kind of the gold standard for making deep learning easy to use before, but life is much easier with FastAI. So if you look, for example, at the last year's course exercise, which is getting dogs versus cats, FastAI lets you get much more accurate, less than half the error on a validation set, of course. Training time is less than half the time. Lines of code is about a sixth of the lines of code. And the lines of code are more important than you might realize, because those 31 lines of Keras code involve you making a lot of decisions, setting lots of parameters, doing lots of configuration. So that's all stuff where you have to know how to set those things to get kind of best practice results. Whereas these 5 lines of code, anytime we know what to do for you, we do it for you. Anytime we can pick a good default, we pick it for you. Okay? So hopefully you'll find this a really useful library, not just for learning deep learning, but for taking it a very long way. How far can you take it? Well, as you'll see, all of the research that we do at FastAI uses the library. And an example of the research we did, which was recently featured in Wired, describes a new breakthrough in natural language processing, which people are calling the ImageNet moment, which is basically we broke a new state-of-the-art result in text classification, which OpenAI then built on top of our paper to do with more compute and more data and some different tasks to take it even further. And this is an example of something that we've done in the last 6 months in conjunction actually with my colleague Sebastian Ruder. An example of something that's being built in the FastAI library, and you're going to learn how to use this brand new model in 3 lessons time. And you're actually going to get this exact result from this exact paper yourself. Another example, one of our alums, Hamel Hussain, who you'll come across on the forum plenty because he's a great guy, very active, built a new system for natural language semantic code search. You can find it on GitHub, where you can actually type in English sentences and find snippets of code that do the thing you ask for. And again, that's being built with the FastAI library using the techniques you'll be learning in the next 7 weeks.
In production.
In production, yeah. Well, it's. I think at this stage it's part of their experiments platform, so it's kind of pre-production, I guess. And so the best place to learn about these things and get involved in these things is on the forums, where as well as categories for each part of the course, there's also a general category for deep learning where people talk about research papers, applications, so on and so forth. So even though today we're kind of going to focus on a small number of lines of code to do a particular thing, which is image classification, and we're not learning much math or theory or whatever, over these 7 weeks, and then part 2, another 7 weeks, we're going to go deeper and deeper and deeper. And so where can that take you? I want to give you some examples. That there is Sarah Hooker. She did our first course a couple of years ago. Her background was economics. Didn't have a background in coding, math, computer science. I think she started learning to code 2 years before she took our course. She helped develop something she started a nonprofit called Delta Analytics. They helped build this amazing system where they attached old mobile phones to trees in the Kenyan rainforests and used it to listen for chainsaw noises, and then they used deep learning to figure out when there was a chainsaw being used, and then they had a system set up to alert rangers to go out and stop illegal deforestation in the rainforests. So that was something that she was doing while she was in the course as part of her kind of class projects. What's she doing now? She is now a Google Brain researcher, which I guess is one of the top, if not the top place to do deep learning. She's just been publishing some papers. Now she is going to Africa to set up Google Brain's first deep learning AI research center in Africa. Now I'll say, like, she worked her ass off. You know, she really, really invested in this course, not just doing all of the assignments, but also going out and reading Ian Goodfellow's book and doing lots of other things, but it really shows where somebody who has no computer science or math background at all can be now one of the world's top deep learning researchers and doing very valuable work. Another example from our most recent course, Christine Payne, she is now at OpenAI. And you can find her post and actually listen to her music samples she actually built something to do automatically create chamber music compositions that you can play and you can listen to online. And so, again, it's her background, math and computer science. Actually, that's her there, classical pianist. Now, I will say she's not your average classical pianist. She's a classical pianist who also has a master's in medical research from Stanford and studied neuroscience and was a high-performance computing expert at D.E. Shaw and was valedictorian at Princeton. Anyway, she, very annoying person, good at everything she does. But, I think it's really cool to see how a kind of a domain expert, in this case the domain of playing piano, can go through the Fast AI course and come out the other end at, I guess OpenAI would be, of the three top research institutes, Google Brain and OpenAI would be two of them, probably along with DeepMind. And interestingly, actually, one of our other students, or I should say alumni of the course, recently interviewed her for a blog post series he's doing on top AI researchers. And she said one of the most important pieces of advice she got was from me. And she said the piece of advice was pick one project, do it really well, make it fantastic. Okay, so that was the piece of advice she found the most useful. And we're going to be talking a lot about you doing projects and making them fantastic during this course. Having said that, I don't really want you to go to AI or Google Brain. What I really want you to do is go back to your workplace or your passion project and apply these skills there, right? Like, let me give you an example. MIT released a deep learning course, and they highlighted in their announcement for this deep learning course this medical imaging example. And one of our students, Alex, who is a radiologist, said, you guys just showed a model overfitting. I can tell because I'm a radiologist, and this is not what this would look like on a chest film. This is what it should look like, and this, as a deep learning practitioner, this is how I know that this is what happened in your model. So Alex is combining his knowledge of radiology and his knowledge of deep learning to assess MIT's model from just two images very accurately, right? And so this is actually what I want most of you to be doing, is to take your domain expertise and combine it with the deep learning practical aspects that you'll learn in this course and bring them together like Alex is doing here. And so a lot of radiologists have actually gone through this course now and have built journal clubs and American Council of Radiology practice groups. There's a Data Science Institute at the ACR now and so forth, and Alex is one of the people who's providing kind of a lot of leadership in this area. I would love you to do the same kind of thing that Alex is doing, which is to really bring deep learning leadership into your industry, into your social impact project, whatever it is that you're trying to do. So another great example was Melissa Fabros, who was a English literature PhD. I think she studied like gendered language in English literature or something. And actually, Rachel in a previous job taught her to code, I think. And then she came into the Fast AI course, and she helped Kiva, a micro-lending social impact organization, to build a system that can recognize faces. Why is that necessary? Well, we're going to be talking a lot about this. But because most AI researchers are white men, most computer vision software can only recognize white male faces effectively. In fact, I think it was IBM's system is like 99.8% accurate on common white face men versus 60% accurate, 65% accurate on dark-skinned women. So it's like, what is that, like 30 or 40 times worse for black women versus white men. And this is really important because for Kiva, black women are, perhaps the most common user base for their microlending platform. So Melissa, after taking our course, and again, working her ass off and being super intense in her study and her work, won this $1 million AI challenge for her work for Kiva. Karthik did our course and realized that the thing he wanted to do wasn't at his company, it was something else, which is to help blind people to understand the world around them, so he started a new startup. You can find it now, it's called Envision. You can download the app, you can point your phone at things, and it will tell you what it sees. And I actually talked to a blind lady about these kinds of apps the other day, and she confirmed to me this is a super useful thing for visually disabled users. And it's the level that you can get to with the content that you're going to get over these 7 weeks and with this software can get you right to the cutting edge in areas you might find surprising. For example, I helped a team of some of our students and some collaborators on actually breaking the world record for training. Remember I mentioned the ImageNet dataset? Lots of people want to train on the ImageNet dataset. We smashed the world record for how quickly you can train it. We use standard AWS cloud infrastructure, cost of $40 of compute to train this model using, again, Fast AI library, the techniques that we learn in this course. So it can really take you a long way. So don't be kind of put off by this, what might seem pretty simple at first. We're going to get deeper and deeper. You can also use it for other kinds of passion project. So Helena Sarin, actually, you should definitely check out her Twitter account, Flagalista. This art is basically a new style of art that she's developed, which combines her painting and drawing with generative adversarial models to create these extraordinary results. And so I think this is super cool. I mean, she's not a professional artist. She is a professional software developer, but she just keeps on producing these beautiful results. And when she started, her art had not really been shown anywhere or discussed anywhere. Now there's recently been some quite high-profile articles describing how she is creating a new form of art. Again, this has come out of the Fast AI course that she developed these skills. Or equally important, Brad Kensler, who figured out how to make a picture of Kanye out of pictures of Patrick Stewart's head. Also something you will learn to do if you wish to. This particular type of what's called style transfer was a really interesting tweak that allowed him to do some things that hadn't quite been done before. And this particular picture helped him to get a job as a deep learning specialist at AWS. So there you go. Another interesting example, another alumni actually worked at Splunk as a software engineer, and he designed an algorithm after like lesson 3, which basically turned out at Splunk to be fantastically good at identifying fraud. We'll talk more about it shortly. If you've seen Silicon Valley, the HBO series, the Hot Dog Not Hot Dog app, that's actually a real app you can download, and it was actually built by Tim Onglade as a Fast AI student project. So there's a lot of cool stuff that you can do. Yes, it was Emmy nominated. So I think we only have one Emmy nominated Fast AI alumni at this stage. So please help change that. All right. The other thing, is the forum threads can kind of turn into these really cool things. So Francisco, who's actually here in the audience, he's a really boring McKinsey consultant like me, right? So Francisco and I both have this shameful past that we were McKinsey consultants, but we left and we're okay now. And he started this thread saying like, oh, this stuff we've just been learning about building NLP in different languages, let's try and do lots of different languages. And he started this thing called the Language Model Zoo. And out of that, there's now been an academic competition was won in Polish that led to an academic paper, Thai state-of-the-art, German state-of-the-art. Basically, students have been coming up with new state-of-the-art results across lots of different languages, and this all is entirely being done by students working together through the forum. So please, get on the forum, but don't be intimidated, Because remember, a lot of the, everybody you see on the forum, the vast majority post all the damn time, right? They've been doing this a lot, and they do it a lot of the time. And so at first it can feel intimidating because it can feel like you're the only new person there. But you're not, right? All of you people in the audience, everybody who's watching, everybody who's listening, you're all new people, right? And so when you just get out there and say like, okay, all you people getting new state-of-the-art results in German language modeling, I can't start my server. I try to click the notebook and I get an error. What do? People will help you. Okay, just make sure you provide all the information. This is the, I'm using Paperspace. This was the particular instance I tried to use. Here's a screenshot of my error. People will help you, okay? Or if you've got something to add. So if people are talking about crop yield analysis and you're a farmer and you think, oh, I've got something to add, so please mention it. Even if you're not sure it's exactly relevant, it's fine, just get involved. And because remember, everybody else on the forum started out also intimidated, right? We all start out not knowing things. And so just get out there and try it. Okay, so let's get back and do some more coding. Yes, Rachel, do we have some questions?
Yeah, there's just a question from earlier about why you're using ResNet as opposed to Inception.
So the question is about this architecture. So there are lots of architectures to choose from, and it would be fair to say there isn't one best one. But if you look at things like the Stanford Dawnbench benchmark for ImageNet classification, you'll see in first place and second place and third place and fourth place is FastAI, Jeremy Howard from FastAI, Jeremy Howard, FastAI, Yaroslav's from the Department of Defense Innovation Team, Google, ResNet, 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 ResNet. ResNet's good enough, okay? So it's fine. There are other architectures. The main reason you might want a different architecture is if you want to do edge computing, so if you want to create a model that's going to sit on somebody's mobile phone. Having said that, even there, most of the time I reckon the best way to get a model onto somebody's mobile phone is to run it on your server and then have your mobile phone app talk to it. It really makes life a lot easier and you get a lot more flexibility. But if you really do need to run something on a low-powered device, then there are some special architectures for that. So the particular question was about Inception. That's another architecture which tends to be pretty memory intensive ResNet. So Inception tends to be pretty memory intensive, but it's okay. It's also it's not terribly resilient. One of the things we try to show you is stuff which just tends to always work, even if you don't quite tune everything perfectly. So ResNet tends to work pretty well across a wide range of different kind of details around choices that you might make. So I think it's pretty good. So we've got this trained model, and so what's actually happened, as we'll learn, is it's basically creating a set of weights. If you've ever done anything like linear regression or logistic regression, you'll be familiar with coefficients. We basically found some coefficients and parameters that work pretty well, and it took us 1 minute and 56 seconds. So if we want to start doing some more playing around and come back later, we probably should save those weights so we can save that 1 minute and 56 seconds. So you can just go learn.save and give it a name. Okay. It's going to put it in a model subdirectory in the same place the data came from. So if you save different models for different data bunches from different data sets, they'll all be kept separate, so don't worry about it. All right, so we talked about how the most important things are how to learn what goes into your model, what comes out. We've seen one way of seeing what goes in. Now let's see what comes out. Okay, so this is the other thing you need to get really good at. So to see what comes out, we can use this class called classification interpretation. And we're going to use this factory method from learner. So we pass in a learn object. So remember, a learn object knows two things. What's your data? And what is your model? It's now not just an architecture, but it's actually a trained model inside there. And that's all the information we need to interpret that model. So we just pass in the learner, and we now have a classification interpretation object. And so one of the things we can do, and perhaps the most useful things to do, is called plot top losses. So we're going to be learning a lot about this idea of loss functions shortly. But in short, a loss function is something that tells you how good was your prediction. And so specifically that means if you predicted one class of cat with great confidence, you said, I am very, very sure that this is a Burman, but actually you were wrong, then that's going to have a high loss because you were very confident about the wrong answer. Okay, so that's what it basically means to have a high loss. So by plotting the top losses, we're going to find out what were the things that we were the most wrong on, or the most confident about but we got wrong. So you can see here, it prints out three things. German Shorthead, or four things. Beagle, 7.04, 0.92. Well, what do they mean? Perhaps we should look at the documentation. So we've already seen help, right? And help just prints out a quick little summary. But if you want to really see how to do something, use doc. And doc tells you the same information as help, but it has this very important thing, which is show in docs. So when you click on show in docs, it pops up the documentation for that method or class or function or whatever. It starts out by showing us the same information about what are the parameters it takes, along with the doc string, but then tells you more information. So in this case, amongst other things, it tells me the title of each shows the prediction, the actual, the loss, and the probability that was predicted. So for example, and you can see there's actually some code you can run. So the documentation always has working code. And so in this case, it was trying things with handwritten digits. And so the first one, it was predicted to be a 7. It was actually a 3. The loss is 5.44. And the probability of the actual class was 0.07. Okay, so we did not have a high probability associated with the actual class. I can see why it thought this was a 7, but nonetheless it was wrong. So this is the documentation, okay? And so this is your friend when you're trying to figure out how to use these things. The other thing I'll mention is if you're a somewhat experienced Python programmer, you'll find the source code of FastAI really easy to read. We try to write everything in just a small number of, much less than half a screen of code, generally 4 or 5 lines of code. If you click source, you can jump straight to the source code, right? So here is the plot top losses. And this is also a great way to find out how to use the FastAI library, because every line of code here, nearly every line of code is calling stuff from the FastAI library. Okay? So don't be afraid to look at the source code. I've got another really cool trick about the documentation that you're going to see a little bit later. Okay, so that's how we can look at these top losses, and these are perhaps the most important image classification interpretation tool that we have, because it lets us see what are we getting wrong. And quite often, like in this case, if you're a dog and cat expert, you'll realize that the things it's getting wrong are breeds that are actually very difficult to tell apart, and you'd be able to look at these and say, oh, I can see why it got this one wrong. Okay? So this is a really useful tool. Another useful tool, kind of, is to use something called a confusion matrix, which basically shows you, for every actual type of dog or cat, how many times was it predicted to be that dog or cat. But unfortunately, in this case, because it's so accurate, this diagonal basically says, oh, it's pretty much right all the time. And you can see there's some slightly darker ones, like a 5 here, but it's really hard to read exactly what that combination is. So what I suggest you use is, instead of, if you've got lots of classes, don't use a confusion matrix. But this is my favorite named function in FastAI. I'm very proud of this. You can call most confused. And most confused will simply grab out of the confusion matrix the particular combinations of predicted and actual that it got wrong the most often. So in this case, the Staffordshire Bull Terrier was what it should have predicted, and instead it predicted an American Pit Bull Terrier, and so forth. It should have predicted a Siamese and actually predicted Burma. That happened 4 times. this particular combination happens 6 times. So this is, again, a very useful thing, because you can look and you can say, like, with my domain expertise, does it make sense that that would be something that was confused about? So these are some of the kinds of tools you can use to look at the output. Let's make our model better. So how do we make the model better? We can make it better using fine-tuning. So far we fitted 4 epochs, and it ran pretty quickly. And the reason it ran pretty quickly is that there was a little trick we used. These deep learning models, these convolutional networks, they have many layers. We'll learn a lot about exactly what layers are, but for now, just know it goes through computation. What we did was we added a few extra layers to the end, and we only trained those. We basically left most of the model exactly as it was. So that's really fast. And if we're trying to build a model of something that's similar to the original pre-trained model, so in this case similar to the ImageNet data, that works pretty well. But what we really want to do is actually go back and train the whole model. So this is why we pretty much always use this 2-stage process. So by default, when we call fit or fit one cycle on a conv learner, it'll just fine-tune these few extra layers added to the end, and it'll run very fast. It'll basically never overfit. But to really get it good, you have to call unfreeze. And unfreeze is the thing that says, please train the whole model. And then I can call fit one cycle again, and the error got much worse. Okay, why? In order to understand why, we're actually going to have to learn more about exactly what's going on behind the scenes. So let's start out by trying to get an intuitive understanding of what's going on behind the scenes. And again, we're going to do it by looking at pictures. We're going to start with this picture. These pictures come from a fantastic paper by Matt Zeiler, who nowadays is CEO of Clarify, which is a very successful computer vision startup, and his supervisor of his PhD, Rob Fergus. And they created a paper showing how you can visualize the layers of a convolutional neural network. So a convolutional neural network will learn mathematically about what the layers are shortly, but the basic idea is that your red, green, and blue pixel values, that are numbers from 0 to 255, go into a simple computation, the first layer, and something comes out of that, and then the result of that goes into a second layer, and the result of that goes into a third layer, and so forth. And there can be up to 1,000 layers of a neural network. ResNet 34 has 34 layers, ResNet 50 has 50 layers. But let's look at layer 1. There's this very simple computation. It's a convolution. If you know what they are, we'll learn more about them shortly. What comes out of this first layer? Well, we can actually visualize the specific coefficients, the specific parameters, by drawing them as a picture. There's actually a few dozen of them in the first layer, so we won't draw all of them, but let's just look at 9 at random. So here are 9 examples of the actual coefficients from the first layer. And so these operate on groups of pixels that are next to each other. And so this first one basically finds groups of pixels that have a little diagonal line in this direction. This one finds diagonal lines in the other direction. This finds gradients that go from yellow to blue in this direction. This one finds gradients that go from pink to green in this direction, and so forth. And so they're very, very simple little filters. That's layer 1 of a ImageNet pre-trained convolutional neural net. Layer 2 takes the results of those filters and does a second layer of computation. And it allows it to create, so here are 9 examples of kind of a way of visualizing this, one of the second layer features. And you can see it's basically learned to create something that looks for corners, top left corners. And this one has learned to find things that find right-hand curves. And this one has learned to find things that find little circles. Right? So you can see how layer 2, like this is the easiest way to see it. In layer 1, we have things that can find just one line. In layer 2, we can find things that have 2 lines joined up, or 1 line repeated. If you then look over here, these 9 show you 9 examples of actual bits of actual photos that activated this filter a lot. Right? So in other words, this little bit of function, math function here, was good at finding these kind of window corners and stuff like that. This little circly one was very good at finding bits of photos that had circles in. Okay, so this is the kind of stuff you've got to get a really good intuitive understanding for. It's like the start of my neural net's going to find simple, very simple gradients and lines. The second layer can find very simple shapes. The third layer can find combinations of those. So now we can find repeating patterns of two-dimensional objects. Or we can find kind of lines that join together. Or we can find, well, what are these things? Well, let's find out. What is this? Let's go and have a look at some bits of picture that activated this one highly. Oh, mainly they're bits of text, although sometimes windows. So it seems to be able to find kind of like repeated horizontal patterns. And this one here seems to be able to find kind of edges of fluffy or flowery things. This one here is kind of finding geometric patterns. Right? So layer 3 was able to take all the stuff from layer 2 and combine them together. Layer 4 can take all the stuff from layer 3 and combine them together. And by layer 4, we've got something that can find dog faces. And let's see what else we've got here. Yeah, various kinds of, oh, here we are, bird legs. So you kind of get the idea. And so by layer 5, we've got something that can find the eyeballs of birds and lizards, or faces of particular breeds of dogs, and so forth. So you can see how by the time you get to layer 34, you can find specific dog breeds and cat breeds, right? This is kind of how it works. So when we first fine-tuned that pre-trained model, we kept all of these layers that you've seen so far. And we just trained a few more layers on top of all of those sophisticated features that had already been created. Right? And so now we're fine-tuning, we're going back and saying, let's change all of these. We'll start with them where they are, right? But let's see if we can make them better. Now, it seems very unlikely that we can make these layer 1 features better. Like, it's very unlikely that the definition of a diagonal line is going to be different when we look at dog and cat breeds versus the ImageNet data that this was originally trained on. So we don't really want to change layer 1 very much, if at all. Whereas the last layers, this thing of like types of dog face, seems very likely that we do want to change that. Right? So you kind of want this intuition, this understanding that the different layers of a neural network represents different levels of kind of semantic complexity. So this is why our attempt to fine-tune this model didn't work, is because we actually, by default, it trains all the layers at the same speed, right? Which is to say it'll update those like things representing diagonal lines and gradients just as much as it tries to update the things that represent the exact specifics of what an eyeball looks like. So we have to change that. Okay? And so to change it, we first of all need to go back to where we were before. Okay? We just broke this model, right? It's much worse than it started out. So if we just go load, this brings back the model that we saved earlier. Remember we saved it as stage 1? Okay? So let's go ahead and load that back up. So that's now, our model's back to where it was before we killed it. And let's run Learning Rate Finder. We'll learn about what that is next week. But for now, just know this is the thing that figures out what is the fastest I can train this neural network at without making it zip off the rails and get blown apart. Okay, so we can call learn.lrfind, and then we can go learn.recorder.plot, and that will plot the result of our LR finder. And what this basically shows you is there's this key parameter that we're going to learn all about called the learning rate. And the learning rate basically says how quickly am I updating the parameters in my model. And you can see that what happens is, as this bottom one here shows me what happens as I increase the learning rate, and this one here shows what's the result, what's the loss. And so you can see once the learning rate gets past 10 to the negative 4, my loss gets worse. Okay? So it actually so happens, in fact I can check this, if I press Shift Tab here, my learning rate defaults to 0.003. So my default learning rate is about here. So you can see why our loss got worse, right? Because we're trying to fine-tune things now, we can't use such a high learning rate. So based on the learning rate finder, I tried to pick something, well before it started getting worse. So I decided to pick 1e neg 6. So I decided I'm going to train at that rate. But there's no point training all the layers at that rate, because we know that the later layers worked just fine before when we were training much more quickly. Again, it was the default, which was, to remind us, 0.003. So what we can actually do is we can pass a range of learning rates to learn.fit. And we do it like this. You use this keyword in Python. You may have come across it before. It's called slice. And that can take a start value and a stop value. And basically what this says is train the very first layers at a learning rate of 1e neg 6, and the very last layers at a rate of 1e neg 4, and then kind of distribute all the other layers across that, between those two values equally. So we're going to see that in a lot more detail, right? But basically, for now, this is kind of a good rule of thumb, is to say after you unfreeze, so this is the thing that's going to train the whole thing, pass a max learning rate parameter, pass it a slice, make the second part of that slice about 10 times smaller than your first stage. So our first stage defaulted to about 1e neg 3, so let's use about 1e neg 4. And then this one should be a value from your learning rate finder, which is well before things started getting worse. And you can see things are starting to get worse maybe about here. So I picked something that's at least 10 times smaller than that. So if I do that, then I get 0.05788. So I don't quite remember what we got before. Yeah, a bit better, right? So we've gone down from a 6.1% to a 5.7%. So that's about a 10 percentage point relative improvement with another 58 seconds of training. So I would perhaps say for most people, most of the time, these two stages are enough to get pretty much a world-class model. You won't win a Kaggle competition, particularly because now a lot of Fast AI alumni are competing on Kaggle, and this is the first thing that they do. But, in practice, you'll get something that's, about as good in practice as the vast majority of practitioners can do. We can improve it by using more layers, and we'll do this next week by basically doing a ResNet 50 instead of a ResNet 34. You can try running this during the week if you want to. You'll see it's exactly the same as before, but I'm using ResNet 50 instead of ResNet 34. What you'll find is it's very likely if you try to do this, you will get an error. And the error will be your GPU has run out of memory. And the reason for that is that ResNet 50 is bigger than ResNet 34. And therefore it has more parameters, and therefore it uses more of your graphics card's memory, which is totally separate to your normal computer RAM. This is GPU RAM. If you're using the kind of default Salamander, AWS, and so forth suggestion, then you'll be having 16 gig of GPU memory. The card I use most of the time has 11 gig of GPU memory. The cheaper ones have 8 gig of GPU memory. And that's kind of the main range you tend to get. If yours has less than 8 gig of GPU memory, it's going to be frustrating for you. Anyway, so you'll be somewhere around there. And it's very likely that when you try to run this, you'll get an out-of-memory error. And that's because it's just trying to do too many parameter updates for the amount of RAM you have. And that's easily fixed. This image data bunch constructor has a parameter at the end, batch size, BS for batch size. And this basically says, how many images do you train at one time? If you run out of memory, just make it smaller. Okay? So this worked for me on an 11 gig card. It probably won't work for you if you've got an 8 gig card. If you do, just make that 32. It's fine to use a smaller batch size. It might take a little bit longer. That's all. Okay? If you've got a bigger, like a 16 gig, you might be able to get away with 64. Okay? So that's just one number you'll need to try during the week. And again, we feed it for a while, and we get down to a 4.4% error rate. So this is pretty extraordinary. I was pretty surprised because, when we first did in the first course just cats versus dogs, we were kind of getting somewhere around a 3% error for something where you've got a 50% chance of being right, and the two things look totally different. So the fact that we can get a 4.4% error for such a fine-grained thing, it's quite extraordinary. In this case, I unfroze it and fitted a little bit more, went from 4.4 to 4.35, it's a tiny improvement. Basically, ResNet 50 is already a pretty good model. It's interesting because, again, you can call most confused here, and you can see the kinds of things that it's getting wrong. And I actually, depending on when you run it, you're going to get slightly different numbers, but you'll get roughly the same kinds of things. So quite often I find that ragdoll and Berman are things that it gets confused, and I actually have never heard of either of those things. So I actually looked them up on the internet, and I found a page on the cat site called "Is This a Berman or a Ragdoll?" And there is a long thread of cat experts arguing intensely about which it is. So I feel fine that my computer had problems. I found something similar. I think it was this Pit Bull versus Staffordshire Bull Terrier. Apparently the main difference is the particular kennel club guidelines as to how they are assessed. But some people think that one of them might have a slightly redder nose. So this is the kind of stuff where actually, even if you're not a domain expert, it helps you become one, right? Because I now know more about which kinds of pet breeds are hard to identify than I used to. So model interpretation works both ways. So what I want you to do this week is to run this notebook, make sure you can get through it. But then what I really want you to do is to get your own image data set. And actually, Francisco, who I mentioned earlier, he started the Language Stew model thread, and he's now helping to TA the course. He's actually putting together a guide that will show you how to download data from Google Images, so you can create your own data set to play with. But before I do, I want to...
There's also one more question.
Okay, I'll come back to that in a moment. Before I do, I want to show you how to create labels in lots of different ways, because your data set, wherever you get it from, won't necessarily be that kind of regex-based approach. It could be in lots of different formats. So to show you how to do this, I'm going to use the MNIST sample. MNIST is pictures of hand-drawn numbers. Just because I want to show you different ways of creating these data sets. The MNIST sample basically looks like this. So I can go path.ls, okay? And you can see it's got a training set and a validation set already. So basically the people that put together this data set have already decided what they want you to use as a validation set. Okay, so if we go path/train.ls, you'll see there's a folder called 3 and a folder called 7. Right? Now this is really, really common way to give people labels. It's basically to say, oh, everything that's a 3, I'll put in a folder called 3. Everything that's a 7, I'll put in a folder called 7. Right? This is often called an ImageNet style data set, because this is how ImageNet is distributed. So if you have something in this format where the labels are just whatever the folder's called, you can say from folder. Okay? And that will create an image data bunch for you. And as you can see, 3, 7, it's created the labels just by using the folder names. Another possibility, and as you can see, we can train that, get 99.55% accuracy, blah, blah, blah. Another possibility, and for this MNIST sample I've got both, it might come with a CSV file that would look something like this. For each file name, what's its label? Now in this case, the labels aren't 3 or 7, they're 0 or 1, which is basically, is it a 7 or not? Right? So that's another possibility. So if this is how your labels are, you can use from CSV. And if it's called labels.csv, you don't even have to pass in a file name. If it's called anything else, then you can pass in the CSV labels file name. Okay, so that's how you can use a CSV. Again, there it is. This is now, is it a 7 or not? Another possibility, and then you can call data.classes to see what it found. Another possibility is, as we've seen, is you've got paths that look like this. And so in this case, this is the same thing. These are the folders, right? I could actually grab the label by using a regular expression. And so here's the regular expression. So we've already seen that approach. And again, you can see data.classes has found it. So what if it's something that's in the file name or the path, but it's not just a regular expression, it's more complex? You can create an arbitrary function that extracts a label from the file name or path. And in that case, you would say from name and function. Another possibility is that you did something even more flexible than that, and so you're going to write some code to create an array of labels. And so in that case, you can just pass in from lists. So here I've created an array of labels. Here are my labels. Here's from lists, okay? And then I just pass in that array. So you can see there's lots of different ways of creating labels. So during the week, try this out. Now you might be wondering, how would you know to do all these things? Like, where am I going to find this kind of information, right? How do you possibly know to do all this stuff? So I'll show you something incredibly cool. Let's grab this function. And do you remember, to get documentation, we type doc. And here's the documentation for the function, and I can click Show in Docs. And it pops up the documentation. So here's the thing. Every single line of code I just showed you, I took it this morning and I copied and pasted it from the documentation. So you can see here the exact code that I just used. So the documentation for FastAI doesn't just tell you what to do, but step to step how to do it. And here is perhaps the coolest bit. If you go to FastAI, FastAI_docs, and click on docs source, it turns out that all of our documentation is actually just Jupyter notebooks. So in this case, I was looking at vision.data. So here is the vision.data notebook. You can download this repo, you can git clone it, and if you run it, you can actually run every single line of the documentation yourself. Okay, so all of our docs is also code. And so like this is the kind of the ultimate example to me of experimenting, right? Is that you can now experiment, and you'll see in GitHub it doesn't quite render properly because GitHub doesn't quite know how to render notebooks properly. But if you git clone this and open it up in Jupyter, you can see it. And so now, anything that you read about in the documentation, nearly everything in the documentation has actual working examples in it with actual data sets that are already sitting in there in the repo for you. And so you can actually try every single function in your browser. Try seeing what goes in and try seeing what comes out.
There's a question, will the library use multi-GPU in parallel by default?
The library will use multiple CPUs by default, but just one GPU by default. We probably won't be looking at multi-GPU until part 2. It's easy to do, and you'll find it on the forum, but most people won't be needing to use that now.
And the second question is whether the library can use 3D data, such as MRI or CAT scan.
Yes, it can, and there is actually a forum thread about that already. Although that's not as developed as 2D yet, but maybe by the time the MOOC is out, it will be. So before I wrap up, I'll just show you an example of the kind of interesting stuff that you can do by doing this kind of exercise. Remember earlier I mentioned that one of our alums who works at Splunk, which is a NASDAQ-listed, big, successful company, created this new anti-fraud software. This is actually how he created it as part of a FastAI Part 1 class project. He took the telemetry of users who had Splunk Analytics installed and watched their mouse movements, and he created pictures of the mouse movements. He converted speed into color and right and left clicks into splodges. He then took the exact code that we saw with an earlier version of the software and trained a CNN in exactly the way we saw, and used that to train his fraud model. So he basically took something which is not obviously a picture, and he turned it into a picture, and got these fantastically good results for a piece of fraud analysis software. So it pays to think creatively. So if you're wanting to study sounds, a lot of people that study sounds do it by actually creating a spectrogram image and then sticking that into a ConvNet. So there's a lot of cool stuff you can do with this. So during the week, yeah, get your GPU going, try and use your first notebook, make sure that you can use lesson 1 and work through it, and then see if you can repeat the process on your own data set. Get on the forum and tell us any little success you had. It's like, oh, I spent 3 days trying to get my GPU running and I finally did. Any constraints that you hit, try it for an hour or 2, but if you get stuck, please ask. And if you're able to successfully build a model with a new data set, let us know. And I will see you next week.
Welcome to lesson 2, where we're going to be taking a deeper dive into computer vision applications and taking some of the amazing stuff that you've all been doing during the week and going even further. So let's take a look. Before we do, a reminder that we have these 2 really important topics on the forums. They're pinned at the top of the forum category. One is fact resources and official course updates. This is where if there's something useful for you to know during the course, we will post there. Nobody else can reply to that thread. So if you set that thread to watching and to notifications, you're not going to be bugged by anybody else except stuff that we think you need to know for the course. And it's got all the official information about how to get set up on each platform. Please note, a lot of people post all kinds of other tidbits about how they've set up things on previous solutions or previous courses or other places. I don't recommend you use those because these are the ones that we're testing every day and that the folks involved in these platforms are testing every day, and they definitely work. Okay, so I would strongly suggest you follow those tips. And if you do have a question about using one of these platforms, please use these discussions, not some other topic that you create, because this way people that are involved in these platforms will be able to see it and things won't get messy. And then secondly, for every lesson there will be an official updates thread for that lesson. So lesson 1 official updates, and the same thing, only FastAI people will be posting to that. You can watch it safely, and we'll have all the things like the videos, the notebooks, and so forth. And they're all wiki threads, so you can help us to make them better as well. So I mentioned the idea of watching a thread. So this is a really good idea, is that you can go to a thread, like particularly those official update ones, and click at the bottom, watching. Okay, and if you do that, that's going to enable notifications for any updates to that thread, particularly if you go into, click on your little username in the top right, preferences, and turn this on. That'll give you an email as well. Okay, so any of you that have missed some of the updates so far, go back and have a look through, because we're really trying to make sure that we keep you updated with anything that we think is important. One thing which can be more than a little overwhelming is even now, after just 1 week, the most popular thread has 1.1 thousand replies. So that's an intimidatingly large number. I've actually read every single one of them, and I know Rachel has, and I know Sylvain has, and I think Francisco has. But you shouldn't need to. What you should do is click Summarize this topic, and it'll appear like this, which is all of the most liked ones will appear, and then there'll be View 31 hidden replies or whatever in between. So that's how you navigate these giant topics. That's also why it's important you click the like button, because that's the thing that's going to cause people to see it in this recommended view. So when you come back to work, hopefully you've realized by now that on the official course website, course-v3.fast.ai, you will click Returning to Work, you will click the name of the platform you're using, and you will then follow the 2 steps. Step 1 will be how to make sure that you've got the latest notebooks, and step 2 will be how to make sure you've got the latest Python library software. Okay? They all look pretty much like this, but they're slightly different from platform to platform, so please don't use some different set of commands you read somewhere else. Only use the commands that you read about here. and that will make everything very smooth. If things aren't working for you, if you get into some kind of messy situation, which we all do, just delete your instance and start again. Unless you've got mission critical stuff there, it's the easiest way just to get out of a sticky situation. And if you follow the instructions here, you really should find it works fine. So this is what I really wanted to talk about most of all, is what people have been doing this week. If you've noticed, and a lot of you have, there's been 167 people sharing their work. And this is really cool because it's pretty intimidating to put yourself out there and say, like, I'm new to all this, but here's what I've done. And so examples of things I thought was really interesting was figuring out who's talking. Is it Ben Affleck or Joe Rogan? I thought this was really interesting. This is like actually very practical. I wanted to clean up my WhatsApp downloaded images to get rid of memes. So I actually built a little neural network. I mean, how cool is that to say like, oh yeah, I've got something that cleans up my WhatsApp. It's a deep learning application I wrote last week. Why not? Like, it's so easy now. You can do stuff like this. And then there's been some really interesting projects. One was looking at the sounds data that was used in this paper. And in this paper, they were trying to figure out what kind of sound things were. And they got, as you would expect, since they published a paper, they got a state-of-the-art of nearly 80% accuracy. Ethan Sutton then tried using the lesson 1 techniques and got 80.5% accuracy. So I think this is pretty awesome. Best as we know, it's a new state-of-the-art for this problem. Maybe somebody since then has published something. We haven't found it yet. They take all of these with a slight grain of salt, but I've mentioned them on Twitter, and lots of people on Twitter follow me, so if everybody knew that there was a much better approach, I'm sure somebody would have said so. This one is pretty cool. Suvash has a new state-of-the-art accuracy for Devanagari text recognition. I think he's got it even higher than this now. And this is actually confirmed by the person on Twitter who created the data set. I don't think he had any idea. He just posted, hey, here's a nice thing I did. And this guy on Twitter was like, oh, I made that data set. Congratulations, you've got a new record. So that was pretty cool. I really like this post from Elena Harley. She describes in quite a bit of detail about the issue of them metastasizing cancers and the use of point mutations and why that's a challenging, important problem. And she's got some nice pictures describing like what she wants to do with this and like how she can go about turning this into pictures. Hey, see, this is the cool trick, right? It's the same with this sounds one, turning sounds into pictures and then using the lesson 1 approach. And here it's turning point mutations into pictures and then using the lesson 1 approach. And what did she find? It seems that she's got a new state-of-the-art result by more than 30%, beating the previous best. Somebody on Twitter who's a VP at a genomics analysis company looked at this as well and thought it looked to be a state-of-the-art in this particular point mutation one as well. So that's pretty exciting. So you can see, when we talked about last week, this idea that this simple process is something which can take you a long way. It really can. I will mention that, something like this one in particular is using a lot of domain expertise. Like it's figuring out what picture to create. I wouldn't know how to do that because I don't even really know what a point mutation is, let alone how to create, something that visually is meaningful that a CNN could recognize. But the actual deep learning side is actually pretty straightforward. Another very cool result from Simon Willison and Natalie Down. They created a Cougar or Not web application over the weekend and won the Science Hack Day award in San Francisco. And so I think that's pretty fantastic. So lots of examples of people doing really interesting work. Hopefully this will be inspiring to you to think, wow, this is cool that I can do this with what I've learned. It can also be intimidating to think like, wow, these people are doing amazing things. But it's important to realize out of the thousands of people doing this course, I'm just picking out the kind of a few of the really amazing ones. And in fact, Simon is one of these very annoying people like Christine Payne, who we talked about last week, who seems to be good at everything he does. He created Django, one of the world's most popular web frameworks. He founded a very successful startup and blah, 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 blah. So, you know, one of these really annoying people who tends to keep being good at things. Now it turns out he's good at deep learning as well. So, you know, that's fine. You know, Simon can go and win a hackathon on his first week of playing with deep learning. Maybe it'll take you 2 weeks to win your first hackathon. That's okay. And I think like it's important to mention this because there was this really inspiring blog post this week from James Dellinger, who talked about how he created a bird classifier using the techniques from lesson 1. But what I really found interesting was at the end, he said he nearly didn't start on deep learning at all because he went to the scikit-learn website, which is one of the most important libraries of Python, and he saw this. And he describes in this blog post about how he was just like, that's not something I can do, that's not something I understand. And then this kind of realization of like, oh, I can do useful things without reading the Greek. So I thought that was a really cool message. And I really want to highlight actually Daniel Armstrong on the forum, I think really is a great role model here, which was he was saying, I want to contribute to the library. And I looked at the docs and I just found it overwhelming. And his next message 1 day later was, I don't know what any of this is. I didn't know how much there was to it. It caught me off guard. My brain shut down. But I love the way it forces me to learn so much. And then 1 day later, I just submitted my first pull request. So I think that's awesome, right? It's this kind of like, it's okay to feel intimidated. There's a lot, right? But just pick one piece and dig into it. You know, try and push a piece of code or a documentation update or create a classifier or whatever. So here's lots of cool classifiers people have built. It's been really, really inspiring. Trinidad and Tobago Islander versus Masquerader classifier, a zucchini versus cucumber classifier. This one was really nice. This was taking the dog and cat breeds thing from last week and actually doing some exploratory work to see what the main features were, and discovered that they could now create a hairiness and classifier. And so here we now have the most hairy dogs and the most bald cats. So there are, you know, interesting things you can do with interpretation. Somebody else on the forum took that and did the same thing for anime to find that they had accidentally discovered an anime hair color classifier. We can now detect the new versus the old Panamanian buses correctly. Apparently these are the new ones. I much prefer the old ones, but maybe that's just me. This was really interesting. Henry Palacci discovered that he can recognize with 85% accuracy which of 110 countries a satellite image is of, which, you know, is definitely got to be beyond human performance of just about anybody. Like, I can't imagine anybody who can do that in practice. So that was fascinating. Batik cloth classification with 100% accuracy. Dave Lawar did this interesting one. He actually went a little bit further using some techniques we'll be discussing in the next couple of courses to build something that can recognize complete or incomplete or foundation buildings and actually plot them on aerial satellite view. So lots and lots of fascinating projects. So don't worry, it's only been 1 week. It doesn't mean everybody has to have had a project out yet. A lot of the folks who already have a project out have done a previous course, so they've got a bit of a head start. But we'll see today how you can definitely create your own classifier this week. So from today, after we dig a bit deeper into really how to make these computer vision classifiers in particular work well, we're then going to look at the same thing for text. We're then going to look at the same thing for tabular data, so kind of like more like spreadsheets and databases. Then we're going to look at collaborative filtering, so kind of recommendation systems. That's going to take us into a topic called embeddings, which is basically a key underlying platform behind these applications. That will take us back into more computer vision and then back into more NLP. So the idea here is that it turns out that it's much better for learning if you kind of see things multiple times. So rather than being like, okay, that's computer vision, you won't see it again for the rest of the course, we're actually going to come back to the two key applications, NLP and computer vision, a few weeks apart, And that's going to force your brain to realize, like, oh, I have to remember this. It's not just something I can throw away. So we are, for people who have more of a hard sciences kind of background in particular, a lot of folks find this, hey, here's some code, type it in, start running it approach, rather than here's lots of theory approach, confusing and surprising and odd at first. And so for those of you, I just wanted to remind you, this basic tip, which is keep going. Now, you're not expected to remember everything yet. You're not expected to understand everything yet. You're not expected to know why everything works yet. You just want to be in a situation where you can enter the code and you can run it and you can get something happening, and then you can start to experiment and you kind of get a feel for what's going on. And then push on, right? Most of the people who have done the course and have gone on to be really successful watch the videos at least 3 times. So they kind of go through the whole lot and then go through it slowly the second time, and then they go through it really slowly the third time. And I consistently hear them say, I get a lot more out of it each time I go through. So don't pause at lesson 1 and stop until you can continue. Right? Yeah. So this approach is based on a lot of research, academic research into learning theory. And one guy in particular, David Perkins from Harvard, has this really great analogy. He's a researcher into learning theory. He describes this approach of the whole game, which is basically if you're teaching a kid to play soccer, you don't, first of all teach them about, how the friction between a ball and grass works, and then teach them how to sew a soccer ball with their bare hands, and then teach them the mathematics of parabolas when you kick something in the air. No, you say, here's a ball. Let's watch some people playing soccer. Okay, now we'll play soccer. And then you gradually over the following years learn more and more so that you can get better and better at it. So this is kind of what we're trying to get you to do, is to play soccer, which in our case is to type code and look at the inputs and look at the outputs. Okay, so let's dig into our first notebook, which is called Lesson 2 Download. And what we're going to do is we're going to see how to create your own classifier with your own images. So it's going to be a lot like last week's pet detector, but it'll detect whatever you like. So it'll be like those some of those examples we just saw. How would you create your own Panama bus detector from scratch? So this is inspired, the approach is inspired by Adrian Rosebrock, who has a terrific website called PyImageSearch, and he has this nice explanation of how to create a data set using Google Images. So that was definitely an inspiration for some of the techniques we use here. So thank you to Adrian. And you should definitely check out his site. It's full of lots of good resources. So, so here we are. So we are going to try to create a teddy bear detector. Thanks. We're going to try and make a teddy bear detector, and we're going to try and separate teddy bears from black bears from grizzly bears. This is very important. I have a 3-year-old daughter, and she needs to know what she's dealing with. In our house, you would be surprised at the number of monsters, lions, and other terrifying threats that are around, particularly around Halloween. And so we always need to be on the lookout to make sure that the thing we're about to cuddle is in fact a genuine teddy bear. Okay, so let's deal with that situation as best as we can. So our starting point is to find some pictures of teddy bears so we can learn what they look like. So I go to images.google.com and I type in teddy bear, and I just scroll through until I kind of find a goodly bunch of them. And it's like, okay, that looks like plenty of teddy bears to me. So then I'll go back to here. So you can see it says search and scroll. Go to Google Images and search. And the next thing we need to do is to get a list of all of the URLs there. And so to do that, you back in your Google Images, you hit Control-Shift-J or Command-Option-J, and you paste this into the window that appears. So I've got Windows, so I go Control Shift J, paste in that code. So this is a JavaScript console. For those of you who haven't done any JavaScript before, I hit Enter, and it downloads my file for me. So I would call this teddies.txt and press Save. Okay, so I now have a file of teddies, or URLs of teddies. So then I would repeat that process for black bears and for brown bears, since that's the classifier I would want, and I'd put each one in a file with an appropriate name. So that's step one. So step two is we now need to download those URLs to our server. Because remember, when we're using Jupyter Notebook, it's not running on our computer, it's running on SageMaker or Cressel or Google Cloud or whatever. So to do that, we start running some Jupyter cells. So let's grab the FastAI library, and let's start with black bears. I've already got my black bears URL. So I'll click on this cell for black bears, and I'll run it. See here how I've got 3 different cells with doing the same thing but different information. This is one way I like to work with Jupyter Notebook. It's something that a lot of kind of people with a more strict scientific background are horrified by. This is not reproducible research. I actually click here and I run this cell to create a folder called black and a file called URLs black for my black bears. I skip the next 2 cells and then I run this cell to create that folder. Okay, and then I go down to the next section and I run the next cell, which is download images for black bears. Right, so that's just going to download my black bears to that folder. And then I'll go back and I'll click on teddies and I'll run that cell and then scroll back down and I'll run this cell. And so that way I'm just going backwards and forwards to download each of the classes that I want. Very manual, but for me, I'm very iterative, I'm very experimental. That works well for me. If you're better at kind of planning ahead than I am, you can, write a proper loop or whatever and do it that way. But when you see my notebooks and see things where there's these kind of like configuration cells doing the same thing in different places, this is a strong sign that I didn't run this in order, right? I clicked one place, went to another, ran that, went back, went back, went back. And for me, I'm an experimentalist. I really like to experiment in my notebook. I treat it like a lab journal. I try things out and I see what happens, and so this is how my notebooks end up looking. It's a really controversial topic. Like for a lot of people, they feel this is like wrong, that you should only ever run things top to bottom. Everything you should do should be reproducible. For me, I don't think that's the best way of using human creativity. I think human creativity is best inspired by trying things out, seeing what happens, and fiddling around. So you can see how you go, see what works for you. So that will download the images to your server. It's going to use multiple processors to do so, and one problem there is if there's something goes wrong, it's a bit hard to see what went wrong. So you can see in the next section there's a commented out section that says max workers equals 0. That'll do it without spinning up a bunch of processors and will tell you the errors better. So if things aren't downloading, try using the second version. Okay, so it takes, so I grabbed a small number of each, and then the next thing that I found I needed to do was to remove the images that aren't actually images at all. And this happens all the time. There's always a few images in every batch that are corrupted for whatever reason. Google image tried to, told us that this URL had an image, but actually it doesn't anymore. So we've got this thing in the library called verify images, which will check all of the images in a path, and will tell you if there's a problem. If you say delete equals true, it will actually delete it for you. Okay, so that's a really nice, easy way to end up with a clean data set. So at this point, I now have a bears folder containing a grizzly folder and a teddies folder and a black folder. In other words, I have the basic structure we need to create an image data bunch to start doing some deep learning. So let's go ahead and do that. Now, very often when you download a data set from like Kaggle or from some academic data set, there will often be a folder called train and a folder called valid and a folder called test, right, containing the different data sets. In this case, we don't have a separate validation set because we just grab these images from Google search, right? But you still need a validation set, otherwise you don't know how well your model is going. And we'll talk more about this in a moment. So whenever you create a data bunch, if you don't have a separate training and validation set, then you can just say, okay, well the training set is in the current folder, because by default it looks in a folder called train, and I want you to set aside 20% of the data, please. So this is going to create a validation set for you automatically and randomly. You'll see that whenever I create a validation set randomly, I always set my random seed to something fixed beforehand. This means that every time I run this code, I'll get the same validation set. So in general, I'm not a fan of making my machine learning experiments reproducible, i.e. ensuring I get exactly the same result every time. The randomness is, to me, really important. A really important part of finding out, is your solution stable? You know, is it going to work like each time you run it? But what is important is that you always have the same validation set, right? Otherwise, when you're trying to decide, has this hyperparameter change improved my model, but you've got a different set of data you're testing it on, then you don't know, maybe that set of data just happens to be a bit easier, right? So that's why I always set the random seed here. So we've now got, let's run that cell. So we've now got a data bunch. And so you can look inside at the data.classes and you'll see these are the folders that we created. So it knows that the classes, or so by classes we mean all the possible labels, black bear, grizzly bear, or teddy bear. We can run show batch and we can take a little look. And it tells us straight away that some of these are going to be a little bit tricky. So this is not a photo, for instance. Some of them kind of cropped funny. Some of them might be tricky, like if you ended up with a black bear standing on top of a grizzly bear, that might be tough. Anyway, so you can kind of double check here, data.classes, there they are. Remember, C is the attribute which the classifiers tells us how many possible labels there are. We'll learn about some other more specific meanings of C later. We can see how many things are in our training set. We can see how many things are in our validation set. So we've got 473 training set, 141 validation set. So at that point we can go ahead. You'll see all these commands are identical to the PET classifier from last week. We can create our CNN, our convolutional neural network, using that data. I tend to default to using a ResNet 34. And let's print out the error rate each time and run fit one cycle 4 times and see how we go. And we have a 2% error rate. So that's pretty good. I personally aren't, I mean, sometimes it's easy for me to recognize a black bear from a grizzly bear, but sometimes it's a bit tricky. This one seems to be doing pretty well. Okay, so after I kind of make some progress with my model and things are looking good, I always like to save where I'm up to save me the 54 seconds of going back and doing it again. And as per usual, we unfreeze the rest of our model. We're going to be learning more about what that means during the course. And then we run the learning rate finder and plot it. It tells you exactly what to type. And we take a look. Now, we're going to be learning about learning rates today, actually. But for now, here's what you need to know. On the learning rate finder, what you're looking for is the strongest downward slope that's kind of sticking around for quite a while, right? So this one here looks more like a bump, but this looks like an actual downward slope to me. So it's kind of like, it's something you're going to have to practice with and get a feel for, like which bit works. So like if you're not sure, is it this bit or this bit, try both learning rates and see which one works better. Okay, but I've been doing this for a while and I'm pretty sure this looks like where it's really learning properly. So I would pick something, okay, here it's not so steep, so I would probably pick something back here for my learning rate. So you can see I picked 3e neg 5, So, you know, somewhere around here. That sounds pretty good. So that's for my bottom learning rate. For my top learning rate, I normally pick, you know, 1e neg 4 or 3e neg 4. It's kind of like I don't really think about it too much. That's a rule of thumb. It always works pretty well. One of the things you'll realize is that most of these parameters don't actually matter that much in detail. If you just copy the numbers that I use each time, the vast majority of the time it'll just work fine. And we'll see places where it doesn't today. Okay, so we've got a 1.4% error rate after doing another couple of epochs. So that's looking great. So we've downloaded some images from Google Image Search, created a classifier. We've got a 1.4% error rate. Let's save it. And then as per usual, we can use the classification interpretation class to have a look at what's going on. And in this case, we made one mistake. There was one black bear classified as a grizzly bear. So that's a really good step. We've come a long way. But possibly you could do even better if your data set was less noisy. Like maybe Google Image Search didn't give you exactly the right images all the time. So how do we fix that? And so we want to clean it up. And so combining a human expert with a computer learner is a really good idea. Almost not nobody, but very, very few people publish on this. Very, very few people teach this. But to me, it's like the most useful skill, particularly for you. You know, most of the people watching this are domain experts, not computer science experts. And so this is where you can use your knowledge of, you know, point mutations in genomics or Panamanian buses or whatever. So let's see how that would work. What I'm going to do is, do you remember the plot top losses from last time where we saw the images which it was like either the most wrong about or the least confident about? We're going to look at those and decide which of those are noisy. Like if you think about it, it's very unlikely that if there is some mislabeled data, that it's going to be predicted correctly and with high confidence. That's really unlikely to happen. So we're going to focus on the ones which the model is saying either it's not confident of or it was confident of and it was wrong about. They are the things which might be mislabeled. Big shout out to the San Francisco FastAI study group who created this new widget this week called the file deleter. That's Zach and Jason and Francisco built this thing where we basically can take the top losses from that interpretation object we just created, right? And then what we're going to do is we're going to say, okay, that returns top losses. There's not just plot top losses, but there's also just top losses. And top losses returns two things, the losses of the things that were the worst, and the indexes into the data set of the things that were the worst. And if you don't pass anything at all, it's going to actually return the entire data set, but sorted. So the first things will be the highest losses. As we'll learn during the course, or we'll keep seeing during the course, every data set in FastAI has an X and a Y. And the X contains the things that are used to, in this case, get the images. So this is the image file names, and the Ys will be the labels. So if we grab the indexes and pass them into the data set X, this is going to give us the file names of the data set ordered by which ones had the highest loss. So which ones it was either confident and wrong about or not confident about. And so we can pass that to this new widget that they've created called the file deleter widget. So just to clarify, this top loss paths contains all of the file names in our data set. When I say in our data set, this particular one is in our validation data set. So what this is going to do is it's going to clean up mislabeled images or images that shouldn't be there. And we're going to remove them from a validation set so that our metrics will be more correct. You then need to rerun these two steps, replacing valid DS with train DS, to clean up your training set to get the noise out of that as well. So it's a good practice to do both. We'll talk about test sets later as well. If you also have a test set, you would then repeat the same thing. So we run file deleter passing in that sorted list of paths. And so what pops up is basically the same thing as plot top losses. So in other words, these are the ones which is either wrong about or least confident about. And so not surprisingly, this one here does not appear to be a teddy bear or a black bear or a brown bear, right? So this shouldn't be in our data set. So what I do is I whack on the delete button, okay? And all the rest do look indeed like bears, and then so I can click confirm, and it'll bring up another 5. What's that? That's not a bear, is it? Does anybody know what that is? I'm going to say that's not a bear. Delete, confirm. Oh, not there. Well, that's a teddy bear. I'll leave that. That's not really. I'll get rid of that one. Confirm. Okay, so what I tend to do when I do this is I'll keep going confirm until I get to a couple of screenfuls of things that all look okay. And that suggests to me that I've kind of got past the worst bits of the data. Okay, and that's it. And so now you can go back, once you do it for the training set as well, and retrain your model. So I'll just note here that what our San Francisco study group did here was that they actually built a little app inside Jupyter Notebook, which you might not have realized is possible. But not only is it possible, it's actually surprisingly straightforward. And just like everything else, you can hit double question mark to find out their secrets. So here is the source code, okay? And really, if you've done any GUI programming before, it'll look incredibly normal. You know, there's basically callbacks for what happens when you click on a button, where you just do standard Python things. And to actually render it, you just use widgets, and you can lay it out using standard boxes and whatever. So this idea of creating applications inside notebooks is like, it's really underused. But it's super neat because it lets you create tools for your fellow practitioners, for your fellow experimenters, right? And you could definitely envisage taking this a lot further. In fact, by the time you're watching this on the MOOC, you'll probably find that there's a whole lot more buttons here because we've already got a long list of to-dos that we're going to add to this particular thing. So that's it. So I think like I'd love for you to have a think about, now that you know it's possible to write applications in your notebook, what are you going to write? And if you Google for IPy widgets, you can learn about the little GUI framework to find out what kind of widgets you can create and what they look like and how they work, and so forth. And you'll find it's actually a pretty, complete GUI programming environment that you can play with, and this will all work nicely with your models and so forth. It's not a great way to productionize an application because it is sitting inside a notebook. This is really for things which are going to help other practitioners, other experimentalists, and so forth. For productionizing things, you need to actually build a production web app, which we'll look at next. Okay, so after you have cleaned up your noisy images, you can then retrain your model, and hopefully you'll find it's a little bit more accurate. One thing you might be interested to discover when you do this is it actually doesn't matter most of the time very much. On the whole, these models are pretty good at dealing with moderate amounts of noisy data. The problem would occur is if your data was not randomly noisy, but biased noisy. So I guess the main thing I'm saying is if you go through this process of cleaning up your data and then you rerun your model and find it's like 0.001% better, that's normal. Okay, it's fine, but it's still a good idea just to make sure that you don't have too much noise in your data in case it is biased. So at this point, we're ready to put our model in production. And this is where I hear a lot of people ask me about, which mega Google, Facebook, highly distributed serving system they should use, and how do they use 1,000 GPUs at the same time, and whatever else. For the vast majority of things that you all do, you will want to actually run in production on a CPU, not a GPU. Why is that? Because a GPU is good at doing lots of things at the same time. But unless you have a very busy website, it's pretty unlikely that you're going to have 64 images to classify at the same time to put into a batch into a GPU. And if you did, you've got to deal with all that queuing and running it all together. All of your users have to wait until that batch has got filled up and run. It's a whole lot of hassle, right? And then if you want to scale that, there's another whole lot of hassle. It's much easier if you just grab one thing, throw it at a CPU to get it done, and it comes back again. So yes, it's going to take, maybe 10 or 20 times longer, right? So maybe it'll take 0.2 seconds rather than 0.01 seconds. That's about the kind of times we're talking about. But it's so easy to scale, right? You can chuck it on any standard serving infrastructure. It's going to be cheap as hell. You can horizontally scale it really easily, right? So most people I know who are running apps that aren't kind of at Google scale based on deep learning are using CPUs. And the term we use is inference, right? So when you're not training a model, but you've got a trained model and you're getting it to predict things, we call that inference. So that's why we say here you probably want to use CPU for inference. So at inference time, you've got your pre-trained model, you've saved those weights, and how are you going to use them to create something like Simon Willison's Cougar detector? Well, first thing you're going to need to know is what were the classes that you trained with, right? You need to know not just what are they, but what were the order, okay? So you will actually need to serialize that or just type them in or in some way make sure you've got exactly the same classes that you trained with. If you don't have a GPU on your server, it will use the CPU automatically. If you want to test, if you have a GPU machine and you want to test using a CPU, you can just uncomment this line, and that tells FastAI that you want to use CPU by passing it back to PyTorch. So here's an example. We don't have a cougar detector. We have a teddy bear detector, and my daughter Claire is about to decide whether to cuddle this friend. Okay, so what she does is she takes Daddy's deep learning model and she gets a picture of this, and here is the picture that she's uploaded to the web app. Okay, and here is a picture of the potentially cuddlesome object. And so we're going to store that in a variable called image. So open image is how you open an image in FastAI, funnily enough. Here is that list of classes that we saved earlier. And so as per usual, we created a data bunch. But this time we're not going to create a data bunch from a folder full of images. We're going to create a special kind of data bunch, which is one that's going to grab one single image at a time. So we're not actually passing it any data. The only reason we pass it a path is so that it knows where to load our model from, right? That's just the path, that's the folder that the model's going to be in. But what we do need to do is that we need to pass it the same information that we trained with. So the same transforms, the same size, the same normalization. This is all stuff we'll learn more about, but just make sure it's the same stuff that you used before. And so now you've got a data bunch that actually doesn't have any data in it at all. It's just something that knows how to transform a new image in the same way that you trained with, so that you can now do inference. So you can now create a CNN with this kind of fake data bunch, and again, you would use exactly the same model that you trained with. You can now load in those saved weights, okay? And so this is the stuff that you would do just once when your web app's starting up, okay? And it takes, 0.1 of a second to run this code. And then you just go learn.predict image. And it's lucky we did that because it is not a teddy bear. This is actually a black bear. So thankfully, due to this excellent deep learning model, my daughter will avoid having a very embarrassing black bear cuddle incident. So what does this look like in production? Well, I took Simon Willison's code and shamelessly stole it, made it probably a little bit worse, but basically it's going to look something like this. So Simon used a really cool web app toolkit called Starlet. If you've ever used Flask, this will look extremely similar, but it's kind of a more modern approach. And by modern, what I really mean is that you can use a wait. It basically means that you can wait for something that takes a while, such as grabbing some data, without using up a process. So for things like I want to get a prediction, or I want to load up some data or whatever, it's really great to be able to use this modern Python 3 asynchronous stuff. So Starlet would come highly recommended for creating your web app. And so, yeah, you just create a route as per usual in a web app. And in that, you say this is async to ensure that it doesn't steal a process while it's waiting for things. You open your image, you call .predict, and you return that response. And then you can use a whatever JavaScript client or whatever to show it. And that's it. That's basically the main contents of your web app. So give it a go, right? This week, even if you've never created a web application before, there's a lot of nice little tutorials online and kind of starter code. If in doubt, why don't you try Starlet? There's a free hosting that you can use. There's one called Python Anywhere, for example. The one that Simon's used, we'll mention that on the forum. It's something you can basically package it up as a Docker thing and shoot it off, and it'll serve it up for you. So it doesn't even need to cost you any money. And so all these classifiers that you're creating, you can turn them into web applications. So I'll be really interested to see what you're able to make of that. That'll be really fun. Okay, so let's take a break. We'll come back at 7:35. See you then. Okay, so let's move on. So I mentioned that most of the time, the kind of rules of thumb I've shown you will probably work. And if you look at the Share Your Work thread, you'll find most of the time people are posting things saying, I downloaded these images, I tried this thing, it worked much better than I expected, well, that's cool. And then like 1 out of 20 says like, I had a problem. So let's have a talk about what happens when you have a problem. And this is where we're starting to start getting into a little bit of theory, because in order to understand why we have these problems and how we fix them, it really helps to know a little bit about what's going on. So first of all, let's look at examples of some problems. The problems basically will be either your learning rate is too high or low, or your number of epochs is too high or low. So we're going to learn about what those mean and why they matter. But first of all, because we're experimentalists, let's try them. All right? So let's go with our teddy bear detector, and let's make our learning rate really high. The default learning rate is 0.003. It works most of the time. So what if we try a learning rate of 0.5? That's huge. What happens? Our validation loss gets pretty damn high. Right? Remember, this is normally something that's underneath 1. Right? So if you see your validation loss do that, right, before we even learn what validation loss is, just know this. If it does that, your learning rate's too high. That's all you need to know. Okay? Make it lower. Doesn't matter how many epochs you do. And if this happens, there's no way to undo this. You have to go back and create your neural net again and fit from scratch with a lower learning rate. So that's learning rate too high. Learning rate too low. What if we use a learning rate not of 0.003, but 1e neg 5, so 0.00001, right? So this is just, I've just copied and pasted what happened when we trained before with our default error, right? With our default learning rate. And within 1 epoch, we were down to a 2 or 3% error rate. With this really low learning rate, our error rate does get better, but very, very slowly, right? And you can plot it. If you go learn.recorder is an object which is going to keep track of lots of things happening while you train. You can call plot losses to plot out the validation and training loss, and you can just see them just like gradually going down so slow. Right? So if you see that happening, then you have a learning rate which is too small. Okay, so bump it up by 10 or bump it up by 100 and try again. The other thing you'll see if your learning rate is too small is that your training loss will be higher than your validation loss. You never want a model where your training loss is higher than your validation loss. That always means you haven't fitted enough, which means either your learning rate is too low or your number of epochs is too low. So if you have a model like that, train it some more or train it with a higher learning rate. Okay? Too few epochs. So what if we train for just one epoch? Our error rate certainly is better than random. It's 5%. But look at this. The difference between training loss and validation loss. The training loss is much higher than the validation loss. So too few epochs and too low a learning rate look very similar, right? And so you can just try running more epochs. And if it's taking forever, you can try a higher learning rate. Or if you try a higher learning rate and the loss goes off to 100,000 million, then put it back to where it was and try a few more epochs. That's the balance, right? That's basically all you care about 99% of the time. And this is only the 1 in 20 times that the defaults don't work for you. Okay, too many epochs, we're going to be talking more about this, create something called overfitting. If you train for too long, as we're going to learn about, it will learn to recognize your particular teddy bears, but not teddy bears in general. Here's the thing. Despite what you may have heard, it's very hard to overfit with deep learning. So we were trying today to show you an example of overfitting, and I turned off everything. And we're going to learn all about these terms soon. I turned off all the data augmentation. I turned off dropout. I turned off weight decay. I tried to make it overfit as much as I can. I trained it on a small-ish learning rate. I trained it for a really long time. And like, maybe I started to get it to overfit, maybe. So the only thing that tells you that you're overfitting is that the error rate improves for a while and then starts getting worse again. You will see a lot of people, even people that claim to understand machine learning, tell you that if your training loss is lower than your validation loss, then you are overfitting. As you will learn today in more detail and during the rest of the course, that is absolutely not true. Any model that is trained correctly will always have train loss lower than validation loss. That is not a sign of overfitting. That is not a sign you've done something wrong. That is a sign you have done something right. Okay. The sign that you are overfitting is that your error starts getting worse. Because that's what you care about, right? You want your model to have a low error. So as long as you're training and your model error is improving, you are not overfitting. How could you be? Okay? So there's basically the they're the main 4 things that can go wrong. There are some other details that we will learn about during the rest of this course. But honestly, if you stopped listening now, please don't, that would be embarrassing. And you just like, okay, I'm going to go and download images. I'm going to create CNNs with ResNet 34 or ResNet 50. I'm going to make sure that my learning rate and number of epochs is okay. And then I'm going to chuck them up in a Starlet web API. Most of the time you're done, okay? At least for computer vision. Hopefully you'll stick around because you want to learn about NLP and collaborative filtering and tabular data and segmentation and stuff like that as well. Let's now understand what's actually going on. What does it mean, loss mean? What does an epoch mean? What does learning rate mean? Because for you to really understand these ideas, you need to know what's going on. And so we're going to go all the way to the other side. Rather than creating a state-of-the-art cougar detector, we're going to go back and create the simplest possible linear model. Okay, so we're going to actually start seeing, a little bit of math. Okay, but don't be turned off. It's okay, right? We're going to do a little bit of math, but it's going to be totally fine even if math's not your thing. Because the first thing we're going to realize is that when we see a picture, like this number 8, it's actually just a bunch of numbers. It's a matrix of numbers. For this grayscale one, it's a matrix of numbers. If it was a color image, it would be have a third dimension. So when you add an extra dimension, we call it a tensor. Rather than a matrix, it would be a 3D tensor of numbers, red, green, and blue. So when we created that teddy bear detector, what we actually did was we created a mathematical function that took the numbers from the images of the teddy bears, and the mathematical function converted those numbers into, in our case, 3 numbers. A number for the probability that it's a teddy, a probability that it's a grizzly, and a probability that it's a black bear. In this case, there's some hypothetical function that's taking the pixels representing a handwritten digit and returning 10 numbers, the probability for each possible outcome, the numbers from 0 to 9. And so what you'll often see in our code and other deep learning code is that you'll find this a bunch of probabilities, and then you'll find something called max or argmax attached to it, a function called. And so what that function is doing is it's saying, find the highest number, so the highest probability, and tell me what the index is. So np.argmax or torch.argmax of this array would return this number here. Okay, we return index 8. Does that make sense? In fact, let's try it. So we know that the function to predict something is called learn.predict. Okay, so we can chuck 2 question marks before it or after it to get the source code. And here it is, right? Pred equals res result dot argmax. And then what is the class? Well, you just pass that into the classes array. So like you should find that the source code in the FastAI library can both kind of strengthen your understanding of the concepts and make sure that you know what's going on and really help you here. You got a question? Come on over.
All right, so can we have a definition of the error rate being discussed and how it is calculated? I assume it's cross-validation error.
Sure. So one way to answer the question of how is error rate calculated would be to type error rate question mark and look at the source code, and it is 1 minus accuracy. Fair enough. And so then a question might be, what is accuracy? Accuracy question mark. It is argmax. So we now know that means find out which particular thing it is, and then look at how often that equals the target. So in other words, the actual value, and take the mean. So that's basically what it is. And so then the question is, okay, well, what is that being applied to? Always in FastAI, metrics, so these things that we pass in, we call them metrics, are always going to be applied to the validation set. Okay? So anytime you put a metric here, it'll be applied to the validation set because that's your best practice, right? That's what you always want to do, is make sure that you're checking your performance on data that your model hasn't seen. And we'll be learning more about the validation set shortly. Remember, you can also type doc. If the source code is not what you want, which it might well not be, you actually want the documentation. That will both give you a summary of the types in and out of the function and a link to the full documentation where you can find out all about how metrics work and what other metrics there are and so forth. And generally speaking, you'll also find links to more information where, for example, you will find complete runs through and sample code and so forth showing you how to use all these things. So don't forget that the doc function is your friend. Okay, and also in the documentation, both in the doc function and in the documentation, you will see a source link. This is like question mark, but what the source link does is it takes you into the exact line of code in GitHub, so you can see exactly how that's implemented and what else is around it. So lots of good stuff there.
Why were you using 3s for your learning rates earlier with 3E neg 5 and 3E neg 4?
We found that 3E neg 3 is just a really good default learning rate. It works most of the time for your initial fine-tuning before you unfreeze. And then I tend to kind of just multiply from there. So I generally find then that the next stage I will pick 10 times lower than that for the second part of the slice, and whatever the LR finder found for the first part of the slice. The second part of the slice doesn't come from the LR finder. It's just a rule of thumb, which is like 10 times less than your first part, which defaults to 3E neg 3. And then the first part of the slice is what comes out of the LR finder. And we'll be learning a lot more about these learning rate details both today and in the coming lessons. But yeah, for now, all you need to remember is that in your your basic approach looked like this. It was learn.fit one cycle, some number of epochs. I often pick 4, and some learning rate, which defaults to 3E neg 3. I'll just type it out fully so you can see. And then we do that for a bit, and then we unfreeze it, right? And then we learn some more. And so this is the bit where I just take whatever I did last time and divide it by 10. And then I also write like that, and then I have to put one more number in here, and that's the number that I get from the learning rate finder, the bit where it's got the strongest slope. So that's kind of the don't have to think about it, don't really have to know what's going on, rule of thumb that works most of the time. But let's now dig in and actually understand it more completely. So we're going to create this mathematical function that takes the numbers that represent the pixels and spits out probabilities for each possible class. And by the way, a lot of the stuff that we're using here, we are stealing from other people who are awesome, and so we are putting their details here. So like, please check out their work, because they've got great work that we are highlighting in our course. I really like this idea of this little animated GIF of the numbers. So thank you to Adam Geitke for creating that. And I guess that was probably on Quora by the looks of this Medium. Oh yes, it was too, that terrific Medium post, I remember. In fact, a whole series of Medium posts. So, so let's look and see how we create one of these functions. And let's start with the simplest function I know, y equals ax plus b. Okay, that's a line, right? That's a line, and the gradient of the line is here, and the intercept of the line is here. Okay, so hopefully, when we said that you need to know high school math to do this course, these are the things we're assuming that you remember. If we do kind of mention some math thing, which I'm assuming you remember, and you don't remember it, don't freak out, right? Happens to all of us. Khan Academy is actually terrific. It's not just for school kids. Go to Khan Academy, find the concept that you need a refresher on, and he explains things really well. So strongly recommend checking that out. Remember, I'm just a philosophy student, right? So I, all the time, I'm trying to either remind myself about something or I never learnt something, and so we have the whole internet to teach us these things. So I'm going to rewrite this slightly. Y equals a1x plus A2. So let's just replace B with A2. I'm just going to give it a different name. Okay. So there's another way of saying the same thing. And then another way of saying that would be if I could multiply A2 by the number 1. Okay, this still is the same thing. Okay. And so now at this point, I'm actually going to say, let's not put the number 1 there, but let's put an x1 here and an x2 here, and I'll say x2 equals 1. Okay, so far, this is not, this is pretty early high school math. This is multiplying by 1, which I think we can handle. Okay, so these two are equivalent with a bit of renaming. Now, in machine learning, we don't just have one equation, we've got lots, right? So if we've got some data that represents the temperature versus the number of ice creams sold, then we kind of have lots of dots. And so each one of those dots, we might hypothesize, is based on this formula, y equals a1 x1 plus a2 x2, right? And so basically there's lots of, so this is our y, this is our x. There's lots of values of y, so we can stick a little I here. And there's lots of values of x, so we can stick a little x here, okay? So the way we kind of do that is a lot like NumPy indexing, right? But rather than things in square brackets, or PyTorch indexing, rather than things in square brackets, we kind of put them down here in our kind of in a subscript to our equation, okay? So this is now saying there's actually lots of these different yi's based on lots of different xi1 and xi2, okay? But notice there's still only one of each of these. Right? So these things here are called the coefficients or the parameters. So this is our linear equation, and this is still, we're going to say that every xi2 is equal to 1. Okay. Why did I do it that way? Because I want to do linear algebra. Why do I want to do in linear algebra? Well, one reason is because Rachel teaches the world's best linear algebra course. So if you're interested, check out Computational Linear Algebra for Coders. So it's a good opportunity for me to throw in a pitch for this free course, for which we make no money, but never mind. But more to the point right now, it's going to make life much easier, right? Because I hate writing loops. I hate writing code, right? I just want the computer to do everything for me. And anytime you see like these little I subscripts, that sounds like you're going to have to do loops and all kinds of stuff. But what you might remember from school is that when you've got like two things being multiplied together, and then they get added up, that's called a dot product. And then if you do that for lots and lots of different numbers I, then that's called a matrix product. So in fact, this whole thing can be written like this. Rather than lots of different yi's, we can say there's one vector called y, which is equal to one matrix called x times one vector called a. Now at this point, I know a lot of you don't remember that. So that's fine. We have a picture to show you. I don't know who created this. Oh, no, I do. Somebody called Andre Stouts created this fantastic thing called matrix multiplication.xyz. And here we have a matrix by a vector. And we're going to do a matrix vector product. Go. That times that times that plus 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 plus. That times that times that plus 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 plus. That times that times that plus 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 plus. Finished. That is what matrix vector multiplication does. In other words, it's just that, except his version is much less messy. Okay, so let's, this is actually an excellent spot to have a little break and find out what questions we have coming through our students. What are they asking, Rachel?
Okay. When generating new image data sets, how do you know how many images are enough? What are ways to measure enough?
Yeah, that's a great question. So another possible problem you have is you don't have enough data. How do you know if you don't have enough data? Because you found a good learning rate, because if you make it higher, then it goes off into massive losses. If you make it lower, it goes really slowly. So you've got a good learning rate. And then you train for such a long time that your error starts getting worse. Okay, so you know that you've trained for long enough. And you're still not happy with the accuracy. It's not good enough for the, teddy bear cuddling level of safety you want. So if that happens, there's a number of things you can do, and we'll learn about some of them we'll learn pretty much all of them during this course. But one of the easiest ones is get more data. Okay, if you get more data, then you can train for longer, get a higher accuracy, lower error rate without overfitting. Unfortunately, there's no shortcut. I wish there was. I wish there was some way to know ahead of time how much data you need. But I will say this, most of the time you need less data than you think. So organizations very commonly spend too much time gathering data, getting more data than it turned out they actually needed. So get a small amount first and see how you go.
What do you do if you have unbalanced classes, such as 200 grizzlies and 50 teddies?
Nothing. Try it. It works. A lot of people ask this question about how do I deal with unbalanced data. I've done lots of analysis with unbalanced data over the last couple of years, and I just can't make it not work. It always works. So there's actually a paper that said, like, if you want to get it slightly better, then the best thing to do is to take that uncommon class and just make a few copies of it. That's called oversampling. But I haven't found a situation in practice where I needed to do that. I've found it always just works fine for me.
Once you unfreeze and retrain with one cycle again, if your training loss is still lower than your validation loss, likely underfitting, do you retrain it unfrozen again, which will technically be more than one cycle, or do you redo everything with a longer epoch per the cycle?
Hey, you guys asked me that last week. My answer's still the same. I don't know. Either's fine. If you do another cycle, then it'll kind of maybe generalize a little bit better. If you start again, do twice as long, it's kind of annoying. Depends how patient you are. It won't make much difference. For me personally, I normally just train a few more cycles. Yeah, it doesn't make much difference most of the time.
So showing the code sample where you were creating a CNN with ResNet 34 for the Grizzly Teddy classifier. It says this requires ResNet 34, which I find surprising. I had assumed that the model created by .save, which is about 85 megabytes on disk, would be able to run without also needing a copy of ResNet 34.
Yeah, and I understand. We're going to be learning all about this shortly. There's no copy of ResNet 34. ResNet 34 is actually what we call an architecture. We're going to be learning a lot about this. It's a functional form. Just like this is a linear functional form. It doesn't take up any room. It doesn't contain anything. It's just a function. ResNet 34 is just a function. It doesn't contain anything. It doesn't store anything. I think the confusion here is that we often use a pre-trained neural net that's been learnt on ImageNet. In this case, we don't need to use a pre-trained neural net. And actually, to entirely avoid that even getting created, you can actually pass pre-trained equals false, and that'll ensure that nothing even gets loaded, which will save you another 0.2 seconds, I guess. So yeah, but we'll be learning a lot more about this. So don't worry if this is a bit unclear. But the basic idea is this thing here is basically the equivalent of saying, is it a line, or is it a quadratic, or is it a reciprocal? This is just a function. This is the ResNet 34 function. It's a mathematical function. It has doesn't take any storage. It doesn't have any numbers. It doesn't have to be loaded. as opposed to a pre-trained model. And so that's why when we did it at inference time, the thing that took space is this bit, which is where we load our parameters, which is basically saying, as we're about to find out, what are the values of A and B. We have to store those numbers. But for ResNet 34, you don't just store two numbers, you store a few million, or a few tens of millions of numbers. So why did we do all this? Well, it's because I wanted to be able to write it out like this. And the nice thing of being able to write it out like this is that we can now do that in PyTorch with no loops, single line of code, and it's also going to run faster. PyTorch really doesn't like loops, right? It really wants you to send it a whole equation to do all at once, which means you really want to try and specify things in these kind of linear algebra ways. So let's go and take a look, because what we're going to try and do then is we're going to try and take this, we're going to call it an architecture. Right? It's just like the world's tiniest neural network. It's got two parameters, you know, A1 and A2. We're going to try and fit this architecture to some data. So let's jump into a notebook and generate some dots, right, and see if we can get it to fit a line somehow. And the somehow is going to be using something called SGD. What is SGD? Well, there's two types of SGD. The first one is where I said in lesson 1, hey, you should all try building these models and try and come up with something cool. And you guys all experimented and found really good stuff. So that's where the S would be student. That would be student gradient descent. So that's version 1 of SGD. Version 2 of SGD, which is what we're going to talk about today, is where we're going to have a computer try lots of things and try and come up with a really good function, and that will be called stochastic gradient descent. The other one that you hear a lot in on Twitter is stochastic grad student descent. So that's the other one that you hear. So we're going to jump into lesson 2 SGD. And so we're going to kind of go bottom up rather than top down. We're going to create the simplest possible model we can, which is going to be a linear model. And the first thing that we need is we need some data. And so we're going to generate some data. The data we're going to generate looks like this. So this might represent temperature, and this might represent number of ice creams we sell, or something like that. But we're just going to create some synthetic data that we know is following a line. And so as we build this, we're actually going to learn a little bit about PyTorch as well. So basically the way we're going to generate this data is by creating some coefficients. A1 will be 3, and A2 will be 2. And we're going to create some, like we looked at before, basically a column of numbers for our x's and a whole bunch of 1s. And then we're going to do this, x at a. What is x at a? X at a in Python means a matrix product between x and a. It actually is even more general than that. It can be a vector-vector product, a matrix-vector product, a vector-matrix product, or a matrix-matrix product. And then actually in PyTorch specifically, it can mean even more general things where we get into higher rank tensors, which we will learn all about very soon. Right? But this is basically the key thing that's going to go on in all of our deep learning. The vast majority of the time, our computers are going to be basically doing this, multiplying numbers together and adding them up, which is a surprisingly useful thing to do. Okay, so we basically are going to generate some data by creating a line, and then we're going to add some random numbers to it. But let's go back and see how we created x and a. So I mentioned that, you know, we've basically got these two coefficients, 3 and 2. And you'll see that we've wrapped it in this function called tensor. You might have heard this word tensor before. Who's heard the word tensor before? About 2/3 of you. Okay. So it's one of these words that sounds scary. And apparently, if you're a physicist, it actually is scary. But in the world of deep learning, it's actually not scary at all. Tensor means array. Okay? It means array. Now, specifically, it's an array of a regular shape, right? So it's not an array where row 1 has 2 things and row 3 has 3 things and row 4 has 1 thing, what you call a jagged array. That's not a tensor. A tensor is any array which has a rectangular or cube or whatever, you know, a shape where every element, every row is the same length, and then every column is the same length. So 4 by 3 matrix would be a tensor. A vector of length 4 would be a tensor. A 3D array of length 3 by 4 by 6 would be a tensor. That's all a tensor is. Okay, and so we have these all the time. For example, an image is a 3-dimensional tensor. It's got number of rows by number of columns by number of channels, normally red, green, blue. So for example, kind of a VGA picture would be 640 by 480 by 3. Or actually, we do things backwards. So when people talk about images, they normally go width by height. But when we talk mathematically, we always go number of rows by number of columns. So it would actually be 480 by 640 by 3. And that will catch you out. We don't say dimensions, though, with tensors. We use one of two words. We either say rank or axes. Rank specifically means how many axes are there, how many dimensions are there. So an image is generally a rank 3 tensor. So what we've created here is a rank 1 tensor, or also known as a vector, right? But like in math, people come up with slightly different words, or actually no, they come up with very different words for slightly different concepts. Why is a 1-dimensional array a vector, and a 2-dimensional array is a matrix, and then a 3-dimensional array, does that even have a name? Not really. Doesn't have a name. Like, it doesn't make any sense. Whereas with computers, we try to have some simple, consistent naming conventions. They're all called tensors. Rank 1 tensor, rank 2 tensor, rank 3 tensor. You can certainly have a rank 4 tensor. If you've got 64 images, then that would be a rank 4 tensor of 64 by 480 by 640 by 3, for example. So tensors are very simple. They just mean arrays. And so in PyTorch, you say tensor, and you pass in some numbers, and you get back, in this case, just a list, get back a vector. Okay? So this then represents our coefficients, the slope and the intercept of our line. And so, because remember, we're not actually going to have a special case of ax plus b. Instead, we're going to say there's always this second x value, which is always 1. You can see it here, always 1, which allows us just to do a simple matrix vector product. Okay, so that's A. And then we wanted to generate this X array of data, which is going to have, we're just going to put random numbers in the first column and a whole bunch of 1s in the second column. So to do that, we basically say to PyTorch, create a rank 2 tensor. Actually, no, sorry, let's start that again. We say to PyTorch that we want to create a tensor of n by 2. So since we passed in a total of 2 things, we get a rank 2 tensor. The number of rows will be n, and the number of columns will be 2. And in there, every single thing in it will be a 1. That's what torch.ones means. And then, this is really important, you can index into that, just like you can index into a list in Python, but you can put a colon anywhere. And a colon means every single value on that axis, or every single value on that dimension. So this here means every single row. And then this here means column 0. So this is every row of column 0. I want you to grab a uniform random number. And here's another very important concept. In PyTorch, anytime you've got a function that ends in an underscore, it means don't return to me that uniform random number, but replace whatever this is being called on with the result of this function. So this takes column 0 and replaces it with a uniform random number between -1 and 1. So there's a lot to unpack there, right? But the good news is those 2 lines of code, plus this one, which we're coming to, cover 95% of what you need to know about PyTorch. How to create an array, how to change things in an array, and how to do matrix operations on an array. Okay, so there's a lot to unpack, but these small number of concepts are incredibly powerful. So I can now print out the first 5 rows. Okay, so :5 is standard Python slicing syntax to say the first 5 rows. So here are the first 5 rows, 2 columns looking like my random numbers and my ones. So now I can do a matrix product of that X by my A, add in some random numbers to add a bit of noise, and then I can do a scatter plot. And I'm not really interested in my scatter plot in this column of ones, right? They're just there to make my linear function more convenient. So I'm just going to plot my 0 index column against my Ys, and there it is. PLT is what we universally use to refer to the plotting library matplotlib. And that's what most people use for most of their plotting in Python. In scientific Python, we use matplotlib. It's certainly a library you'll want to get familiar with because being able to plot things is really important. There are lots of other plotting packages. Lots of them, the other packages are better at certain things than matplotlib, but like matplotlib can do everything reasonably well. Sometimes it's a little awkward, but you know, for me, I do pretty much everything in matplotlib because there's really nothing it can't do, even though some libraries can do other things a little bit better or a little bit prettier. But it's really powerful. So once you know matplotlib, you can do everything. So here I'm asking matplotlib to give me a scatter plot of my x's against my y's, and there it is. Okay, so this is my my dummy data representing, like, you know, temperature and ice cream sales. So now what we're going to do is we're going to pretend we were given this data and we don't know that the values of our coefficients are 3 and 2. So we're going to pretend that we never knew that. We have to figure them out. Okay, so how would we figure them out? How would we draw a line to fit to this data? And why would that even be interesting? Well, we're going to look at more about why it's interesting in just a moment, but the basic idea is this. If we can find, this is going to be kind of perhaps really surprising, but if we can find a way to find those 2 parameters to fit that line to those, how many points were there? N was 100. If we can find a way to fit that line to those 100 points, we can also fit these arbitrary functions that convert from pixel values to probabilities. It'll turn out that this techniques that we're going to learn to find these 2 numbers works equally well for the 50 million numbers in ResNet 34. So we're actually going to use an almost identical approach. So that's this, and this is the bit that I found in previous classes people have the most trouble digesting. Like I often find, even after week 4 or week 5, people will come up to me and say, I don't get it. How do we actually train these models? And I'll say, it's SGD. It's that thing we saw in the notebook with the 2 numbers. It's like, yeah, but we're fitting a neural network. It's like, I know, and we can't print the 50 million numbers anymore, but it is literally identically doing the same thing. And the reason this is hard to digest is that the human brain has a lot of trouble conceptualizing of what an equation with 50 million numbers looks like and can do. So you just kind of, for now, will have to take my word for it. It can do things like recognize teddy bears. You know, these functions turn out to be very powerful. And we're going to learn a little bit more in just a moment about how to make them extra powerful. But for now, this thing we're going to learn to fit these 2 numbers is the same thing that we've just been using to fit 50 million numbers. Okay, so we want to find what PyTorch calls parameters, or in statistics you'll often hear called coefficients, these values of A1 and A2. We want to find these parameters such that the line that they create minimizes the error between that line and the points. So in other words, if we created, if the A1 and A2 we came up with resulted in this line, then we'd look and we'd see like how far away is that line from each point. And we'd say, oh, that's quite a long way. And so maybe there was some other A1 or A2 which resulted in this line. And then we'd say like, oh, how far away is each of those points? And then eventually we come up with this line, and it's like, oh, in this case, each of those is actually very close. Right? So you can see how in each case we can say how far away is the line at each spot away from its point, and then we can take the average of all those, and that's called the loss. Right? That is the value of our loss. Right? So you need some mathematical function that can basically say how far away is this line from those points. For this kind of problem, which is called a regression problem, a problem where your dependent variable is continuous, so rather than being grizzlies or teddies, it's like some number between -1 and 6. This is called a regression problem. And for regression, the most common loss function is called mean squared error, which pretty much everybody calls MSE. You may also see RMSE, which is root mean squared error. And so the mean squared error is the loss. It's the difference between some prediction that you've made, okay, which is like the value at the line, and the actual number of ice cream sales. And so in the mathematics of this, people normally refer to the actual, they normally call it Y, and the prediction, they normally call it Y hat, as in they write it like that. Okay. And so what I try to do, like when we're writing something like a mean squared error equation, there's no point writing ice cream here and temperature here, because we want it to apply to anything. So we tend to use these like mathematical placeholders. So the value of mean squared error is simply the difference between those two squared, right? And then we can take the mean. Because remember, that is actually a vector, or what we now call it, a rank 1 tensor. And that is actually a rank 1 tensor. So it's the value of the number of ice cream sales at each place, right? So when we subtract one vector from another vector, and we're going to be learning a lot more about this, but it does something called element-wise arithmetic. In other words, it subtracts each one from each other. And so we end up with a vector of differences. And then if we take the square of that, it squares everything in that vector. And so then we can take the mean of that to find the average square of the differences between the actuals and the predicted. So if you're more comfortable with mathematical notation, what we just wrote there was the sum of, which way around did we do it? Y hat minus Y squared over n. Right? So that equation is the same as that equation. So one of the things I'll note here is I don't think this is, more complicated or unwieldy than this, right? But the benefit of this is you can experiment with it. Like once you've defined it, you can use it. You can send things into it and get stuff out of it and see how it works, right? So for me, most of the time, I prefer to explain things with code rather than with math, right? Because I can actually, they're the same, right? They're doing, in this case at least, in all the cases we'll look at, They're exactly the same, they're just different notations for the same thing. But one of the notations is executable, it's something that you can experiment with, and one of them is abstract. So that's why I'm generally going to show code. So the good news is if you're a coder with not much of a math background, actually you do have a math background, because code is math, right? If you've got more of a math background and less of a code background, then actually a lot of the stuff that you learned from math is going to translate very directly into code. And now you can start to experiment really with your math. Okay, so this is a loss function. This is something that tells us how good our line is. So now we have to kind of come up with what is the line that fits through here. Because remember, we don't know. We're going to pretend we don't know. So what you actually have to do is you have to guess. You actually have to come up with a guess. What are the values of A1 and A2? So let's say we guessed that A1 and A2 are both 1. So this is our tensor. A is 1, 1. Right? So here is how we create that tensor. And I wanted to write it this way because you'll see this all the time. Like written out, it should be 1.0. Oh, sorry, it looks like we're starting with -1. -1. Written out fully, it would be -1.0, 1.0. Like that's written out fully. We can't write it without the point because that's now an int, not a floating point. So that's going to spit the dummy if you try to do calculations with that in neural nets. Right? I'm lazy. I'm far too lazy to type .0 every time. Python knows perfectly well that if you add a dot next to any of these numbers, then the whole thing is now floats. Right? So that's why you'll often see it written this way, particularly by lazy people like me. Okay, so A is a tensor. You can see its floating point. You see, like even PyTorch is lazy. They just put a dot. They don't bother with a 0. Right? But if you want to actually see exactly what it is, you can write dot type, and you can see it's a float tensor. Okay. And so now we can calculate our predictions with this like random guess, x at A, matrix product of x and A. And we can now calculate the mean squared error of our predictions and our actuals. And that's our loss. Okay, so for this regression, our loss is 8.9. And so we can now plot a scatter plot of x against y, and we can plot a scatter plot of x against y hat, our predictions, and there they are. Okay, so this is the 1, -1 line, sorry, -1, 1 line, and here's our actuals. So that's not great, which is not surprising, because it's just a guess. So SGD, or gradient descent more generally, and anybody who's done engineering or probably computer science at school will have done plenty of this, like Newton's method, whatever. It's all the stuff that you did at university. If you didn't, don't worry, we're going to learn it now. It's basically about taking this guess and trying to make it a little bit better. So how do we make it a little bit better? Well, there's only two numbers, right? And the two numbers are the intercept of that orange line and the gradient of that orange line. So what we're going to do with gradient descent is we're going to simply say, what if we changed those two numbers a little bit? What if we made the intercept a little bit higher or a little bit lower? What if we made the gradient a little bit more positive or a little bit more negative? So there's like 4 possibilities. And then we can just calculate the loss for each of those 4 possibilities and see what worked. Did lifting it up or down make it better? Did tilting it more positive or more negative make it better? And then all we do is we say, okay, well, whichever one of those made it better, that's what we're going to do. And that's it, right? But here's the cool thing, for those of you that remember calculus, you don't actually have to move it up and down and round about. You can actually calculate the derivative. The derivative is the thing that tells you, would moving it up or down make it better, or would rotating it this way or that way make it better? Okay. So the good news is, if you didn't do calculus or you don't remember calculus, I just told you everything you need to know about it, right? which is that it tells you how changing one thing changes the function. Right? That's what the derivative is. Kind of, not quite strictly speaking, but close enough, also called the gradient. Okay, so the gradient or the derivative tells you how changing A1 up or down would change our MSE, how changing A2 up or down would change our MSE, and it just does it more quickly. It does it more quickly than actually moving it up and down. Right? So in school, unfortunately, they force us to sit there and calculate these derivatives by hand. We have computers. Computers can do that for us. We are not going to calculate them by hand. Instead, we're going to call .grad. On our computer, that will calculate the gradient for us. So here's what we're going to do. We're going to create a loop. We're going to loop through 100 times, and we're going to call a function called update. That function is going to calculate y hat, our prediction. It is going to calculate loss, our mean squared error. From time to time, it will print that out so we can see how we're going. It will then calculate the gradient. And in PyTorch, calculating the gradient is done by using a method called backward. So you'll see something really interesting, which is mean squared error was just a simple standard mathematical function. PyTorch, for us, keeps track of how it was calculated and lets us calculate the derivative. So if you do a mathematical operation on a tensor in PyTorch, you can call backward to calculate the derivative. What happens to that derivative? It gets stuck inside an attribute called .grad. So I'm going to take my coefficients A, and I am going to subtract from them my gradient. And there's an underscore here. Why? Because that's going to do it in place. So it's going to actually update those coefficients A to subtract the gradients from them, right? So why do we subtract? Well, because the gradient tells us if I move the whole thing downwards, the loss goes up. If I move the whole thing upwards, the loss goes down. So I want to do the opposite of the thing that makes it go up, right? So because our loss, we want our loss to be small. So that's why we have to subtract. And then there's something here called LR. LR is our learning rate. And so literally all it is the thing that we multiply by the gradient. Why is there any LR at all? Let me show you why. Let's take a really simple example. A quadratic. Right? And let's say your algorithm's job was to find where that quadratic was at its lowest point. And so how could it do this? Well, just like what we're doing now, the starting point would just be to pick some x value at random and then pop up here to find out what the value of y is. Okay? And that's its starting point. And so then it can calculate the gradient. And the gradient is simply the slope. Right? It tells you moving in which direction is going to make you go down. And so the gradient tells you you have to go this way. So if the gradient was really big, you might jump this way a very long way. So you might jump all the way over to here, maybe even here, right? And so if you jumped over to there, then that's actually not going to be very helpful, because then you see, well, where does that take us to? Oh, it's now worse, right? We jumped too far. So we don't want to jump too far, so maybe we should just jump a little bit, maybe to here. And the good news is that is actually a little bit closer. And so then we'll just do another little jump, see what the gradient is, and do another little jump. That takes us to here. And another little jump, that takes us to here. Here, here, right? So in other words, we find our gradient to tell us kind of what direction to go and like, do we have to go a long way or not too far? But then we multiply it by some number less than 1 so we don't jump too far. And so hopefully at this point, this might be reminding you of something, which is what happened when our learning rate was too high. So do you see why that happened now? Our learning rate was too high, meant that we jumped all the way past the right answer, further than we started with, and it got worse and worse and worse. So that's what a learning rate too high does. On the other hand, if our learning rate is too low, then you just take tiny little steps. And so eventually you're going to get there, but you're doing lots and lots of calculations along the way. So you really want to find something where it's kind of either like this, or maybe it's kind of a little bit backwards and forwards. Maybe it's kind of like this. Something like that. You know, you want something that kind of gets in there quickly, but not so quickly it jumps out and diverges, not so slowly that it takes lots of steps. So that's why we need a good learning rate. And so that's all it does. So if you look inside the source code of any deep learning library, you'll find this. You'll find something that just says coefficients dot subtract learning rate times gradient. And we'll learn about some we'll learn about some easy but important optimizations we can do to make this go faster. But that's basically it. There's a couple of other little minor issues that we don't need to talk about now, one involving zeroing out the gradients, another involving making sure that you turn gradient calculation off when you do the SGD update. If you're interested, we can discuss them on the forum. Or you can do our Introduction to Machine Learning course, which covers all the mechanics of this in more detail. But this is the basic idea. So if we run update 100 times, printing out the loss from time to time, you can see it starts at 8.9, and it goes down, 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 down. And so we can then print our scatter plots, and there it is. That's it. Believe it or not, that's gradient descent. So we just need to start with a function that's a bit more complex than x at a. But as long as we have a function that can represent things like, is this a teddy bear, we now have a way to fit it. Okay? And so let's now take a look at this as a picture, as an animation. And this is one of the nice things that you can do with Matplotlib, is you can take any plot and turn it into an animation, right? And so you can now actually see it updating each step. So let's see what we did here. We simply said, as before, create a scatter plot, but then rather than having a loop, we used Matplotlib's func animation to call 100 times this function. And this function just called that update that we created earlier, and then updated the y data in our line. And so it did that 100 times, waiting 20 milliseconds after each one, and there it is. Right? So you might think that like visualizing your algorithms with animations is some amazing and complex thing to do, but actually now you know it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 lines of code. Okay? So I think that is pretty damn cool. So that is SGD visualized. And so we can't visualize as conveniently what updating 50 million parameters in a ResNet 34 looks like, but it's basically doing the same thing. Okay? And so studying these simple versions is actually a great way to get an intuition. So you should try running this notebook with a really big learning rate, with a really small learning rate, and see what this animation looks like. Right? And try and get a feel for it. Maybe you can even try a 3D plot. I haven't tried that yet, but I'm sure it would work fine too. So the only difference between stochastic gradient descent and this is something called mini batches. You'll see what we did here was we calculated the value of the loss on the whole data set on every iteration. But if your data set is 1.5 million images in ImageNet, that's going to be really slow, right? Just to do a single update of your parameters, you've got to calculate the loss on 1.5 million images. You wouldn't want to do that. So what we do is we grab 64 images or so at a time at random, and we calculate the loss on those 64 images, and we update our weights. And then we grab another 64 random images, and we update the weights. So in other words, the loop basically looks exactly the same, but at this point here, it would basically be y, square bracket, and some random indexes here, and some random indexes here, and we'd basically do the same thing. Well, actually, sorry, it would be there, right? So some random indexes on our x and some random indexes on our y to do a mini batch at a time. That would be the basic difference. And so once you add those, grab a random few points each time, those random few points are called your mini batch, and that approach is called SGD, or stochastic gradient descent. Okay. So there's quite a bit of vocab we've just covered, right? So let's just remind ourselves. The learning rate is a thing that we multiply our gradient by to decide how much to update the weights by. An epoch is one complete run through all of our data points, or all of our images. So for the non-stochastic gradient descent we just did, every single loop we did the entire data set. But if you've got a data set with 1,000 images and your mini batch size is 100, then it would take you 10 iterations to see every image once. So that would be one epoch. Epochs are important because if you do lots of epochs, then you're looking at your images lots of times. And so every time you see an image, there's a bigger chance of overfitting. So we generally don't want to do too many epochs. A mini batch is just a random bunch of points that you use to update your weights. SGD is just gradient descent using mini batches. Architecture and model kind of mean the same thing. In this case, our architecture is y equals xa. Right? The architecture is the mathematical function that you're fitting the parameters to. And we're going to learn either today or next week what the mathematical function of things like ResNet34 actually is. But it's basically pretty much what you've just seen. It's a bunch of matrix products. Parameters, also known as coefficients, also known as weights, are the numbers that you're updating. And then loss function is the thing that's telling you how far away or how close you are to the correct answer. Any questions? All right. So these models, these predictors, these teddy bear classifiers are functions that take pixel values and return probabilities. They start with some functional form like y equals xa, and they fit the parameters a using SGD to try and do the best to calculate your predictions. So far we've learned how to do regression, which is a single number. Next week we'll learn how to do the same thing for classification, where we have multiple numbers, but it's basically the same. In the process, we had to do some math. We had to do some linear algebra, and we had to do some calculus. And a lot of people get a bit scared at that point and tell us, I am not a math person. If that is you, that's totally okay, but you're wrong. You are a math person. In fact, it turns out that when in the actual academic research around this, there are not math people and non-math people. It turns out to be entirely a result of culture and expectations. So you should check out Rachel's talk. There's no such thing as not a math person, where she will introduce you to some of that academic research. And so if you think of yourself as not a math person, you should watch this so that you learn that you're wrong, that your thoughts are actually there because somebody has told you you're not a math person. But there's actually no academic research to suggest that there is such a thing. In fact, there are some cultures, like Romania and China, where the not a math person concept never even appeared. It's almost unheard of in some cultures for somebody to say, I'm not a math person, because that just never entered that cultural identity. So don't freak out if words like derivative and gradient and matrix product are things that you're kind of scared of. It's something you can learn. It's something you'll be okay with. Okay. So the last thing that we're going to close with today. Oh, I just got a message from Simon Willison. Simon's telling me he's actually not that special. Lots of people won medals. So that's the worst part about Simon, is not only is he really smart, he's also really modest, which I think is just awful. I mean, if you're going to be that smart, at least be a horrible human being and, you know, make it okay. Okay, so the last thing I want to close with is the idea of, and we're going to look at this more next week, underfitting and overfitting. We just fit a line to our data, but imagine that our data wasn't actually line-shaped, right? And so if we tried to fit something which was like constant plus constant times x, i.e. a line to it, then it's never going to fit very well, right? No matter how much we change these two coefficients, it's never going to get really close. On the other hand, we could fit some much bigger equation, so in this case it's a higher degree polynomial, with lots of wiggly bits, like so, right? But if we did that, it's very unlikely we go and look at some other place to find out the temperature that it is and how much ice cream they're selling and that we'll get a good result, because like the wiggles are far too wiggly. So this is called overfitting. We're looking for some mathematical function that fits just right, to stay with the teddy bear analogies. So you might think, if you have a statistics background, the way to make things fit just right is to have exactly the right number of parameters. It's to use a mathematical function that doesn't have too many parameters in it. It turns out that's actually completely not the right way to think about it. There are other ways to make sure that we don't overfit. And in general, this is called regularization. Regularization are all the techniques to make sure that when we train our model, that it's going to work not only well on the data it's seen, but on the data it hasn't seen yet. So the most important thing to know when you've trained a model is actually how well does it work on data that it hasn't been trained with. And so as we're going to learn a lot about next week, that's why we have this thing called a validation set. So what happens with a validation set is that we do our mini batch STD training loop with one set of data, with one set of teddy bears, grizzlies, black bears. And then when we're done, we check the loss function and the accuracy to see how good is it on a bunch of images which were not included in the training. And so if we do that, then if we have something which is too wiggly, it'll tell us, oh, your loss function and your error is really bad, because on the bears that it hasn't been trained with, the wiggly bits are in the wrong spot. Or if it was underfitting, it would also tell us that your validation set's really bad. So, like, even for people that don't go through this course and don't learn about the details of deep learning, like if you've got managers or colleagues or whatever at work who are kind of wanting to like learn about AI, the only thing that you really need to be teaching them is about the idea of a validation set, because that's the thing they can then use to figure out, you know, is somebody selling them snake oil or not? You know, to like hold back some data, and then they get told like, oh, here's a model that we're going to roll out. And then you say, okay, fine. I'm just going to check it on this held out data to see whether it generalizes. There's a lot of details to get right when you design your validation set. We will talk about them briefly next week, but a more full version would be in Rachel's piece on the FastAI blog called How and Why to Create a Good Validation Set. And this is also one of the things we go into in a lot of detail in the Intro to Machine Learning course. So we're going to try and give you enough to get by for this course, but it is certainly something that's worth deeper study as well. Any questions or comments before we wrap up? Okay, good. All right, well, thanks everybody. I hope you have a great time building your web applications. See you next week.
Welcome back to lesson 3. So we're going to start with a quick correction, which is to let you know that when we referred to this chart as coming from Quora last week, we were correct. It did come from Quora, but actually we realized originally it came from Andrew Ng's excellent machine learning course on Coursera. So apologies for the incorrect citation. But in exchange, let's talk about Andrew Ng's excellent machine learning course on Coursera. It's really great. As you can see, people gave it 4.9 out of 5 stars. In some ways, it's a little dated, but a lot of the content really is as appropriate as ever and taught in a more bottom-up style. So it can be quite nice to combine Andrew's bottom-up style and our top-down style and meet somewhere in the middle. Also, if you're interested in more machine learning foundations, you should check out our machine learning course as well. If you go to course.fast.ai and click on the machine learning button, that will take you to our course, which is about twice as long as this deep learning course and kind of takes you much more gradually through some of the foundational stuff around validation sets and model interpretation and how PyTorch tensors work and stuff like that. I think all these courses together, if you want to really dig deeply into the material, do all of them. I know a lot of people who have and end up saying, oh, I got more out of each one by doing the whole lot. Or you can skip backwards and forwards, see which one works for you. We started talking about deploying your web app last week. One thing that's going to make life a lot easier for you is that on the Course V3 website, there's a production section where right now we have one platform, but more will be added by the time this video comes out, showing you how to deploy your web app really, really easily. And when I say easily, for example, here's the How to Deploy on Zeit guide created by San Francisco study group member Navjot. As you can see, it's just a page. There's almost nothing to do. And it's free. It's not going to serve 10,000 simultaneous requests, but it'll certainly get you started, and I found it works really well. It's fast, and so deploying a model doesn't have to be slow or complicated anymore. And the nice thing is you can kind of use this for an MVP, and if you do find you're starting to get 1,000 simultaneous requests, then you know that things are working out, and you can start to upgrade your instance types or add to a more traditional big engineering approach. So if you actually use this starter kit, it will actually create my teddy bear finder for you. And this is an example of my teddy bear finder. So the idea is it's as simple as possible, this template. So you can fill in your own style sheets, your own custom logic, and so forth. This is kind of designed to be a minimal thing so you can see exactly what's going on. The back end is a simple kind of REST style interface that sends back JSON, and the front end is a super simple little JavaScript thing. It should be a good way to get a sense of how to build a web app which talks to a PyTorch model. So examples of web apps people have built during the week. Edward Ross built the What Car Is That app, or more specifically the What Australian Car Is That. I thought it was kind of interesting that Edward said on the forum that the building of the app was actually a great experience in terms of understanding how the model works himself better. And it's interesting that he's describing trying it out on his phone. And a lot of people think oh, if I want something on my phone, I have to create some kind of mobile TensorFlow, ONNX, whatever, tricky mobile app. You really don't. You can run it all in the cloud and make it just a web app, or use some kind of simple little GUI front end that talks to a REST back end. It's not that often that you'll need to actually run stuff on the phone. So this is a good example of that. C. Werner has created a guitar classifier. You can decide whether your food is healthy or not. Apparently this one is healthy. That can't be right. I would have thought a hamburger is more what we're looking for, but there you go. Apparently Trinidad and Tobago is the home of the hummingbird. So if you're visiting, you can find out what kind of hummingbird you're looking at. You can decide whether or not to eat a mushroom. If you happen to be one of the cousins of Charlie Harrington, you can now figure out who is who. I believe this was actually designed for his fiancée. Even will tell you about the interests of this particular cousin. So, fairly niche application, but, apparently there are 36 people who will appreciate this at least. I have no cousins. That's a lot of cousins. This is an example of an app which actually takes a video feed and turns it into a motion classifier. That's pretty cool. I like it. Team 26, good job. Here's a similar one for American Sign Language. And so, it's not a big step from taking a single image model to taking a video model. You can just grab the occasional frame, put it through your model, and update the UI as the kind of model results come in. So it's really cool that you can do this kind of stuff either in client or in browser nowadays. Henry Palacci has built Your City From.space, which he describes as creepy, how accurate it is. So here is where I live, which it figured out was in the United States. It's interesting, he describes here how he actually had to be very thoughtful about the validation set he built, make sure that the satellite tiles were not overlapping or close to each other. In doing so, he realized he had to download more data, but once he did, he got this amazingly effective model that can look at satellite imagery and figure out what country it's from. I thought this one was pretty interesting, which was doing univariate time series analysis by converting it into a picture using something I've never heard of, a gradient angular field. But he says he's getting close to state-of-the-art results for univariate time series modeling by turning it into a picture. And so I like this idea of turning stuff that's not a picture into a picture. So something really interesting about this project, which was looking at emotion classification from faces, was that he was specifically asking the question, how well does it go without changing anything, just using the default settings? Which I think is a really interesting experiment because we're all told it's really hard to train models and it takes a lot of, specific knowledge. And actually we're finding that that's often not the case. And he looked at this facial expression recognition data set. There was a 2017 paper that he compared his results to, and he got equal or slightly better results than the state-of-the-art paper on emotion recognition without doing any custom hyperparameter tuning at all. So that was really cool. And then Elena Harley, who I featured one of her works last week, has done another really cool work in the genomic space, which is looking at variant analysis, looking at false positives in these kinds of pictures. And she found she was able to decrease the number of false positives coming out of the kind of industry standard software she was using by 500% by using a deep learning workflow. And I think this is a nice example of something where if you're going through, spending hours every day looking at something, in this case looking at, kind of get rid of the false positives, maybe you can make that a lot faster by using deep learning to do a lot of the work for you. And again, this is an example of a computer vision-based approach on something which initially wasn't actually images. So that was, that's a really cool application. So really nice to see what people have been building in terms of both web apps and just classifiers. What we're going to do today is look at a whole lot more different types of model that you can build. and we're going to kind of zip through them pretty quickly, and then we're going to go back and say, like, oh, how did all these things work? What's the common denominator? But all of these things, you can create web apps from these as well, but you'll have to think about how to slightly change that template to make it work with these different applications. I think that'll be a really good exercise in making sure you understand the material. So the first one we're going to look at is a data set of satellite images. And satellite imaging is a really fertile area for deep learning. It's certainly a lot of people already using deep learning and satellite imaging, but only scratching the surface. And the data set that we're going to look at looks like this. It has satellite tiles, and for each one, as you can see, there's a number of different labels for each tile. One of the labels always represents the weather that's shown, so in this case cloudy or partly cloudy. And then all of the other labels tell you any interesting features that are seen there. So primary means primary rainforest, agriculture means there's some farming, road, and so forth. So as I'm sure you can tell, this is a little different to all the classifiers we've seen so far, because there's not just one label, there's potentially multiple labels. So multi-label classification can be done in a very similar way. But the first thing we're going to need to do is to download the data. Now this data comes from Kaggle. Kaggle is mainly known for being a competitions website, and it's really great to download data from Kaggle when you're learning, because you can see how would I have gone in that competition. And it's a good way to see whether you kind of know what you're doing. I tend to think the goal is to try and get in the top 10%. In my experience, all the people in the top 10% of a competition really know what they're doing. So if you can get in the top 10%, then that's a really good sign. Pretty much every Kaggle data set is not available for download outside of Kaggle, at least the competition data sets. So you have to download it through Kaggle. The good news is that Kaggle provides a Python-based downloader tool, which you can use. So we've got a quick description here of how to download stuff from Kaggle. So to install stuff, to download stuff from Kaggle, you first have to install the Kaggle download tool, so just pip install Kaggle. And so you can see what we tend to do when there's one-off things to do is we show you the commented out version in the notebook, and you can just remove the comment. So here's a cool tip for you. If you select a few lines and then hit Control/, it uncomments them all. And then when you're done, select them again, Control/ again, and recomments them all. Okay? So if you run this line, it'll install Kaggle for you. Depending on your platform, you may need sudo, you may need / something else, /pip, you may need source activate. So have a look on the setup instructions, or actually the returning to work instructions on the course website to see, like, when we do conda install, you have to do the same basic steps for your pip install. So once you've got that module installed, you can then go ahead and download the data. And basically it's as simple as saying Kaggle competitions download, the competition name, and then the files that you want. The only other steps before you do that is that you have to authenticate yourself. And you'll see there's a little bit of information here on exactly how you can go about downloading from Kaggle the file containing your API authentication information. So I won't bother going through it here, but just follow these steps. Sometimes stuff on Kaggle is not just zipped or tarred, but it's compressed with a program called 7-zip, which will have a 7z extension. If that's the case, you'll need to either apt install p7zip, or, and here's something really nice, some kind person has actually created a conda installation of 7-zip that works on every platform. So you can always just run this conda install, doesn't even require sudo or anything like that. And this is actually a good example of where conda is super handy, is that you can actually install binaries and libraries and stuff like that, and it's nicely cross-platform. So that's a good, if you don't have 7-zip installed, that's a good way to get it. And so this is how you unzip a 7-zip file. In this case, it's tarred and 7-zipped, so you can do this all in one step. So 7ZA is the name of the 7-zip archiver program that you would run. Okay, so that's all basic stuff, which if you're not so familiar with the command line and stuff, it might take you a little bit of experimenting to get it working. Feel free to ask on the forum. Make sure you search the forum first to get started. Okay, so once you've got the data downloaded and unzipped, you can take a look at it. So in this case, because we have multiple labels for each tile, we clearly can't have a different folder for each image telling us what the label is. We need some different way to label it. And so the way that Kaggle did it was they provided a CSV file that had each file name along with a list of all of the labels. In order to just take a look at that CSV file, we can read it using the pandas library. If you haven't used pandas before, it's kind of the standard way of dealing with tabular data in Python. It pretty much always appears in the PD namespace. In this case, we're not really doing anything with it other than just showing you the contents of this file. So we can read it, we can take a look at the first few lines, and there it is. So we want to turn this into something we can use for modeling. So the kind of object that we use for modeling is an object of the data bunch class. So we have to somehow create a data bunch out of this. Once we have a data bunch, we'll be able to go .showBatch to take a look at it, and then we'll be able to go create CNN with it, and then we'll be able to start training. Okay? So really the trickiest step previously in deep learning has often been getting your data into a form that you can get it into a model. So far, we've been showing you how to do that using various factory methods. So methods where you basically say, I want to create this kind of data from this kind of source with these kinds of options. The problem is, I mean, that works fine sometimes, and we showed you a few ways of doing it over the last couple of weeks. But sometimes you want more flexibility, because there's so many choices that you have to make about where do the files live and what's the structure they're in and how do the labels appear and how do you split out the validation set and how do you transform it and so forth. So we've got this unique API that I'm really proud of called the data block API. And the data block API makes each one of those decisions a separate decision that you make. There's separate methods and with their own parameters for every choice that you make around how do I create, set up my data. So for example, to grab the planet data, we would say we've got a list of image files that are in a folder and they're labeled based on a CSV with this name. They have this separator. Remember I showed you back here that there's a space between them? So by passing in separator, it's going to create multiple labels. The images are in this folder. They have this suffix. We're going to randomly split out a validation set with 20% of the data. We're going to create data sets from that, which we're then going to transform with these transformations. And then we're going to create a data bunch out of that, which we'll then normalize using these statistics. So there's all these different steps. So to give you a sense of what that looks like, the first thing I'm going to do is kind of go back and explain what are all of the PyTorch and FastAI kind of classes that you need to know about that are going to appear in this process, because you're going to see them all the time in the FastAI docs and the PyTorch docs. So the first one you need to know about is a class called a dataset. And the dataset class is part of PyTorch, and this is the source code for the dataset class. As you can see, it actually does nothing at all. The dataset class in PyTorch defines two things, get item and len. In Python, these special things that are underscore, underscore something, underscore, underscore, Pythonistas call them dunder something. So this would be dunder get item, dunder len. And they're basically special magical methods that do some special behavior. This particular method, you can look them up in the Python docs. This particular method means that your object, if you had an object called O, can be indexed with square brackets. something like that, right? So that would call get item with 3 as the index. And then this one called len means that you can go len o, and it will call that method. Now, and you can see in this case, they're both not implemented. So that is to say, although PyTorch says tell PyTorch about your data, you have to create a data set. It doesn't really do anything to help you create the data set. It just defines what the data set needs to do. So in other words, your data, the starting point for your data, is something where you can say, what is the third item of data in my data set? So that's what getItem does. And how big is my data set? That's what the length does. So FastAI has lots of data set subclasses that do that for all different kinds of stuff. And so far, you've been seeing image classification data sets. So they're data sets where getItem will return an image and a single label of what is that image. So that's what a data set is. Now, a data set is not enough to train a model. The first thing we know we have to do, if you think back to the gradient descent tutorial last week, is we have to have a few images or a few items at a time so that our GPU can work in parallel. Remember, we do this thing called a mini batch. A mini batch is a few items that we present to the model at a time that it can train from in parallel. So to create a mini batch, we use another PyTorch class called a data loader. And so a data loader takes a data set in its constructor. So it's now saying, oh, this is something I can get the third item and the fifth item and the ninth item. And it's going to grab items at random and create a batch of whatever size you ask for and pop it on the GPU and send it off to your model for you. Right? So a data loader is something that grabs individual items, combines them into a mini batch, pops them on the GPU for modeling. So that's called a data loader, and it comes from a data set. So you can see already there's kind of choices you have to make. You know, what kind of data set am I creating? What is the data for it? Where is it going to come from? And then when I create my data loader, what batch size do I want to use? Right? This still isn't enough to train a model. Not really, because we've got no way to validate the model. If all we have is a training set, then we have no way to know how we're doing because we need a separate set of held out data, a validation set to see how we're getting along. So for that, we use a FastAI class called a data bunch. And a data bunch is something which, as it says here, binds together a training data loader and a valid data loader. And when you look at the FastAI docs, when you see these kind of monospace font things, they're always referring to some symbol you can look up elsewhere. So in this case, you can see trainDL is here. And there's no point knowing what that there's an argument with a certain name unless you know what that argument is. So you should always look after the colon to find out that is a data loader. Okay, so when you create a data bunch, you're basically giving it a training set data loader and a validation set data loader. And that's now an object that you can send off to a learner and start learning, start fitting. Right? So they're the basic pieces. So coming back to here, this stuff, plus this line, is all the stuff which is creating the data set. So it's saying where did the images come from? Because the data set, the indexer returns two things. It returns the image and the labels, assuming it's an image data set. So where do the images come from? Where do the labels come from? And then I'm going to create two separate data sets, the training and the validation. This is the thing that actually turns them into PyTorch data sets. This is the thing that transforms them. Okay, and then this is actually going to create the data loader and the data bunch in one go. So let's look at some examples of this data block API, because once you understand the data block API, you'll never be lost for how to convert your data set into something you can start modeling with. So here's some examples of using the data block API. So for example, if you're looking at MNIST, which remember is the pictures and classes of handwritten numerals, you can do something like this. what kind of data set is this going to be? It's going to come from a list of image files which are in some folder, and they're labeled according to the folder name that they're in. And then we're going to split it into train and validation according to the folder that they're in, train and validation. You can optionally add a test set. We're going to be talking more about test sets later in the course. Okay, we'll convert those into PyTorch data sets now that that's all set up. We'll then transform them using this set of transforms. And we're going to transform into something of this size. And then we're going to convert them into a data bunch. So each of those stages inside these parentheses are various parameters you can pass to customize how that all works, right? But in the case of something like this MNIST data set, all the defaults pretty much work. So this is all fine. So here it is. So you can check, let's grab something. So data.trainds is the data set, not the data loader, the data set. So I can actually index into it with a particular number. So here is the 0 indexed item in the training data set. It's got an image and a label. We can show batch to see an example of the pictures of it, and we could then start training. Here are the classes that are in that data set. And this little cut down sample of MNIST just has 3s and 7s. Here's an example using Planet. This is actually, again, a little subset of Planet we use for, make it easy to try things out. So in this case, again, it's an image file list. Again, we're grabbing it from a folder. This time we're labeling it based on a CSV file. We're randomly splitting it. By default, it's 20%. Creating data sets, transforming it using these transforms. We're going to use a smaller size and then create a data bunch. There it is. And so data bunches know how to draw themselves, amongst other things. So here's some more examples we're going to be seeing later today. What if we look at this data set called CanVid? CanVid looks like this. It contains pictures, and every pixel in the picture is color-coded, right? So in this case, we have a list of files in a folder, and we're going to label them, in this case, using a function. And so this function is basically the thing, we're going to see it later, which tells it whereabouts of the color coding for each pixel. It's in a different place. Randomly split it in some way, create some data sets in some way. We can tell it for our particular list of classes, how do we know what pixel value 1 versus pixel value 2 is? And that was something that we can basically read in, like so. Again, some transforms. Create a data bunch. You can optionally pass in things like what batch size do you want. And again, it knows how to draw itself, and you can start learning with that. Or one more example. What if we wanted to create something like this? It has like vase and chair and remote control and book. This is called an object detection data set. So again, we've got a little minimal COCO data set. COCO is kind of the most famous academic data set for object detection. We can create it using the same process. Grab a list of files from a folder, label them according to this little function, randomly split them, create an object detection data set, create a data bunch. In this case, as you'll learn, when we get to object detection, you have to use generally smaller batch sizes or you'll run out of memory. As you'll also learn, you have to use something called a collation function. And once that's all done, we can again show it, and here's our object detection data set. So you get the idea, right? So here's a really convenient notebook. Where will you find this? This notebook is the documentation. Remember how I told you that all of the documentation comes from notebooks? You'll find them in your FastAI repo in docs_source. So this, which you can play with and experiment with inputs and outputs and try all the different parameters, you will find the data block API examples of use. If you go to the documentation, here it is, the data block API examples of use. Right? So remember, everything that you want to use in FastAI, you can look it up in the documentation. So let's search data block API. Go straight there. And away you go. And so once you find some documentation that you actually want to try playing with yourself, just look up the name, data block, and then you can open up a notebook with the same name in the FastAI repo and play with it yourself. Okay. So that's a quick overview of this really nice data block API, and there's lots of documentation for all of the different ways you can label inputs and split data and create data sets and so forth. And so that's what we're using for Planet. Okay, so we're using that API. You'll see, like in the documentation, these two steps we had all joined up together. We can certainly do that here too, but you'll learn in a moment why it is that we're actually splitting these up into two separate steps, which is also fine as well. So a few interesting points about this. Transforms. So transforms by default, remember you can hit Shift-Tab to get all the information, right? Transforms by default will flip randomly each image, right? But they'll actually randomly only flip them horizontally, which makes sense, right? If you're trying to tell if something's a cat or a dog, it doesn't matter whether it's pointing left or right, but you wouldn't expect it to be upside down. On the other hand, satellite imagery, whether something's cloudy or hazy, or whether there's a road there or not, could absolutely be flipped upside down. There's no such thing as a right way up from space. So flip vert, which defaults to false, we're going to flip over to true to say, like, yeah, randomly, you should actually do that. And it doesn't just flip it vertically. It actually tries also each possible 90-degree rotation. So there are 8 possible kind of symmetries that it tries out. So there's various other things here. I found that these particular settings work pretty well for Planet. One that's interesting is warp. Perspective warping is something which very few libraries provide, and those that do provide it, it tends to be really slow. I think FastAI is the first one to provide really fast perspective warping. And basically, the reason this is interesting is if I kind of look at you from below versus look at you from above, the kind of your shape changes, right? And so when you're taking a photo of a cat or a dog, you know, sometimes you'll be higher, sometimes you'll be lower. Then that kind of change of shape is certainly something that you would want to include as you're creating your training batches. You want to modify it a little bit each time. Not true for satellite images. A satellite always points straight down at the planet. So if you added perspective warping, you would be making changes that aren't going to be there in real life. So I turn that off. So this is all something called data augmentation. We'll be talking a lot more about it later in the course. But you can start to get a feel for the kinds of things that you can do to augment your data. And in general, maybe the most important one is if you're looking at astronomical data or kind of pathology, you know, digital slide data or satellite data, you know, data where there isn't really an up or a down, turning on flip vert equals true is generally going to make your models generalize better. Okay, so here's the steps necessary to create our data bunch. And so now to create a satellite imagery classifier, multi-label classifier, that's going to figure out for each satellite tile what's the weather and what can I see in it. There's basically nothing else to learn. Everything else that you've already learnt is going to be exactly nearly the same. Here it is. Learn equals create CNN. Data, architecture, right? And in this case, when I first built this notebook, I used ResNet 34 as per usual. And I found this was a case, I tried ResNet 50 as I always like to do. I found ResNet 50 helped a little bit and I had some time to run it. So in this case, I was using ResNet 50. There's one more change I make, which is metrics. Now, to remind you, a metric has got nothing to do with how the model trains. Changing your metrics will not change your resulting model at all. The only thing that we use metrics for is we print them out during training. See here, it's printing out accuracy and it's printing out this other metric called F beta. So if you're trying to figure out how to do a better job with your model, changing the metrics will never be something that you need to do there. They're just to show you how you're going. So that's the first thing to know. You can have one metric or no metrics or a list of multiple metrics. to be printed out as your model's training. In this case, I want to know two things. The first thing I want to know is the accuracy, and the second thing I want to know is how would I go on Kaggle? And Kaggle told me that I'm going to be judged on a particular metric called the F-score. So I'm not going to bother telling you about the F-score. It's not really interesting enough to be worth spending your time on. You can look it up. But it's basically this. When you have a classifier, you're going to have some false positives. You're going to have some false negatives. How do you weigh up those two things to kind of create a single number? There's lots of different ways of doing that, and something called the F-score is basically a nice way of combining that into a single number. And there are various kinds of F-scores, F1, F2, and so forth. And Kaggle said in the competition rules, we're going to use a metric called F2. So we have a metric called F beta, which is, in other words, it's F with 1 or 2 or whatever, depending on the value of beta. And we can have a look at its signature, and you can see that it's got a threshold and a beta. Okay, so the beta is 2 by default, and Kaggle said that they're going to use F2, so I don't have to change that. But there's one other thing that I need to set, which is a threshold. What does that mean? Well, here's the thing. Do you remember we had a little look the other day at the source code for the accuracy metric? So if you put 2 question marks, you get the source code. And we found that it used this thing called argmax. And the reason for that, if you remember, was we kind of had this, input image that came in, and it went through our model, and at the end, it came out with a table of 10 numbers, right? This is like if we're doing MNIST digit recognition, and the 10 numbers were like the probability of each of the possible digits. And so then we had to look through all of those and find out which one was the biggest. And so that the function in NumPy or PyTorch or just math notation that finds the biggest and returns its index is called argmax, right? So to get the accuracy for our pet detector, we used this accuracy function that's called argmax to find out behind the scenes which class ID, pet, was the one that we're looking at, and then it compared that to the actual, and then took the average, and that was the accuracy. We can't do that for satellite recognition in this case because there isn't one label we're looking for. There's lots. So instead, what we do is we look at, so in this case, I don't know if you remember, but a data bunch has a special attribute called C. And C is going to be basically how many outputs do we want our model to create. And so for any kind of classifier, we want one probability for each possible class. So in other words, data.c for classifiers is always going to be equal to the length of data.classes. Right? So data.classes, there they all are. There's the 17 possibilities, right? So we're going to have one probability for each of those. But then we're not just going to pick out one of those 17. We're going to pick out n of those 17. And so what we do is we compare each probability to some threshold. And then we say anything that's higher than that threshold, we're going to assume that the model's saying it does have that feature. And so we can pick that threshold. I found that for this particular data set, a threshold of 0.2 seems to generally work pretty well. This is the kind of thing you can easily just experiment to find a good threshold. So I decided I wanted to print out the accuracy at a threshold of 0.2. So the normal accuracy function doesn't work that way. It doesn't argmax. We have to use a different accuracy function called accuracy_thresh. And that's the one that's going to compare every probability to a threshold and return all the things higher than that threshold and compare accuracy that way. And so one of the things we would pass in is thresh. Now, of course, our metric is going to be calling our function for us. So we don't get to tell it every time every time it calls back, what threshold do we want? So we really want to create a special version of this function that always uses an accuracy of a threshold of 0.2. So one way to do that would be to go define something called accuracy O2 that takes some input and some target and returns accuracy threshold with that input and that target and a threshold of 0.2. We could do it that way, right? But it's so common that you want to kind of say, create a new function that's just like that other function, but we're always going to call it with a particular parameter. That computer science has a term for that. It's called a partial. It's called a partial function application. And so Python 3 has something called partial that takes some function and some list of keywords and values and creates a new function that is exactly the same as this function, but is always going to call it with that keyword argument. So here, this is exactly the same thing as the thing I just typed in. Ac02 is now a new function that calls accuracy thresh with a threshold of 0.2. And so this is a really common thing to do, particularly with the FastAI library, because there's lots of places where you have to pass in functions, and you very often want to pass in a slightly customized version of a function. So here's how you do it. So here I've got an accuracy threshold 0.2. I've got a f beta threshold 0.2. I can pass them both in as metrics. And I can then go ahead and do all the normal stuff. LR find, recorder.plot, find the thing with the steepest slope. So I don't know, somewhere around 1e neg 2. So we'll make that our learning rate. And then fit for a while with 5, slice LR, and see how we go. Okay? And so we've got an accuracy of about 96% and an f beta of about 0.926. And so you could then go and have a look at Planet, leaderboard, private leaderboard. Okay, and so the top 50th is about 0.93. So we kind of say like, oh, we're on the right track. Okay, with something we're doing fine. So as you can see, like once you get to a point that the data's there, there's very little extra to do most of the time.
So when your model makes an incorrect prediction in a deployed app, is there a good way to record that error and use that learning to improve the model in a more targeted way?
Oh yeah, that's a great question. So the first bit, is there a way to record that? Of course there is. You record it. That's up to you, right? So maybe some of you can try it this week. You need to have your user tell you you were wrong. This Australian car, you said it was a Holden, and actually it's a Falcon. So first of all, you'll need to collect that feedback, and the only way to do that is to ask the user to tell you when it's wrong. So you now need to record in some log somewhere, something saying, you know, this was the file, I've stored it here, this was the prediction I made, this was the actual, this is the actual that they told me, and then at the end of the day or at the end of the week, you could set up a little job to run something, or you can manually run something. And what are you going to do? You're going to do some fine-tuning. What does fine-tuning look like? Good segue, Rachel. It looks like this, right? So let's pretend here's your saved model, right? And so then we unfreeze, right? And then we fit a little bit more, right? Now in this case, I'm fitting with my original data set. But you could create a new data bunch with just the misclassified instances and go ahead and fit, right? And the misclassified ones are likely to be particularly interesting, so you might want to fit at a slightly higher learning rate, you know, to make them kind of really mean more, or you might want to run them through a few more epochs. But it's exactly the same thing, right? You just call fit with your misclassified examples and passing in the correct classification. And that should really help your model quite a lot. There are various other tweaks you can do to this, but that's the basic idea.
The next question, could someone talk a bit more about the data block ideology? I'm not quite sure how the blocks are meant to be used. Do they have to be in a certain order? Is there any other library that uses this type of programming that I could look at?
Yes, they do have to be in a certain order. They do have to be in a certain order, and it's basically the order that you see in the example of use, right? It's what kind of data do you have? Where does it come from? How do you label it? How do you split it? What kind of data sets do you want? Optionally, how do I transform it? And then how do I create a data bunch from it? So they're the steps. I mean, we invented this API. I don't know if other people have independently invented it. The basic idea of kind of a pipeline of things that dot into each other is pretty common in a number of places. Not so much in Python, but you see it more in JavaScript. Although this kind of approach of like each stage produces something slightly different, you tend to see it more in like ETL software, like extraction, transformation, and loading software, where there's kind of particular stages in a pipeline. So yeah, I mean, it's been inspired by a bunch of things. But yeah, all you need to know is kind of use this example to guide you, and then look up the documentation to see, which particular kind of thing you want. And in this case, the image file list, you're actually not going to find the documentation for image file list in DataBlock's documentation, because this is specific to the vision application. So to then go and actually find out how to do something for your particular application, you would then go, to look at text and vision and so forth, and that's where you can find out what are the DataBlock API pieces available for that application. And of course, you can then look at the source code. If you've got some totally new application, you could create your own part of any of these stages. Like pretty much all of these functions are, very few lines of code. Maybe we could look at an example of one. Image list from folder, so let's just put that somewhere temporary. And then we're going to go t.label from CSV. Then you can look at the documentation to see exactly what that does, and that's going to call label from data frame. So I mean, this is already like useful. Like if you wanted to create a data frame, a pandas data frame from something other than the CSV, you now know that you could actually just call label from data frame, and you can look up to find what that does. And as you can see, like most fast AI functions are no more than a few lines of code. They're normally pretty straightforward to see what are all the pieces there and how can you use them. And it's probably one of these things that as you play around with it, you'll get a good sense of how it all gets put together. But if during the week there are particular things where you're thinking, I don't understand how to do this, please let us know and we'll try to help you. Sure.
What resources do you recommend for getting started with video? For example, being able to pull frames and submit them to your model.
I guess the answer is it depends. If you're using the web, which I guess probably most of you will be, then there's web APIs that basically do that for you. So you can grab the frames with the web API, and then they're just images which you can pass along. If you're doing it client side, I guess most people tend to use OpenCV for that. But maybe people during the week could, who are doing these video apps, can tell us what have you used and found useful, and we can start to prepare something in the lesson wiki with a list of video resources, since it sounds like some people are interested. Okay, so just like usual, we unfreeze our model, and then we fit some more, and we get down to 9 to 9-ish. So one thing to notice here is that before we unfreeze, you'll tend to get this shape pretty much all the time. If you do your learning rate finder before you unfreeze, it's pretty easy, find the steepest slope, not the bottom, right? Remember, we're trying to find the bit where we can like slide down it quickly. So if you start at the bottom, it's just going to send you straight off to the end here. So somewhere around here. And then we can call it again after you unfreeze. and you'll generally get a very different shape, right? And this is a little bit harder to say what to look for because it tends to be this kind of shape where you get a little bit of upward and then a kind of very gradual downward and then up here. So, you know, I tend to kind of look for just before it shoots up and go back about 10x, right, as a kind of a rule of thumb. So 1e neg 5, right? And that is what I do for the first half of my slice. And then for the second half of my slice, I normally do whatever learning rate I used for the frozen part, so LR, which was 0.01, kind of divided by 5, or divided by 10, somewhere around that. So that's kind of my rule of thumb, right? Look for the bit kind of at the bottom, find about 10x smaller. That's the number that I put here, and then LR over 5 or LR over 10 is kind of what I put there. Seems to work most of the time. We'll be talking more about exactly what's going on here. This is called discriminative learning rates as the course continues. So how am I going to get this better than 929? Because, you know, there are, how many people in this competition? About 1,000 teams, right? So we want to get into the top 10%. So the top 5% would be 0.931-ish. The top 10% is going to be about 929-ish. So we're not quite there, right? So here's the trick, right? I don't know if you remember, but when I created my data set, I put size equals 128. And actually the images that Calcle gave us are 256. So I used a size of 128 partially because I wanted to experiment quickly. It's much quicker and easier to use small images to experiment. But there's a second reason. I now have a model that's pretty good at recognizing the contents of 128 by 128 satellite images. So what am I going to do if I now want to create a model that's pretty good at 256 by 256 satellite images? Well, why don't I use transfer learning? Why don't I start with the model that's good at 128 by 128 images and fine-tune that? So don't start again, right? And that's actually going to be really interesting because if I'm trained quite a lot, if I'm on the verge of overfitting, which I don't want to do, right, then I'm basically creating a whole new data set, effectively, one where my images are twice the size on each axis, right, so 4 times bigger. So it's really a totally different data set as far as my convolutional neural network's concerned. So I kind of going to lose all that overfitting. I get to start again. So let's create a new learner, right? Well, I mean, let's keep our same learner, but use a new data bunch where the data bunch is 256 by 256. So that's why I actually stopped here, right, before I created my data sets. Because I'm going to now take this data source, and I'm going to create a new data bunch with 256 instead. So let's have a look at how we do that. So here it is. Take that source, right? Take that source, transform it with the same transforms as before, but this time use size 256. Right? Now that should be better anyway, because this is going to be, you know, higher resolution images. But also I'm going to start with, I haven't got rid of my learner. It's the same learner I had before. So I'm going to start with this kind of pre-trained model. And so I'm going to replace the data inside my learner with this new data bunch. And then I will freeze again. So that means I'm going back to just training the last few layers. And I will do a new LR find. And because I actually now have a pretty good model, like it was pretty good for 128 by 128, so it's probably going to be like at least okay for 256 by 256, I don't get that same sharp shape that I did before. But I can certainly see where it's way too high, right? So I'm going to pick something well before where it's way too high. Again, maybe 10x smaller. So here I'm going to go 1e neg 2 over 2. That's, you know, seems well before it shoots up. And so let's fit a little bit more. Okay, so we've frozen again. So we're just training the last few layers and fit a little bit more. And as you can see, I very quickly, remember kind of 928 was where we got to before after quite a few epochs. We're straight up there and suddenly we've passed 0.93. Right? So we're now already kind of into the top 10%. So we've hit our first goal, right? We're at the very least pretty competent at the problem of recognizing satellite imagery. But of course now, we can do the same thing before. We can unfreeze and train a little more. Okay, again, using the same kind of approach I described before, LR over 5 here, an even smaller one here, train a little bit more, 0.9314. So that's actually pretty good, 0.931. Somewhere around top 20-ish. So you can see actually when my friend Brendan and I entered this competition, we came 22nd with 0.9315, and we spent, this was a year or two ago, months trying to get here. So using kind of pretty much, you know, defaults with some minor tweaks and one trick, which is the resizing tweak, you can kind of get right up into the top of the leaderboard of this very challenging competition. Now, I should say, we don't really know where we'd be. We'd actually have to check it on the test set that Kaggle gave us and actually submit to the competition, which you can do. You can do a late submission. And so later on in the course, we'll learn how to do that. But we certainly know we're doing well. You know, we're doing very well. So that's great news. And so you can see also as I kind of go along, I tend to save things. You can name your models whatever you like, but I just want to basically know, you know, is it kind of before or after the unfreeze? So kind of had stage 1 or 2. What size was I training on? What architecture was I training on? So that way I can kind of always go back and experiment pretty easily. So that's Planet, multi-label classification. Let's look at another example. The other example next we're going to look at is this data set called Canvid, and it's going to be doing something called segmentation. We're going to start with a picture like this, and we're going to try and create a color-coded picture like this, where all of the bicycle pixels are the same color, all of the road line pixels are the same color, all of the tree pixels are the same color, all of the building pixels are the same color, the sky the same color, and so forth. Okay? Now, we're not actually going to make them colors. We're actually going to do it where each of those pixels has a unique number. So in this case, the top left is building, so I guess building is number 4. The top right is tree, so tree is 26, and so forth. All right? So in other words, this single top left pixel, we're basically, like imagine this, we're going to do a classification problem, just like the PETS classification, for the very top left pixel. We're going to say, what is that top left pixel? Is it bicycle, road lines, sidewalk, building? What is the very top left pixel? And then, what is the next pixel along? What is the next pixel along? So we're going to do a little classification problem for every single pixel in every single image. So that's called segmentation. Right? In order to build a segmentation model, you actually need to download or create a data set where someone has actually labeled every pixel. So as you can imagine, that's a lot of work. Okay, so this is so that's going to be a lot of work. You're probably not going to create your own segmentation data sets, but you're probably going to download or find them from somewhere else. This is very common in medicine, life sciences. You know, if you're looking through slides at nuclei, it's very likely you already have a whole bunch of segmented cells and segmented nuclei. If you're in radiology, you probably already have lots of examples of segmented lesions and so forth. So there's a lot of, kind of different domain areas where there are domain-specific tools for creating these segmented images. As you could guess from this example, it's also very common in kind of self-driving cars and stuff like that, where you need to see, what objects are around and where are they. So in this case, there's a nice data set called Canvid, which we can download, and they have already got a whole bunch of images and segment masks prepared for us, which is pretty cool. And remember, pretty much all of the data sets that we have provided kind of inbuilt URLs for, you can see their details at course.fast.ai/datasets. And nearly all of them are academic data sets where some very kind people have gone to all of this trouble for us so that we can use this data set and made it available for us to use. So if you do use it, one of these data sets for any kind of project, it would be very, very nice if you were to go and find the citation and say, you know, thanks to these people for this data set, okay? Because they've provided it, and all they're asking in return is for us to give them that credit. Okay, so here is the Canvid data set, here is the citation, and on our datasets page, that will link to the academic paper where it came from. Okay, Rachel, now is a good time for a question.
Is there a way to use learn.lr find and have it return a suggested number directly rather than having to plot it as a graph and then pick a learning rate by visually inspecting that graph? And then there are a few other questions, I think, around more guidance on reading the learning rate finder graph.
Yeah, I mean, that's a great question. I mean, the short answer is no. And the reason the answer is no is because this is still a bit more artisanal than I would like. You know, as you can kind of see, I've been kind of saying how I read this learning rate graph depends a bit on what stage I'm at and kind of what the shape of it is. I guess like when you're just training the head, so before you unfreeze, it pretty much always looks like this. And you could certainly create something that kind of creates a slightly, creates a smooth version of this, finds the sharpest negative slope and picked that. You would probably be fine nearly all the time. But then for, these kinds of ones, it requires a certain amount of experimentation. But the good news is you can experiment, right? You can try. Obviously, if the line's going up, you don't want it. Almost certainly at the very bottom point, you don't want it, right? Because you need it to be going downwards. But if you kind of start with somewhere around 10x smaller than that, and then also you could try another 10x smaller than that, try a few numbers, and find out which ones work best. And within a small number of weeks, you will find that you're picking the best learning rate most of the time. Right? So I don't know. It's kind of, so at this stage, it still requires a bit of playing around to get a sense of the different kinds of shapes that you see and how to respond to them. Maybe by the time this video comes out, someone will have a pretty reliable auto learning rate finder. We're not there yet. It's probably not a massively difficult job to do. Be an interesting project. Collect a whole bunch of different data sets, maybe grab all the data sets from our datasets page, try and come up with some simple heuristic, compare it to all the different lessons I've shown. That'd be a really fun project to do. But at the moment, we don't have that. I'm sure it's possible, but we haven't got there. Okay, so how do we do image segmentation? Same way we do everything else. And so basically, we're going to start with some path which has got some information in it of some sort. So I always start by, untiring my data, do an ls, see what I was given. In this case, there's a folder called labels and a folder called images. So I'll create paths for each of those. We'll take a look inside each of those. And, at this point, you can see there's some kind of coded file names for the images and some kind of coded file names for the segment masks. And then you kind of have to figure out how to map from one to the other. Normally these kind of data sets will come with a README you can look at, or you can look at their website. Often it's kind of obvious. In this case, I can see these ones always have this kind of particular format. These ones always have exactly the same format with an _p. So when I did this, honestly, I just guessed. I thought, oh, it's probably the same thing, _p. And so I created a little function that basically took the file name and added the _p and put it in the different place. and I tried opening it, and I noticed it worked. So, so I've created this little function that converts from the image file names to the equivalent label file names. I opened up that to make sure it works. Normally, we use OpenImage to open a file, and then you can go .show to take a look at it. But this, as we described, this is not a usual image file. It contains integers. So you have to use OpenMask rather than OpenImage because we want to return integers, not floats. And FastAI knows how to deal with masks. So if you go mask.show, it will automatically color code it for you in some appropriate way. That's why we said OpenMask. So, we can kind of have a look inside, look at the data, see what the size is. So there's 720 by 960. We can take a look at the data inside, and so forth. The other thing you might have noticed is that they gave us a file called codes.txt and a file called valid.txt. So codes.txt, we can load it up and have a look inside, and not surprisingly, it's got a list telling us that, for example, number 4 is 0, 1, 2, 3, 4. It's building. Top left is building. There you go. Okay? So just like we had, grizzlies, black bears, and teddies, here we've got the coding for what each one of these pixels means. So we need to create a data bunch. So to create a data bunch, we can go through the data block API and say, okay, we've got a list of image files that are in a folder. We need to create labels, which we can use with that get y file name function we just created. We then need to split into training and validation. In this case, I don't do it randomly. Why not? Because actually, the pictures they've given us are frames from videos. So if I did them randomly, I would be having like 2 frames next to each other, one in the validation set, one in the training set. That would be far too easy. That's treating, right? So the people that created this data set actually gave us a data set saying, here is the list of file names that are meant to be in your validation set. And they're non-contiguous parts of the video. So here's how you can split your validation and training using a file name file. So from that, I can create my data sets. And so I actually have a list of class names. So like often with stuff like the planet data set or the pets data set, we actually have a string saying, this is a pug, or this is a ragdoll, or this is a Burman, or this is cloudy, or whatever. In this case, you don't have every single pixel labeled with an entire string. That would be incredibly inefficient. They're each labeled with just a number, and then there's a separate file telling you what those numbers mean. So here's where we get to tell it in the data block API, this is the list of what the numbers mean. Okay, so these are the kind of parameters that the data block API gives you. Here's our transformations. And so here's an interesting point. Remember I told you that, for example, sometimes we randomly flip an image, right? What if we randomly flip the independent variable image, but we don't also randomly flip this one? They're now not matching anymore, right? So we need to tell FastAI that I want to transform the y. So x is our independent variable, y is our dependent. I want to transform the y as well. So whatever you do to the x, I also want you to do to the y. So there's all these little parameters that we can play with. And I can create a data bunch. I'm using a smaller batch size because, as you can imagine, because I'm creating a classifier for every pixel, that's going to take a lot more GPU. Right? So I found a batch size of 8 is all I could handle. And then normalize in the usual way. And this is quite nice. FastAI, because it knows that you've given it a segmentation problem, when you call show batch, it actually combines the 2 pieces for you and it will color code the photo. Isn't that nice? Right? So you can see here the green on the trees and the red on the lines and this kind of color on the walls and so forth. Right? So you can see here are the pedestrians. This is the pedestrian's backpack. So this is what the ground truth data looks like. So once we've got that, we can go ahead and create a learner. I'll show you some more details in a moment. Call LRFind, find the sharpest bit, which looks about 1A neg 2. Call fit, passing in slice LR, and see the accuracy, and save the model, and unfreeze, and train a little bit more. So that's the basic idea, okay? And so we're going to have a break, and when we come back, I'm going to show you some little tweaks that we can do, and I'm also going to explain this custom metric that we've created, and then we'll be able to go on and look at some other cool things. So let's all come back at 8 o'clock, 6 minutes. Okay, welcome back everybody, and we're going to start off with a question we got during the break.
Could you use unsupervised learning here, pixel classification with the bike example, to avoid needing a human to label a heap of images?
Well, not exactly unsupervised learning, but you can certainly get a sense of where things are without needing these kind of labels. And time permitting, we'll try and see some examples of how to do that. You're certainly not going to get such a quality and such a specific output as what you see here, though. If you want to get this level of segmentation mask, you need a pretty good segmentation mask ground truth to work with.
And is there a reason we shouldn't deliberately make a lot of smaller data sets to step up from in tuning, let's say 64 by 64, 128 by 128, 256 by 256, and so on?
Yes, you should totally do that. It works great. Try it. I've found this idea is something that I first came up with in the course a couple of years ago, and I kind of thought it seemed obvious and just presented it as a good idea, and then I later discovered that nobody had really published this before, and then we started experimenting with it, and it was basically the main trick that we used to win the ImageNet competition, the Dawnbench ImageNet training competition. And we're like, wow, this wasn't, not only was this not standard, nobody had heard of it before. There's been now a few papers that use this trick for various specific purposes, but it's still largely unknown. And it means that you can train much faster, it generalizes better. There's still a lot of unknowns about exactly like how small and how big and how much at each level and so forth. But I guess in as much as it has a name now, it probably does, and I guess we'd call it progressive resizing. I found that going much under 64 by 64 tends not to help very much. But yeah, it's a great technique, and I'd definitely try a few different sizes.
What does accuracy mean for pixel-wise segmentation? Is it correctly classified pixels divided by the total number of pixels?
Yep, that's it. So if you imagine each pixel was a separate, object you're classifying, it's exactly the same accuracy. And so you actually can just pass in accuracy as your metric. But in this case, we actually don't. We've created a new metric called accuracy CAMVID. And the reason for that is that when they labeled the images, sometimes they labeled a pixel as void. I'm not quite sure why. Maybe it was some that they didn't know, or somebody felt that they'd made a mistake, or whatever. But some of the pixels are void. And in the CAMVID paper, they say when you're reporting accuracy, you should remove the void pixels. So we've created an accuracy CAMVID. So all metrics take the actual output of the neural net, that's the input this is what they call the input, because it's the input to the metric, and the target, i.e. the labels you're trying to predict. So we then basically create a mask. So we look for the places where the target is not equal to void. And then we just take the input, do the argmax as per usual, just the standard accuracy argmax, but then we just grab those that are not equal to the void code. We do the same for the target, and we take the mean. Okay? So it's just a standard accuracy. It's almost exactly the same as the accuracy source code we saw before with the addition of this mask. So this quite often happens, that the particular Kaggle competition metric you're using, or the particular way your organization, scores things or whatever, there's often like little tweaks you have to do, and this is how easy it is, right? And so, as you'll see, to do this stuff, the main thing you need to know pretty well is how to do basic mathematical operations in PyTorch. So that's just something you kind of need to practice.
I've noticed that most of the examples and most of my models result in a training loss greater than the validation loss. What are the best ways to correct that? I should add that this still happens after trying many variations on number of epochs and learning rate.
Okay, good question. So remember from last week, if your training loss is higher than your validation loss, then you're underfitting. Okay, it definitely means that you're underfitting. You want your training loss to be lower than your validation loss. If you're underfitting, you can train for longer. You can train the last bit at a lower learning rate. But if you're still underfitting, then you're going to have to decrease regularization. And we haven't talked about that yet. So in the second half of this part of the course, we're going to be talking quite a lot about regularization and specifically how to avoid overfitting or underfitting by using regularization. If you want to skip ahead, we're going to be learning about weight decay, dropout, and data augmentation will be the key things that we'll be talking about. Okay. For segmentation, we don't just create a convolutional neural network. We can, but actually an architecture called UNet turns out to be better. And actually, let's find it. Okay, so this is what a UNet looks like, and this is from the university website where they talk about the UNet. And so we'll be learning about this both in this part of the course and in part 2 if you do it. But basically, this bit down on the left-hand side is what a normal convolutional neural network looks like. It's something which starts with a big image and gradually makes it smaller and smaller and smaller and smaller until eventually you just have one prediction. What a UNet does is it then takes that and makes it bigger and bigger and bigger again, and then it takes every stage of the downward path and kind of copies it across, and it creates this U-shape. It was originally actually created or published as a biomedical image segmentation method, but it turns out to be useful for far more than just biomedical image segmentation. So it was presented at MICI, which is the main medical imaging conference, and as of just yesterday, it actually just became the most cited paper of all time from that conference. So it's been incredibly useful, over 3,000 citations. You don't really need to know any of the details at this stage. All you need to know is if you want to create a segmentation model, you want to be saying learner.createUnit rather than create CNN. But you pass it the normal stuff. The data bunch, an architecture, and some metrics, okay? So having done that, everything else works the same. You can do the yellow finder, find the slope, train it for a while, watch the accuracy go up, save it from time to time, unfreeze, probably want to go about 10 less, so it's still going up, so probably 10 less than that. So 1e neg 5, comma, LR over 5, train a bit more, and there we go, right? Now, here's something interesting. You can, learn.recorder is where we keep track of what's going on during training, and that's got a number of nice methods, one of which is plot losses, and this plots your training loss and your validation loss. And you'll see quite often they actually go up a bit before they go down. Why is that? That's because you can also plot your learning rate over time, and you'll see that your learning rate goes up and then it goes down. Why is that? Because we said fit one cycle, and that's what fit one cycle does. It actually makes the learning rate start low, go up, and then go down again. Why is that a good idea? Well, to find out why that's a good idea, let's first of all look at a really cool project done by Jose Fernandez Portal during the week. He took our gradient descent demo notebook and actually plotted the weights over time, not just the ground truth and model over time. And he did it for a few different learning rates. And so remember, we had two weights. We were doing basically y equals ax plus b, or in his nomenclature here, y equals w naught x plus w1. And so we can actually look and see over time what happens to those weights. And we know this is the correct answer here, right? So at a learning rate of 0.1, it kind of like slides on in here, and you can see that it takes a little bit of time to get to the right point, and you can see the loss improving. At a higher learning rate of 0.7, you can see that the ground truth, the model jumps to the ground truth really quickly. And you can see that the weights jump straight to the right place really quickly. What if we have a learning rate that's really too high? You can see it takes a very, very, very long time to get to the right point. Or if it's really too high, it diverges. Okay, so you can see here why getting the right learning rate is important. When you get the right learning rate, it really zooms into the best spot very quickly. Now, as you get closer to the final spot, something interesting happens, which is that you really want your learning rate to decrease, right? Because you're getting close to the right spot, right? And what actually happens is, I can only draw 2D, sorry. You don't generally actually have some kind of loss function surface that looks like that. Remember, there's lots of dimensions, but it actually tends to kind of look like bumpy, like that, right? And so you kind of want a learning rate that's like high enough to jump over the bumps, right? But then once you get close to the middle, once you get close to the best answer, you don't want to be just jumping backwards and forwards between bumps. So you really want your learning rate to go down so that as you get closer, you take smaller and smaller steps. So that's why it is that we want our learning rate to go down at the end. Now, this idea of decreasing the learning rate during training has been around forever, and it's just called learning rate annealing. But the idea of gradually increasing it at the start is much more recent, and it mainly comes from a guy called Leslie Smith. And if you're in San Francisco next week, actually you can come and join me and Leslie Smith. We're having a meetup where we'll be talking about this stuff, so come along to that. What Leslie discovered is that if you gradually increase your learning rate, what tends to happen is that actually what tends to happen is that loss function surfaces tend to kind of look something like this. Bumpy, 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 flat, bumpy, 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 bumpy. Something like this, right? They have flat areas and bumpy areas. And if you end up in the bottom of a bumpy area, that solution will tend not to generalize very well because you found a solution it's good in that one place, but it's not very good in other places. Whereas if you found one in the flat area, it probably will generalize well because it's not only good in that one spot, but it's good kind of around it as well. If you have a really small learning rate, it'll tend to kind of plod down and stick in these places, right? But if you gradually increase the learning rate, then it'll kind of like jump down, and then as the learning rate goes up, it's going to start kind of going up again like this, right? and then the learning rate's now going to be up here. It's going to be bumping backwards and forwards, and eventually the learning rate starts to come down again, and so it'll tend to find its way to these flat areas. So it turns out that gradually increasing the learning rate is a really good way of helping the model to explore the whole function surface and try and find areas where both the loss is low and also it's not bumpy. Because if it was bumpy, it would get kicked out again. And so this allows us to train at really high learning rates, so it tends to mean that we solve our problem much more quickly and we tend to end up with much more generalizable solutions. So if you call plot losses and find that it's just getting a little bit worse and then it gets a lot better, you found a really good maximum learning rate. So when you actually call fit one cycle, you're not actually passing in a learning rate, you're actually passing in a maximum learning rate. And if it's kind of always going down, particularly after you unfreeze, that suggests you could probably bump your learning rates up a little bit because you really want to see this kind of shape. It's going to train faster and generalize better, just a little bit, right? And you'll tend to particularly see it in the validation set. The orange is the validation set, right? And again, the difference between kind of knowing the theory and being able to do it is looking at lots of these pictures, right? So like after you train stuff, type learn.recorder. And hit tab and see what's in there, right? And particularly the things that start with plot, and start getting a sense of like, what are these pictures looking like when you're getting good results? And then try making the learning rate much higher, try making it much lower, more epochs, less epochs, and get a sense of what these look like. So in this case, we used a size in our transforms of the original image size over 2. These 2 slashes in Python means integer divide, okay? Because obviously we can't have half pixel amounts in our sizes. So integer divided by 2. And we used a batch size of 8, and I found that fits on my GPU. It might not fit on yours. If it doesn't, you can just decrease the batch size down to 4. And this isn't really solving the problem, because the problem is to segment all of the pixels, not half of the pixels. So I'm going to use the same trick that I did last time, which is I'm now going to put the size up to the full size of the source images, which means I now have to halve my batch size, otherwise I run out of GPU memory. And I'm then going to set my learner. I can either say learn.data equals my new data, or I actually found I had a lot of trouble with kind of GPU memory, so I generally restarted my kernel, came back here, created a new learner, and loaded up the weights that I saved last time. But the key thing here being that this learner now has the same weights that I had here, but the data is now the full image size. So I can now do an LR find again, find an area where it's kind of, well before it goes up. So I'm going to use 1 in neg 3 and fit some more. And then unfreeze and fit some more. And you can go to learn.showResults to see how your predictions compare to the ground truth. And you've got to say, they really look pretty good. Not bad, huh? So how good is pretty good? An accuracy of 92.15. The best paper I know of for segmentation was a paper called the 100 Layers Tiramisu, which developed a convolutional dense net, came out about 2 years ago. So after I trained this today, I went back and looked at the paper to find their state-of-the-art accuracy. Here it is. And I looked it up, and their best was 91.5, and we got 92.1. So I got to say, when this happened today, I was like, wow. I don't know if better results have come out since this paper, but I remember when this paper came out, and it was a really big deal. I was like, wow, this is an exceptionally good segmentation result. Like when you compare it to the previous bests that they compared it to, it was a big step up. And so like in last year's course, we spent a lot of time in the course re-implementing the 100 layers tiramisu. And now, with our totally default fast AI class, I'm easily beating this. And I also remember this I had to train for hours and hours and hours, whereas today's I trained in minutes. So this is a super strong architecture for segmentation. So yeah, I'm not going to promise that this is the definite state of the art today because I haven't done a complete literature search to see what's happened in the last 2 years, but it's certainly beating the world's best approach the last time I looked into this, which was in last year's course, basically. And so these are kind of just all the little tricks, I guess, we've picked up along the way in terms of like how to train things well, things like using the pre-trained model and things like, you know, using the one-cycle convergence and all these little tricks. They work extraordinarily well. And it's really nice to be able to like show something in class where we can say, you know, we actually haven't published the paper on the exact details of how this variation of the UNet works. There's a few little tweaks we do. But if you come back for part 2, we'll be going into all of the details about how we make this work so well. But for you, all you have to know at this stage is that you can say learner.createUNet, and you should get great results also. There's another trick you can use if you're running out of memory a lot, which is you can actually do something called mixed precision training. And mixed precision training means that instead of using, for those of you that have done a little bit of computer science, instead of using single precision floating point numbers, you can do all most of the calculations in your model with half precision floating point numbers, so 16 bits instead of 32 bits. The very idea of this has only been around really for the last couple of years in terms of like hardware that actually does this reasonably quickly. And then FastAI library, I think, is the first and probably still the only that makes it actually easy to use this. If you add 2 FP16 on the end of any learner call, you're actually going to get a model that trains in 16-bit precision. Because it's so new, you'll need to have kind of the most recent CUDA drivers and all that stuff for this even to work. When I tried it this morning on some of the platforms, it just killed the kernel. So you need to make sure you've got the most recent drivers. But if you've got a really recent GPU, like a 2080 Ti, not only will it work, but it'll work about twice as fast as otherwise. Now, the reason I'm mentioning it is that it's going to use less GPU, RAM. So even if you don't have like a 2080 Ti, you might find, or you'll probably find that things that didn't fit into your GPU without this, then do fit in with this. Now, I actually have never seen people use 16 mixed precision floating point for segmentation before. Just for a bit of a laugh, I tried it and actually discovered that I got an even better result. So I only found this morning, so I don't have anything more to add here other than quite often when you make things a little bit less precise in deep learning, it generalizes a little bit better. And I've never seen a 92.5 accuracy on Canvid before. So yeah, not only will this be faster, you'll be able to use bigger batch sizes, but you might even find, like I did, that you get an even better result. So that's a cool little trick. You just need to make sure that every time you create a learner, you add this to FP16. If your kernel dies, it probably means you have slightly out-of-date CUDA drivers, or maybe even too old graphics card. I'm not sure exactly which cards support FP16. Okay, so one more before we kind of rewind. Sorry, 2 more. The first one I'm going to show you is an interesting data set called the BWE head pose data set. And Gabriele Finelli was kind enough to give us permission to use this in the class. His team created this cool data set. Here's what the data set looks like. It's pictures. It's actually got a few things in it. We're just going to do a simplified version. And one of the things they do is they have a dot saying this is the center of the face. And so we're going to try and create a model that can find the center of a face. So for this data set, there's a few data set specific things we have to do, which I don't really even understand, but I just know from the README that you have to. They used some kind of depth sensing camera. I think they actually used a Kinect, Xbox Kinect. There's some kind of calibration numbers that they provide in a little file, which I had to read in. And then they provided a little function that you have to use to take their coordinates to change it from this depth sensor calibration thing to end up with actual coordinates. So when you open this and you see these little conversion routines, that's just, I'm just doing what they told us to do, basically. It's got nothing particularly to do with deep learning to end up with this dot. The interesting bit really is where we create something which is not an image or an image segment, but an image points. And we'll mainly learn about this later in the course. But basically, image points use this idea of kind of their coordinates, right? They're not pixel values, they're x, y coordinates. There's just two numbers. As you can see, let me see. Okay. So here's an example for a particular image file name, this particular image file, and here it is. The coordinates of the center of the face are at 263, 428, and here it is. So there's just two numbers which represent whereabouts on this picture is the center of the face. So if we're going to create a model that can find the center of a face, we need a neural network that spits out two numbers. But note, this is not a classification model. These are not two numbers that you look up in a list to find out that they're road or building or ragdoll cat or whatever. They're actual locations. So, so far, everything we've done has been a classification model, something that's created labels or classes. This, for the first time, is what we'd call a regression model. A lot of people think regression means linear regression. It doesn't. Regression just means any kind of model where your output is some continuous number or set of numbers. So we need to create an image regression model, something that can predict these two numbers. So how do you do that? Same way as always, right? So we can actually just say, I've got a list of image files, it's in a folder, and I want to label them using this function that we wrote that basically does the stuff that the README says to grab the coordinates out of their text files. So that's going to give me the two numbers for every one. And then I'm going to split it according to some function. And so in this case, the files they gave us, again, they're from videos. And so I picked just one folder to be my validation set. In other words, a different person. So again, I was trying to think about, like, how do I validate this fairly? So I said, well, the fair validation would be to make sure that it works well on a person that it's never seen before. So my validation set is all going to be a particular person. Create a data set. And so this data set, I just tell it what kind of data set is it. Well, they're going to be a set of points. So points means, specific coordinates. Do some transforms. Again, I have to say transform y equals true because that red dot needs to move if I flip or rotate or warp, right? Pick some size. I just picked a size that's going to work pretty quickly. Create a data bunch, normalize it. And again, show batch. There it is, okay? I noticed that their red dots don't always seem to be quite in the middle of the face. I don't know exactly what their kind of internal algorithm for putting dots on. It kind of sometimes looks like it's meant to be the nose, but sometimes it's not quite the nose. Anyway, you get it's somewhere around the center of the face or the nose. So how do we create a model? We create a CNN. we're going to be learning a lot about loss functions in the next few lessons. But generally, basically the loss function is that number that says how good is the model. And so for classification, we use this loss function called cross-entropy loss, which says basically, you remember this from earlier lessons, did you predict the correct class, and were you confident of that prediction? Now, we can't use that for regression, so instead we use something called mean squared error. And if you remember from last lesson, we actually implemented mean squared error from scratch. It's just the difference between the two squared and added up together. Okay, so we need to tell it this is not classification, so we use mean squared error. Try all of these. So this is not classification, so we have to use mean squared error. And then once we've created the learner, we've told it what loss function to use, we can go ahead and do LR_find. We can then fit. And you can see here, within a minute and a half, our mean squared error is 0.0004. Now the nice thing is about like mean squared error, that's very easy to interpret, right? So we're trying to predict something which is somewhere around a few hundred, and we're getting a squared error on average of 0.0004, so we can feel pretty confident that this is a really good model, and then we can look at the results by learn.showResults, and we can see predictions, ground truth, it's doing a nearly perfect job. Okay, so that's how you can do image regression models. So anytime you've got something you're trying to predict, which is some continuous value, you use an approach that's something like this. So last example before we look at some kind of more foundational theory stuff, NLP. And next week we're going to be looking at a lot more NLP. But let's now do the same thing, but rather than creating a classification of pictures, let's try and classify documents. And so we're going to go through this in a lot more detail next week, but let's do the quick version. Rather than importing from fastai.vision, I now import for the first time from fastai.text. That's where you'll find all the application-specific stuff for analyzing text documents. And in this case, we're going to use a data set called IMDb. And IMDb has lots of movie reviews. They're generally about a couple of thousand words. And each movie review has been classified as either negative or positive. So it's just in a CSV file, so we can use pandas to read it. We can take a little look. We can take a look at a review. And basically, as per usual, we can either use factory methods or the data block API to create a data bunch. So here's the quick way to create a data bunch from a CSV of texts, data bunch from CSV, and that's that. And yeah, at this point, I could create a learner and start training it. But we're going to show you a little bit more detail, which we're mainly going to look at next week. The steps that actually happen when you create these data bunches is there's a few steps. The first is it does something called tokenization, which is it takes those words and it converts them into a standard form of tokens, where there's basically each token represents a word, but it does things like, see here, see how didn't has been turned here into two separate words? And you see how everything's been lowercased? See how your has been turned into two separate words? So tokenization is trying to make sure that each token, each thing that we've got with spaces around it here, represents a single, linguistic concept. Okay. Also, it finds words that are really rare, like really rare names and stuff like that, and replaces them with a special token called unknown. So anything starting with XX in FastAI is some special token. So this is tokenization. So we end up with something where we've got a list of tokenized words. You'll also see that things like punctuation end up with spaces around them to make sure that they're separate tokens. The next thing we do is we take a complete unique list of all of the possible tokens. That's called the vocab. and that gets created for us. And so here's the first 10 items of the vocab. So here is every possible token, the first 10 of them that appear in all of the movie reviews. And we then replace every movie review with a list of numbers. And the list of numbers simply says what numbered thing in the vocab is in this place. So here 6 is 0, 1, 2, 3, 4, 5, 6. So this is the word ah. And this is 3, 0, 1, 2, 3. This was a comma, and so forth. Right? So through tokenization and numericalization, this is the standard way in NLP of turning a document into a list of numbers. We can do that with the data block API, right? So this time it's not image files list, it's text, split data from a CSV, convert them to data sets, tokenize them, numericalize them, create a data bunch, and at that point, we can start to create a model. As we'll learn about next week, when we do NLP classification, we actually create two models. The first model is something called a language model, which, as you can see, we train in a kind of a usual way. We say we want to create a language model learner. We train it. We can save it. We unfreeze. We train some more. And then after we've created a language model, we fine-tune it to create the classifier. So here's the thing where we create the data bunch for the classifier. We create a learner. We train it. And we end up with some accuracy. So that's the really quick version. We're going to go through it in more detail next week. But you can see the basic idea of training an NLP classifier is very, very, very similar to creating every other model we've seen so far. And this accuracy, so the current state of the art for IMDb classification is actually the algorithm that we built and published with a colleague named Sebastian Ruder. And this basically, what I just showed you, is pretty much the state-of-the-art algorithm with some minor tweaks. You can get this up to about 95% if you try really hard. So this is very close to the state-of-the-art accuracy that we developed. There's a question. Okay, now's a great time for a question.
For a data set very different than ImageNet, like the satellite images or genomic images shown in Lesson 2, we should use our own stats. Jeremy once said, if you're using a pre-trained model, you need to use the same stats it was trained with. Why is that? Isn't it that normalized data with its own stats will have roughly the same distribution like ImageNet? The only thing I can think of which may differ is skewness. Is it the possibility of skewness or something else the reason of your statement? And does that mean you don't recommend using pre-trained models with very different data sets, like the 1-point mutation that you mentioned in Lesson 2?
No. As you can see, I've used pre-trained models for all of those things. Every time I've used an ImageNet pre-trained model, and every time I've used ImageNet stats. Why is that? Because that model was trained with those stats. Right? So for example, imagine you're trying to classify different types of green frogs. So if you were to use your own per channel means from your data set, you would end up converting them to a mean of 0, a standard deviation of 1 for each of your red, green, and blue channels, which means they don't look like green frogs anymore. They now look like gray frogs, right? But ImageNet expects frogs to be green. Okay, so you need to normalize with the same stats that the ImageNet training people normalized with, otherwise the unique characteristics of your data set won't appear anymore. You actually normalize them out in terms of the per channel statistics. So you should always use the same stats that the model was trained with. Okay, so in every case, what we're doing here is we're using gradient descent with mini batches, so stochastic gradient descent, to fit some parameters of a model. And those parameters are parameters to basically matrix multiplications. In the second half of this part, we're actually going to learn about a little tweak called convolutions, but it's basically a type of matrix multiplication. The thing is, though, no amount of matrix multiplications is possibly going to create something that can read IMDb movie reviews and decide if it's positive or negative, or look at satellite imagery and decide whether it's got a road in it. That's far more than a linear classifier can do. Now, we know these are deep neural networks, and deep neural networks contain lots of these matrix multiplications, but every matrix multiplication is just a linear model, and a linear function on top of a linear function is just another linear function. Right? If you remember back to your high school math, you might remember that if you have a y equals ax plus b, and then you stick another cy plus d on top of that, it's still just another slope and another intercept. So no amount of stacking matrix multiplications is going to help in the slightest. So what are these models actually? What are we actually doing? And here's the interesting thing. All we're actually doing is we literally do have a matrix multiplication or a slight variation like a convolution that we'll learn about. But after each one, we do something called a nonlinearity or an activation function. An activation function is something that takes the result of that matrix multiplication and sticks it through some function. And these are some of the functions that we use. In the old days, the most common function that we used to use was basically this shape. These shapes are called sigmoid. And they have, particular mathematical definitions. Nowadays, we almost never use those for these between each matrix multiply. Nowadays, we nearly always use this one. It's called a rectified linear unit. It's very important when you're doing deep learning to use big, long words that sound impressive. Otherwise, normal people might think they can do it too. But just between you and me, a rectified linear unit is defined using the following function. That's it. Okay, so, and if you want to be really exclusive, of course, you then shorten the long version and you call it a ReLU to show that you're really in the exclusive team. So this is a ReLU activation, right? So here's the crazy thing. If you take your red, green, blue pixel inputs and you chuck them through a matrix multiplication, and then you replace the negatives with 0, and you put it through another matrix multiplication, replace the negatives with 0, and you keep doing that again and again and again, you have a deep learning neural network. That's it, right? So how the hell does that work? So extremely cool guy called Michael Nielsen showed how this works. He has a very nice website. It's actually more than a website, it's a book. Neural Networks and deeplearning.com. And he has these beautiful little JavaScript things where you can get to play around, because this was back in the old days, this was back when we used to use sigmoids, right? And what he shows is that if you have enough he shows these little matrix multiplications. If you have enough little matrix multiplications followed by sigmoids, and exactly the same thing works for a matrix multiplication followed by a ReLU, you can actually create arbitrary shapes, right? And so this idea that these combinations of linear functions and nonlinearities can create arbitrary shapes actually has a name. And this name is the universal approximation theorem. And what it says is that if you have stacks of linear functions and nonlinearities, the thing you end up with can approximate any function arbitrarily closely. So you just need to make sure that you have a big enough matrix to multiply by or enough of them. So if you have, now this function, which is just a sequence of matrix multipliers and nonlinearities, where the nonlinearities can be, basically any of these things. We normally use this one. if that can approximate anything, then all you need is some way to find the particular values of the weight matrices in your matrix multiplies that solve the problem you want to solve. And we already know how to find the values of parameters. We can use gradient descent. And so that's actually it, right? And this is the bit I find the hardest thing normally to explain to students, is that we're actually done now. People often come up to me after this lesson and they say, what's the rest? Please explain to me the rest of deep learning. But like, no, there's no rest. Like, we have a function where we take our input pixels or whatever, we multiply them by some weight matrix, we replace the negatives with zeros, we multiply it by another weight matrix, replace the negatives with zeros, we do that a few times, we see how close it is to our target, and then we use gradient descent to update our weight matrices using the derivatives, and we do that a few times, and eventually we end up with something that can classify movie reviews, or can recognize pictures of ragdoll cats. That's actually it. Okay, so it's the reason it's hard to understand intuitively is because we're talking about weight matrices that have, once you add them all up, something like 100 million parameters. They're very big weight matrices, right? So your intuition about what multiplying something by a linear model and replacing the negatives with zeros a bunch of times can do, your intuition doesn't hold, right? You just have to accept empirically the truth is doing that works really well. So in part 2 of the course, we're actually going to build these from scratch, right? But I mean, just to skip ahead, you basically will find that, it's going to be kind of 5 lines of code, right? It's going to be a little for loop that goes, t equals, x at weight matrix 1, t2 equals max of t comma 0, stick that in a for loop that goes through each weight matrix, and at the end, calculate my loss function. And of course, we're not going to calculate the gradients ourselves because PyTorch does that for us. And that's about it. So, okay, question.
There's a question about tokenization. I'm curious about how tokenizing words works when they depend on each other, such as San Francisco.
Yeah, okay. Okay, tokenization. How do you tokenize something like San Francisco? San Francisco contains 2 tokens, San Francisco. That's it. That's how you tokenize San Francisco. The question may be coming from people who have done like traditional NLP, often need to kind of use these things called n-grams. And n-grams are kind of this idea of like a lot of NLP in the old days was all built on top of linear models, where you basically counted how many times particular strings of text appeared, like the phrase San Francisco. That would be a bigram, or an n-gram with an n of 2. The cool thing is that with deep learning, we don't have to worry about that. Like with many things, a lot of the complex feature engineering disappears when you do deep learning. So with deep learning, each token is literally just a word, or in the case that the word really consists of 2 words, like your, you split it into 2 words. And then what we're going to do is we're going to then let the deep learning model figure out how best to combine words together. Now, when we say, like, let the deep learning model figure it out, of course, all we really mean is find the weight matrices using gradient descent that give the right answer. Like, there's not really much more to it than that. Again, there's some minor tweaks, right? In the second half of the course, we're going to be learning about the particular tweak for image models, which is using a convolution. That'll be a CNN. For language, there's a particular tweak we do called using recurrent models, or an RNN, but they're very minor tweaks on what we've just described. So basically, it turns out with an RNN that it can learn that San plus Francisco has a different meaning when those two things are together.
Some satellite images have 4 channels. How can we deal with data that has 4 channels or 2 channels when using pre-trained models?
Yeah, that's a good question. I think that's something that we're going to try and incorporate into FastAI. So hopefully by the time you watch this video, there will be easier ways to do this. But the basic idea is a pre-trained ImageNet model expects red, green, and blue pixels. So if you've only got 2 channels, there's a few things you can do. But basically, you'll want to create a 3rd channel. And so you can create the 3rd channel as either being all zeros, or it could be the average of the other 2 channels. And so you can just use, normal PyTorch arithmetic to create that 3rd channel. You could either do that ahead of time in a little loop and save your 3-channel versions, or you could create a custom dataset class that does that on demand. For 4-channel, you probably don't want to get rid of the 4th channel. So instead, what you'd have to do is to actually modify the model itself. So to know how to do that, we'll only know how to do that in a couple more lessons' time. But basically, the idea is that the initial weight matrix, weight matrix is really the wrong term. They're not weight matrices, they're weight tensors. So they can have more than just 2 dimensions. So that initial weight matrix in the neural net, it's actually a tensor, and one of its axes is going to have 3 slices in it. So you would just have to change that to add an extra slice, which I would generally just initialize to 0 or to some random numbers. So that's the short version. But really, to answer this, to understand exactly what I meant by that, we're going to need a couple more lessons to get there. Okay, so wrapping up, what have we looked at today? Basically, we started out by saying, hey, it's really easy now to create web apps. We've got starter kits for you that show you how to create web apps, and people have created some really cool web apps using what we've learned so far, which is single label classification. But the cool thing is, the exact same steps we use to do single label classification, you can also do to do multi-label classification, such as in the planet, or you could use to do segmentation, or you could use to do any kind of image regression, or, this is probably a bit early for you to actually try this yet, you could do for NLP classification and a lot more. So, and in each case, all we're actually doing is we're doing gradient descent on not just 2 parameters, but on maybe 100 million parameters, but it's still just plain gradient descent, along with a nonlinearity, which is normally this one, which it turns out the universal approximation theorem tells us, lets us arbitrarily accurately approximate any given function, including functions such as converting a spoken waveform into the thing the person was saying, or converting a sentence in Japanese to a sentence in English, or converting a picture of a dog into the word dog. These are all mathematical functions that we can learn using this approach. So this week, see if you can come up with an interesting idea of a problem that you would like to solve, which is either multi-label classification, or image regression, or image segmentation, something like that, and see if you can try to solve that problem. You will probably find the hardest part of solving that problem is creating the data bunch, and so then you'll need to dig into the data block API to try to figure out how to create the data bunch from the data you have. And with some practice, you will start to get pretty good at that. It's not a huge API. There's a small number of pieces. It's also very easy to add your own. But for now, you know, ask on the forum if you try something and you get stuck. Okay, great. So next week, we're going to come back and we're going to look at some more NLP. We're going to learn some more about some details about how we actually train with SGD quickly. We're going to learn about things like Atom and RMS prop and so forth. And hopefully, we're also going to show off lots of really cool web apps and models that you've all built during the week. So I'll see you then. Thanks. Okay, welcome to lesson 4. We are going to finish our journey through these kind of key applications. We've already looked at a range of vision applications. We've looked at classification, localization, image regression. We've briefly touched on NLP. We're going to do a deeper dive into NLP transfer learning today. We're going to then look at tabular data, and we're going to look at collaborative filtering, which are both super useful applications. And then we're going to take a complete U-turn. We're going to take that collaborative filtering example and dive deeply into it to understand exactly what's happening mathematically, exactly what's happening in the computer. And we're going to use that to gradually go back in reverse order through the applications again in order to understand exactly what's going on behind the scenes of all of those applications. Before we do, somebody on the forum was kind enough to point out that when we compared ourselves to the what we think might be the state of the art, or was recently the state of the art for Canvid, it wasn't a fair comparison because the paper actually used a small subset of the classes, and we used all of the classes. So Jason in our study group was kind enough to rerun the experiments with the correct subset of classes from the paper, and our accuracy went up to 94% compared to 91.5% in the paper. So I think that's a really cool result and a great example of how some pretty much just using the defaults nowadays can get you far beyond what was the best of a year or two ago. It's certainly the best last year when we were doing this course, because we studied it quite intensely. So that's really exciting. So what I wanted to start with is going back over NLP a little bit to understand really what was going on there. So first of all, a quick review. So remember, NLP is natural language processing. It's about taking text and doing something with it. And text classification is a particularly useful, kind of practically useful applications. That's what we're going to start off focusing on. Because classifying a text, classifying a document can be used for anything from spam prevention to identifying fake news, to finding a diagnosis for medical reports, finding mentions of your product in Twitter, so on and so forth. So it's pretty interesting. And actually there was a great example. There was a great example during the week from one of our students who is a lawyer. And he mentioned on the forum that he had really great results from classifying legal texts using this NLP approach. And I thought this was a great example. So this is the poster that they presented at an academic conference this week describing the approach. And actually this series of 3 steps that you see here, and I'm sure you recognize this classification matrix, this series of 3 steps here is what we're going to start by digging into. So we're going to start out with a movie review like this one, and going to decide whether it's positive or negative sentiment about the movie. But here's the problem. We have in the training set 25,000 movie reviews. So we've got 25,000 movie reviews, and for each one we have like one bit of information. They liked it or they didn't like it. And as we're going to look into in a lot more detail today and in the current lessons, our neural networks, remember they're just a bunch of matrix multiplies and simple nonlinearities, particularly replacing negatives with zeros. Those weight matrices start out random. And so if you start out with some random parameters and try to train those parameters to learn how to recognize positive versus negative movie reviews, you only have literally 25,000 ones and zeros to actually tell you, I like this one, I don't like that one. That's clearly not enough information to learn basically how to speak English well enough to recognize they liked this or they didn't like this. And sometimes that can be pretty nuanced, right? The English language, often particularly with like movie reviews, people, because these are like online movie reviews on IMDb, people can often like use sarcasm. It can be really quite tricky. So for a long time, until very recently, like this year, neural nets didn't do a good job at all of this kind of classification problem. And that was why. There's not enough information available. So the trick, hopefully you can all guess, it's to use transfer learning. It's always the trick. So last year in this course, I tried something crazy, which was I thought, what if I try transfer learning to demonstrate that it can work for an NLP as well? And I tried it out, and it worked extraordinarily well. And so here we are a year later, and transfer learning in NLP is absolutely the hit thing now. And so I'm going to describe to you what happens. The key thing is we're going to start with the same kind of thing that we used for computer vision, a pre-trained model that's been trained to do something different to what we're doing with it. And so for ImageNet, that was originally built as a model to predict which of 1,000 categories each photo falls into, and people then fine-tuned that for all kinds of different things, as we've seen. So we're going to start with a pre-trained model that's going to do something else, not movie review classification. We're going to start with a pre-trained model which is called a language model. A language model is has a very specific meaning in NLP, and it's this. A language model is a model that learns to predict the next word of a sentence. Right? And to predict the next word of a sentence, you actually have to know quite a lot about English, assuming you're doing it in English, and quite a lot of world knowledge. And by world knowledge, I'll give you an example. Here's your language model, and it's read, I'd like to eat a hot what? Obviously, dog, right? It was a hot what? Probably day, right? Now, previous approaches to NLP use something called n-grams largely, which is basically saying how often do these pairs or triplets of words tend to appear next to each other. And n-grams are terrible at this kind of thing. As you can see, there's not enough information here to decide what the next word probably is. But with a neural net, you absolutely can. So here's the nice thing. If you train a neural net to predict the next word of a sentence, then you actually have a lot of information. Rather than having a single bit for every 2,000 word movie review, liked it or didn't like it, every single word you can try and predict the next word. So in a 2,000 word movie review, there are 1,999 opportunities to predict the next word. Better still, you don't just have to look at movie reviews. Because really the hard thing isn't so much does this person like the movie or not, but how do you speak English? Right? So you can learn how do you speak English, roughly, from some much bigger set of documents. And so what we did was we started with Wikipedia. And Stephen Merity and some of his colleagues built something called the Wikitext 103 dataset, which is simply a subset of most of the largest articles from Wikipedia, with a little bit of pre-processing that's available for download. And so you're basically grabbing Wikipedia, and then I built a language model on all of Wikipedia. Right? So I just built a neural net which would predict the next word in every significantly sized Wikipedia article. And that's a lot of information. If I remember correctly, it's something like 1 billion tokens. Right? So we've got 1 billion separate things to predict. Every time we make a mistake on one of those predictions, we get the loss we get gradients from that, and we can update our weights and make them better and better until we can get pretty good at predicting the next word of Wikipedia. Why is that useful? Because at that point, I've got a model that knows probably how to complete sentences like this, and so it knows quite a lot about English and quite a lot about how the world works, what kinds of things tend to be hot in different situations, for instance. I mean, ideally it would learn things like, in 1996, in a speech to the United Nations, United States President blah said. Now that would be a really good language model because it would actually have to know who was the United States President in that year. So like getting really good at training language models is a great way to learn a lot about, or teach a neural net a lot about, what is our world? What's in our world? How do things work in our world? So it's a really fascinating topic. And it's actually one that philosophers have been studying for hundreds of years now. There's actually a whole theory of philosophy which is about like what can be learned from studying language alone. So it turns out, empirically, quite a lot. And so here's the interesting thing. You can start by training a language model on all of Wikipedia, and then we can make that available to all of you. Just like a pre-trained ImageNet model for vision, we've now made available a pre-trained Wikitext model for NLP. Not because it's particularly useful of itself. Predicting the next word of sentences is somewhat useful, but not normally what we want to do. But it tells us it's a model that understands a lot about language and a lot about what language describes. So then we can take that and we can do transfer learning to create a new language model that's specifically good at predicting the next word of movie reviews. So if we can build a language model that's good at predicting the next word of movie reviews, pre-trained with the Wikitext model, right, then that's going to understand a lot about my favorite actor is Tom who, right? Or, I thought the photography was fantastic, but I wasn't really so happy about the director, whatever, right? It's going to learn a lot about specifically how movie reviews are written. It'll even learn things like what are the names of some popular movies. So that would then mean we can still use a huge corpus of lots of movie reviews, even if we don't know whether they're positive or negative, right, to learn a lot about how movie reviews are written. So for all of this pre-training and all of this language model fine-tuning, we don't need any labels at all. It's what the researcher Jan LeCun calls self-supervised learning. In other words, it's a classic supervised model. We have labels, right? But the labels are not things that somebody else have created. They're kind of built into the data set itself. So this is really, really neat. Because at this point, we've now got something that's good at understanding movie reviews, and we can fine-tune that with transfer learning to do the thing we want to do, which in this case is to classify movie reviews to be positive or negative. And so my hope was, when I tried this last year, that at that point, 25,000 ones and zeros would be enough feedback to fine-tune that model. And it turned out it absolutely was. All right, Rachel, let's go with a question.
Does the language model approach work for text in forums that are informal English, misspelled words, or slang or short form like S6 instead of Samsung S6?
Yes, absolutely it does. Particularly if you start with your Wikitext model and then fine-tune it with your, we call it a target corpus, right? So a corpus is just a bunch of documents, right? It could be emails or tweets or medical reports or whatever. So you could fine-tune it so it can learn a bit about the specifics of the slang, or abbreviations or whatever that didn't appear in the full corpus. And so interestingly, this is one of the big things that people were surprised about when we did this research last year. People thought that learning from something like Wikipedia wouldn't be that helpful because it's not that representative of how people tend to write. But it turns out it's extremely helpful because there's a much bigger difference between Wikipedia and random words than there is between like Wikipedia and Reddit, say. So it kind of gets you 99% of the way there. So these language models themselves can be quite powerful. So for example, there was a blog post from, what are they called? SwiftKey? SwiftType? SwiftKey. The folks that do the mobile phone predictive text keyboard, and they described how they kind of rewrote their underlying model to use neural nets. So, and now, this was a year or two ago, now most phone keyboards seem to do this. You'll be typing away on your mobile phone, and in the predictions, there'll be something telling you what word you might want next. So that's a language model in your phone. Another example was the researcher Andre Karpathy, who's now runs all this stuff at Tesla. Back when he was a PhD student, he created a language model of text in LaTeX documents, and created these automatic generation of LaTeX documents that then became these kind of automatically generated papers. That's pretty cute. So we're not really that interested in the output of the language model ourselves. We're just interested in it because it's helpful for this process. So we briefly looked at the process last week. So let's just have a reminder. Right? The basic process is we're going to start with the data in some format. So for example, we've prepared a little IMDb sample that you can use where it's in CSV file. So you can read it in with pandas and see there's negative or positive, the text of each movie review, and Boolean of is it in the validation set or the training set. So there's an example of a movie review. And so you can just go text data bunch from CSV to grab a language model specific data bunch, and then you can create a learner from that in the usual way and fit it. You can save the data bunch, which means that the pre-processing that is done, you don't have to do it again, you can just load it. So what goes on behind the scenes? Well, what happens behind the scenes if we now load it as a classification data bunch, that's going to allow us to see the labels as well. Then, as we described, it basically creates a separate unit. We call it a token for each separate part of a word. So most of them are just 4 words, but sometimes if it's like an apostrophe S from its, it'll get its own token. Every bit of punctuation tends to get its own token, like a comma or a full stop, and so forth. And then the next thing that we do is numericalization, which is where we find what are all of the unique tokens that appear here, and we create a big list of them. Here's the first 10 in order of frequency, and that big list of unique possible tokens is called the vocabulary, or we just call it vocab. And so what we then do is we replace the tokens with the ID of where is that token in the vocab. Okay, and that's numericalization. Here's the thing though, as you'll learn, every word in our vocab is going to require a separate row in a weight matrix in our neural net. And so to avoid that weight matrix getting too huge, we restrict the vocab to no more than, by default, 60,000 words. And if a word doesn't appear more than 2 times, we don't put it in the vocab either. So we kind of keep the vocab to a reasonable size in that way. And so when you see these XX unc, that's an unknown token. So when you see those unknown tokens, it just means this was something that was not a common enough word to appear in our vocab. Okay, so there is the numericalized version. We also have a couple of other special tokens like XX field. This is a special thing where if you've got like title, summary, abstract, body, like separate parts of a document, each one will get a separate field, so they all get numbered. Also, you'll find if there's something in all caps, it gets lowercased and a token called XX cap will get added to it. Personally, I more often use the data block API because you get, there's less to remember about exactly what data bunch to use and what parameters and so forth, and it can be a bit more flexible. So another approach to doing this is to just decide what kind of list you're creating. So what's your independent variable? So in this case, my independent variable is text. What is it coming from? A CSV. How do you want to split it into validation versus training? So in this case, column number 2 was the is validation flag. How do you want to label it with positive or negative sentiment, for example? So column 0 had that, and then turn that into a data bunch. That's going to do the same thing. Okay, so now let's grab the whole data set, which has 25,000 reviews in training, 25,000 reviews in validation, and then 50,000 what they call unsupervised movie reviews. So 50,000 movie reviews that haven't been scored at all. So there it is, positive, negative, unsupervised. So we're going to start, as we described, with the language model. Now the good news is we don't have to train the Wikitext 103 language model. Not that it's difficult, you can use exactly the same steps that you see here, just download the Wikitext 103 corpus and run the same code. But it takes 2 or 3 days on a decent GPU, so not much point you doing it. You may as well start with hours. Even if you've got a big corpus of like medical documents or legal documents, you should still start with Wikitext 103. Like there's just no reason to start with random weights. It's always good to use transfer learning if you can. So we're going to start then at this point, which is fine-tuning our IMDb language model. So we can say, okay, it's a list of text files, and the full IMDb actually is not in a CSV. Each document is a separate text file. So that's why we use a different constructor for our independent variable, text files list, say where it is. And in this case, we have to make sure we just don't include the train and test folders. And we randomly split it by 0.1. Now this is interesting, 10%. Why are we randomly splitting it by 10% rather than using the predefined train and test they gave us? This is one of the cool things about transfer learning. Even though our test set or our validation set has to be held aside, it's actually only the labels that we have to keep aside. So we're not allowed to use the labels in the test set. So if you think about something like a Kaggle competition, you certainly can't use the labels because they don't even give them to you. But you can certainly use the independent variables. So in this case, you could absolutely use the text that is in the test set to train your language model. So this is a good trick, right? Is actually when you do the language model, concatenate the training and test set together, and then just split out a smaller validation set. So you've got more data to train your language model. So that's a little trick. And so if you're doing NLP stuff on Kaggle, for example, or you've just got a smaller subset of labeled data, make sure that you use all of the text you have to train your language model, because there's no reason not to. How are we going to label it? Well, remember, a language model kind of has its own labels. So the text itself is the label, so label for language model does that for us. And create a data bunch and save it, and that takes a few minutes to tokenize and numericalize. So since that takes a few minutes, we save it. Later on, you can just load it. No need to run that again. So here's what it looks like. And at this point, things are going to look very familiar. We create a learner. But instead of creating a CNN learner, we're going to create a language model learner. So behind the scenes, this is actually not going to create a CNN, a convolutional neural network. It's going to create an RNN, a recurrent neural network. So we're going to be learning exactly how they're built over the coming lessons. But in short, they're the same basic structure. The input goes into a weight matrix, a matrix multiply, that then you replace the negatives with zeros, and it goes into another matrix multiply, and so forth a bunch of times. So it's the same basic structure. As usual, when we create a learner, you have to pass in two things, the data. So here's our language model data. In this case, what pre-trained model we want to use. And so here, the pre-trained model is the Wikitext 103 model. That will be downloaded for you from FastAI if you haven't used it before, just like the same thing with things like ImageNet pre-trained models are downloaded for you. This here sets the amount of dropout. We haven't talked about that yet. We've talked briefly about this idea that there's something called regularization, and you can reduce the regularization to avoid underfitting. So for now, just know that by using a number lower than 1 is because when I first tried to run this, I was underfitting And so if you reduce that number, then it will avoid underfitting. Okay, so we've got a learner, we can LR find, looks pretty standard. And so then we can fit one cycle. And so what's happening here is we are just fine-tuning the last layers. So normally after we fine-tuned the last layers, the next thing we do is we go unfreeze and train the whole thing. And so here it is. Unfreeze and train the whole thing. And as you can see, even on a pretty beefy GPU, that takes 2 or 3 hours. And in fact, I'm still underfitting. Right? So I'd probably tonight I might train it overnight and try and do a little bit better. Right? Because you can see, well, I guess I'm not underfitting. I'm guessing I could probably train this a bit longer because you can see the accuracy hasn't started going down again. Right? So I wouldn't mind trying to train that a bit longer. But the accuracy, it's interesting. 0.3 means, you know, we're guessing the next word of the movie review correctly about 1/3 of the time. So that sounds like a pretty high number, the idea that you can actually guess the next word that often. So that's a good sign that my language model is doing pretty well. For kind of more limited domain documents like medical transcripts and legal transcripts, you'll often find this accuracy gets a lot higher. So sometimes this can be even 50% or more. But anything, you know, 0.3 or more is pretty good. So you can now run learn.predict and pass in the start of a sentence, and it will try and finish off that sentence for you. Now, I should mention, this is not designed to be a good text generation system. This is really more designed to kind of check that it seems to be creating something that's vaguely sensible. There's a lot of tricks that you can use to generate much higher quality text, none of which we're using here, right? But you can kind of see that it's you know, certainly not random words that it's generating. It sounds vaguely English-like, even though it doesn't make any sense. So at this point, we have a movie review model. So now we're going to save that in order to load it into our classifier to be our pre-trained model for the classifier. But I actually don't want to save the whole thing. A lot of this, you know, kind of the second half, as we'll learn, the second half of the language model is all about predicting the next word rather than about understanding the sentence so far. So the bit which is specifically about understanding the sentence so far is called the encoder. So I just saved that. Right? So, and again, we're going to learn the details of this over the coming weeks. We're just going to save the encoder, so the bit that understands the sentence rather than the bit that generates the word. So now we're ready to create our classifier. So step one, as per usual, is to create a data bunch. And we're going to do basically exactly the same thing, bring it in, okay? And here's our path. But we want to make sure that it uses exactly the same vocab that it used for the language model. If word number 10 was the in the language model, we need to make sure that word number 10 is the in the classifier, because otherwise the pre-trained model is going to be totally meaningless. So that's why we pass in the vocab from the language model to make sure that this data bunch is going to have exactly the same vocab. So that's an important step. Split by folder, and this time label. So remember the last time we had split randomly, okay, but this time we need to make sure that the labels of the test set are not touched. So we split by folder. And then this time we label it not for a language model, but we label these classes. And then finally create a data bunch. And remember, sometimes you'll find that you run out of GPU memory. This will very often happen to you if you... So I was running this on an 11 gig machine, so you should make sure this number's a bit lower if you run out of memory. You may also want to make sure you restart the notebook and kind of start it just from here. So batch size 50 is as high as I could get on an 11 gig card. If you're using a P2 or P3 on Amazon, or the K80 on Google, for example, I think you'll get 16 gig, so you might be able to make this a bit higher, get it up to 64. So you can find whatever batch size fits on your card. So here's our data bunch, as we saw before, and the labels. So this time, rather than creating a language model learner, we're creating a text classifier learner. But again, same thing, pass in the data that we want, figure out how much regularization we need. Again, if you're overfitting, then you can increase this number. If you're underfitting, you can decrease the number. And most importantly, load in our pre-trained model. And remember specifically, it's this half of the model called the encoder, which is the bit that we want to load in. And freeze. LR find the learning rate, and fit for a little bit. And we're already up nearly to 92% accuracy after less than 3 minutes of training. So this is a nice thing. In your particular domain, whether it be law or medicine or journalism or government or whatever, you probably only need to train your domain's language model once, and that might take, overnight to train well. But once you've got it, you can now very quickly create all kinds of different classifiers and models with that. In this case, already a pretty good model after 3 minutes, right? So when you first start doing this, you might find it it's like annoying that your first models take 4 hours more to create that language model. But the key thing to remember is you only have to do that once for your entire kind of domain of stuff that you're interested in. And then you can build lots of different classifiers and other models on top of that in a few minutes. Okay? Right, so we can save that to make sure we don't have to run it again. And then here's something interesting. I'm going to explain this more in just a few minutes. I'm not going to say unfreeze. Instead, I'm going to say freeze to. And what that says is unfreeze the last 2 layers. Don't unfreeze the whole thing. And so we've just found it really helps with these text classification, not to unfreeze the whole thing, but to unfreeze 1 layer at a time. So unfreeze the last 2 layers, train it a little bit more, unfreeze the next layer again, train it a little bit more, unfreeze the whole thing, train it a little bit more. You'll also see I'm passing in this thing, momentums equals 0.8, 0.7. We're going to learn exactly what that means in the next week or two, probably next week. But for now, and we may even automate it, so maybe by the time you watch the video of this won't even be necessary anymore. But basically, we found for training recurrent neural networks, RNNs, it really helps to decrease the momentum a little bit. So that's what that is. So that gets us a 94.4 accuracy after about half an hour or less of training, actually quite a lot less, of training the actual classifier. We can actually get this quite a bit better with a few tricks. I don't know if we'll learn all the tricks this part, it might be next part, but even this very simple kind of standard approach is pretty great. If we compare it to last year's state-of-the-art on IMDb, this is from the Cove paper from McCann et al. At Salesforce Research. Their paper was 91.8% accurate. In the best paper they could find, they found a fairly domain-specific sentiment analysis paper from 2017 that got 94.1. And here we've got 94.4. And the best models I've been able to build since have been about 95, 95.1. So if you're looking to do text classification, this really standardized transfer learning approach works super well. Any questions, Rachel? Okay, so that was NLP, and we'll be learning more about NLP later in this course. But now I wanted to switch over and look at tabular. Now, tabular data is pretty interesting because it's the stuff that, for a lot of you, is actually what you use day to day at work, in spreadsheets, in relational databases. Just come close, I guess.
All right, so where does the magic number of 2.6 to the 4th in the learning rate come from?
Yeah, good question. So the learning rate is various things divided by 2.6 to the 4th. The reason it's to the 4th, you will learn about at the end of today. So let's focus on the 2.6. Why 2.6? Basically, this, as we're going to see in more detail later today, this number, the difference between the bottom of the slice and the top of the slice is basically what's the difference between how quickly the lowest layer of the model learns versus the highest layer of the model learns. So this is called discriminative learning rates. And so really the question is, like, as you go from layer to layer, how much do I decrease the learning rate by? And we found out that for NLP RNNs, that the answer is 2.6. How did we find out that it's 2.6? I ran lots and lots of different models, like a year ago or so, using lots of different sets of hyperparameters of various types, dropout, learning rates, and discriminative learning rate, and so forth. And then I created something called a random forest, which is a kind of model where I attempted to predict how accurate my NLP classifier would be based on the hyperparameters. And then I used random forest interpretation methods to basically figure out what the optimal parameter settings were. And I found out that the answer for this number was 2.6. So that's actually not something I've published, or I don't think I've even talked about it before. So there's a new piece of information. You can actually, a few months after I did this, I think Stephen Merity and somebody else did publish a paper describing a similar approach, so the basic idea may be out there already. Some of that idea comes from a researcher named Frank Hatter and one of his collaborators. They did some interesting work showing how you can use random forests to actually find optimal hyperparameters. So it's kind of a neat trick. A lot of people are very interested in this thing called AutoML, which is this idea of like building models to figure out how to train your model. We're not big fans of it on the whole, but we do find that building models to better understand how your hyperparameters work and then finding like those rules of thumb, like, oh, basically it can always be 2.6, quite helpful. So that's just something we're kind of been playing with. Okay, so so let's talk about tabular data. So tabular data, such as you might see in a spreadsheet or a relational database, or a financial report, it can contain all kinds of different things. And I kind of tried to make a little list of some of the kinds of things that I've seen tabular data analysis used for. Using neural nets for analyzing tabular data is, or at least last year when I first presented this, maybe we started this 2 years ago. Anyway, when we first presented this, people were deeply skeptical and they thought it was a terrible idea to use neural nets to analyze tabular data, because like everybody knows that you should use logistic regression or random forests or gradient boosting machines, all of which have their place for certain types of things. But since that time, it's become clear that the commonly held wisdom is wrong. It's not true that neural nets are not useful for tabular data. In fact, they're extremely useful. And we've shown this in quite a few of our courses. But what's really kind of also helped is that some really effective organizations have started publishing papers and posts and stuff describing how they've been using neural nets for analyzing tabular data. One of the key things that comes up again and again is that although feature engineering doesn't go away, it certainly becomes simpler. Right? So Pinterest, for example, replaced the gradient boosting machines that they were using to decide how to put stuff on their homepage with neural nets. And they presented at a conference this approach, and they described how it really made engineering a lot easier because a lot of the hand-created features weren't necessary anymore. You still need some, but it was just simpler. Right? So they ended up with something that was more accurate, but perhaps even more importantly, it required less maintenance. Right? So I wouldn't say it's the only tool that you need in your toolbox for analyzing tabular data. But, where else? I used to use random forests 99% of the time when I was doing machine learning with tabular data. I now use neural nets 90% of the time. It's kind of my standard first go-to approach now, and it tends to be pretty reliable, pretty effective. One of the things that's made it difficult is that until now, there hasn't been an easy way to kind of create and train tabular neural nets, like nobody's really made it available in a library. So we've actually just created fastai.tabular, and I think this is pretty much the first time that it's become really easy to use neural nets with tabular data. So let me show you how easy it is. This is actually coming directly from the examples folder in the FastAI repo. I haven't changed it at all. And as per usual, as well as importing FastAI, you should import your application. So in this case, it's tabular. We assume that your data is in a pandas data frame. A pandas data frame is kind of the standard format for tabular data in Python, and it's lots of ways to get it in there, but probably the most common might be pd.readcsv. But whatever your data's in, you can probably get it into a pandas data frame easily enough. Okay, hit me with the question.
What are the 10% of cases where you would not default to neural nets?
Good question. I guess I still tend to kind of give them a try. Yeah, I don't know. It's kind of like as you do things for a while, you start to get a sense of the areas where things don't quite work as well. I have to think about that during the week. I don't think I have a rule of thumb, but I would say you may as well try both. Like I would say, try a random forest and try a neural net. They're both pretty quick and easy to run, and see how it looks. And if they're roughly similar, I might kind of dig into each and see if I can make them better and better. But if the random forest is doing way better, I'd probably just stick with that. Use whatever works. So I currently have the wrong notebook in the lesson repo, so I'll update it after the class. So sorry about that. So we start with the data in a data frame, and so we've got a little thing, adult sample. It's a classic old data set. I'll have to dig up the citation for it because I forgot to put it in this notebook. It's a pretty small, simple, old data set that's good for experimenting with, basically. And it's a CSV file, so you can read it into a data frame with pandas.readcsv, pd.readcsv. If your data is in a relational database, pandas can read from that. If it's in Spark or Hadoop, pandas can read from that. Pandas can read from most stuff that you can throw at it. So that's why we kind of use it as a default starting point. And as per usual, I think it's nice to use the data block API. And so in this case, the list that we're trying to create is a tabular list, and we're going to create it from a data frame. And so you can tell it what the data frame is and what the path that you're going to use to kind of save models and intermediate steps is. And then you need to tell it what are your categorical variables and what are your continuous variables. So we're going to be learning a lot more about what that means to the neural net next week. But for now, the quick summary is this. Your independent variables are the things that you're using to make predictions with, right? So things like education and marital status and age and so forth. Some of those variables, like age, are basically numbers. They could be any number. You could be 13.36 years old or 19.4 years old or whatever. Whereas things like marital status are options that can be selected from a discrete group. Married, single, divorce, whatever. Sometimes those options might be quite a lot more, like occupation. There's a lot of possible occupations. And sometimes they might be binary, could be just true or false. But anything which you can select the answer from a small group of possibilities is called a categorical variable. And so we're going to need to use a different approach in the neural net to modeling categorical variables to what we use for continuous variables. For categorical variables, we're going to be using something called embeddings, which we'll be learning about later today. For continuous variables, they can just be sent into the neural net just like pixels in a neural net can, because like pixels in a neural net are already numbers. These continuous things are already numbers as well. So that's easy. Okay, so that's why you have to tell the tabular list from data frame which ones are which. There are some other ways to do that by pre-processing them in pandas to make things categorical variables, but it's kind of nice to have one API for doing everything. You don't have to think too much about it. Then we've got something which is a lot like transforms in computer vision. Transforms in computer vision do things like flip a photo on its axis, or turn it a bit, or brighten it, or normalize it. But for tabular data, instead of having transforms, we have things called processes. And they're nearly identical, but the key difference, which is quite important, is that a processor is something that happens ahead of time, right? So we basically pre-process the data frame rather than doing it as we go, right? So transformations are really for data augmentation, where you want to like randomize it and do it differently each time, whereas processes are things that you want to do once ahead of time. So we have a number of processes in the FastAI library, and the ones we're going to use this time are fill missing. So that's going to look for missing values and deal with them some way. We're going to find categorical variables and turn them into pandas categories. And we're going to do normalization ahead of time, which is to take continuous variables and subtract their mean and divide it by them by their standard deviation, so they're 0, 1 variables. The way we deal with missing data, we'll talk more about next week, but in short, we replace it with a median and add a new column, which is a binary column of saying whether that was missing or not. Normalization, there's an important thing here, which is, in fact, for all of these things, whatever you do to the training set, you need to do exactly the same thing to the validation set and the test set. So whatever you replaced your missing values with, you need to replace them with exactly the same thing in the validation set. So FastAI handles all these details for you. They're the kinds of things that if you have to do it manually, at least if you're like me, you'll screw it up lots of times until you finally get it right. So that's what these processes are here. Then we're going to split into training versus validation sets, and in this case we do it by providing a list of indexes, so the indexes from 800 to 1000. It's very common, I don't quite remember the details of this data set, but it's very common for wanting to keep your validation sets to be contiguous groups of things, like if they're map tiles, they should be the map tiles that are next to each other. If they're time periods, they should be time period, days that are next to each other. If they're video frames, they should be video frames next to each other, because otherwise you're kind of cheating, right? So it's often a good idea to use split by IDX and to grab a range that's next to each other if your data has some kind of structure like that, or find some other way to structure it in that way. All right, so that's now given us a training and a validation set. We now need to add labels. And in this case, the labels can come straight from the data frame we grabbed earlier, so we just have to tell it which column it is. And so the dependent variable is, I think it's whether they're making over $50,000 salary. That's the thing we're trying to predict in this case. We'll talk about test sets later, but in this case we can add a test set. And finally get our data bunch. So at that point, we have something that looks like this. Okay, so there is our data. And then to use it, it looks very familiar. You get a learner. In this case, it's a tabular learner. Passing in the data, some information about your architecture, and some metrics. And you then call fit. You had some questions? All right, let's hit the questions.
How to combine NLP tokenized data with metadata, such as tabular data, with FastAI. For instance, for IMBD classification, how to use information like who the actors are, year made, genre, etc.
Yeah, we're not quite up to that yet. So I need to learn a little bit more about how neural net architectures work. But conceptually, it's kind of the same as the way we combine categorical variables and continuous variables. Basically, in the neural network, you can have two different sets of inputs merging together into some layer. Could go into an early layer or into a later layer. It kind of depends. If it's like text and an image and some metadata, you probably want the text going into an RNN, the image going into a CNN, the metadata going into some kind of tabular model like this, and then you'd have them basically all concatenated together and then go through some fully connected layers and train them end to end. We'll probably largely get into that in part 2. In fact, we might entirely get into that into part 2. I'm not sure if we'll have time to cover it in part 1. But conceptually, it's a fairly simple extension of what we'll be learning in the next 3 weeks.
Next question is, do you think things like scikit-learn and XGBoost will eventually become outdated? Will everyone use deep learning tools in the future, except for maybe small data sets?
I have no idea. I'm not good at making predictions. I'm not a machine learning model. I mean, XGBoost is a really nice piece of software. There's quite a few really nice pieces of software for gradient boosting in particular. They have some really nice features, or actually Random Forest in particular has some really nice features for interpretation, which I'm sure we'll find similar versions for neural nets, but they don't necessarily exist yet. So I don't know. For now, they're both useful tools. Scikit-learn is a library that's often used for kind of pre-processing and running models. Yeah, I mean, again, it's hard to predict where things will end up. It's kind of, in some ways, it's more focused on some older approaches to modeling. But I don't know, they keep on adding new things, so we'll see. I keep trying to incorporate more scikit-learn stuff into FastAI, and then I keep finding ways I think I can do it better, and I throw it away again. So, so that's why there's still no scikit-learn dependencies in FastAI. I keep finding other ways to do stuff. Okay, so we're going to learn what layers equals means either towards the end of class today or the start of class next week, but this is where we're basically defining our architecture, just like when we chose ResNet 34 or whatever for ConvNets. We'll look at more about metrics in a moment, but just to remind you, metrics are just the things that get printed out. They don't change our model at all. So in this case, we're saying I want you to print out the accuracy to see how we're doing. Okay, so that's how to do tabular. This is going to work really well because we're going to hit our break soon. And the idea was that after 3.5 lessons, we're going to hit the end of all of the quick overview of applications, and then we're going to go down the other side. I think we're going to be to the minute we're going to hit it, right? Because the next one is collaborative filtering. Okay, so collaborative filtering is where you have information about who bought what or who liked what. You know, it's basically something where you have something like a user or a reviewer or whatever, and information about what they've bought or what they've written about or what they've reviewed, right? So in the most basic version of collaborative filtering, you just have 2 columns, something like user ID and movie ID. And that just says this user bought that movie, this user bought that movie, this user bought that movie. So for example, Amazon has a really big list of user IDs and product IDs of like, what did you buy? Then you can add additional information to that table, such as, oh, they left a review. What review did they give it? So it's now like user ID, movie ID, number of stars. You could add a time code. So like this user bought this product at this time and gave it this review. But they're all basically this same kind of structure. So there's kind of like two ways you could draw that collaborative filtering structure. One is kind of a two-column approach where you've got like user and, I don't know, movie, right? And you've got user ID, movie ID, user, you know, each pair basically describes that user watched that movie, possibly also plus number of stars, you know, 3, 4, 1, whatever. Well, the other way that you could write it would be you could have like all the users down here and all the movies along here, right? And then, you know, you can look and find a particular cell in there to find out, you know, could be the rating of that user for that movie, or there's just a 1 there if that user watched that movie or whatever. So there's like two different ways of representing the same information. Conceptually, it's often easier to think of it this way, right? But most of the time you won't store it that way explicitly, because most of the time you'll have what's called a very sparse matrix, which is to say most users haven't watched most movies, or most customers haven't purchased most products. So if you store it as a matrix where every combination of customer and product is a separate cell in that matrix, it's going to be enormous. So you tend to store it like this, or you can store it as a matrix using some kind of special sparse matrix format. And if that sounds interesting, you should check out Rachel's computational linear algebra course on FastAI, where we have lots and lots and lots of information about sparse matrix storage approaches. For now, though, we're just going to kind of keep it in this format on the left-hand side. So for collaborative filtering, there's a really nice data set called Movie Lens, created by the Group Lens group, very helpfully, and you can download various different sizes, 20 million ratings, 100,000 ratings. We've actually created an extra small version for playing around with, which is what we'll start with today, and then probably next week we'll use the bigger version. But so you can grab the small version using urls.ml sample, and it's a CSV, so you can read it with pandas. Here it is, right? It's basically a list of user IDs. We don't actually know anything about who these users are. There's some movie IDs. There is some information about what the movies are, but we won't look at that until next week. And then there's the rating, and then there's the timestamp. We're going to ignore the timestamp for now. So that's a subset of our data. That's the head. So the head in pandas is just the first few rows. So now that we've got a data frame, I mean, the nice thing about collaborative filtering is it's incredibly simple. Like, that's all the data that we need. So you can now go ahead and say, get collaborative learner, and you can actually just pass in the data frame directly. The architecture, you have to tell it how many factors you want to use, and we're going to learn what that means after the break. And then something that can be helpful is to tell it what the range of scores are, and we're going to see how that helps after the break as well. So in this case, the minimum score is 0, the maximum score is 5. So now that you've got a learner, you can go ahead and call fit one cycle. And trains for a few epochs, and there it is. So at the end of it, you now have something where you can pick a user ID and a movie ID and guess whether or not that user will like that movie. There's a lot of, so this is obviously a super useful application that a lot of you are probably going to try during the week in past classes. A lot of people have taken this collaborative filtering approach back to their workplaces and discovered that using it in practice is much more tricky than this, because in practice you have something called the cold start problem. So the cold start problem is that the time you particularly want to be good at recommending movies is when you have a new user, and the time you particularly care about recommending a movie is when it's a new movie. But at that point you don't have any data in your collaborative filtering system, and it's really hard. As I say this, we don't currently have anything built into FastAI to handle the cold start problem, and that's really because the cold start problem, the only way I know of to solve it, in fact the only way I think that conceptually you can solve it, is to have a second model which is not a collaborative filtering model but a metadata driven model for new users or new movies. I don't know if Netflix still does this, but certainly what they used to do when I signed up to Netflix was they started showing me lots of movies and saying, have you seen this? Did you like it? Have you seen this? Did you like it? You know, and so they fixed the cold start problem through the UX. So there was no, cold start problem. They found like 20 really common movies and asked me if I liked them. They used my replies to those 20 to show me 20 more that I might have seen. And, by the time I'd gone through 60, I wasn't, there was no cold start problem anymore. And for new movies, it's not really a problem because like the first 100 users who haven't seen the movie, go in and say whether they liked it. And then the next 100,000, the next million, it's not a cold start problem anymore. But the other thing you can do if you, for whatever reason, kind of can't go through that UX of like asking people, did you like those things? So for example, if you're selling products and you don't really want to show them like a big selection of your products and say, did you like this? Because you just want them to buy. You could instead try and use a metadata-based kind of tabular model. What geography did they come from? Maybe their age and sex. You can try and make some guesses about the initial recommendations. Right? So collaborative filtering is specifically for once you have a bit of information about your users and movies or customers and products or whatever. Yeah, okay.
How does the language model trained in this manner perform on code switch data, such as Hindi written in English words or text with a lot of emojis? And then do you want the second question? Or?
Separately. Yeah, that's a good question. So text with emojis, it'll be fine. There's not many emojis in Wikipedia. And where they are in Wikipedia, it's more like a Wikipedia page about the emoji rather than the emoji being used in a sensible place. But you can and should do this language model fine-tuning where you take a corpus of text where people are using emojis in usual ways, and so you fine-tune the Wikitext language model to your Reddit or Twitter or whatever language model. And there aren't that many emojis, right? If you think about it, there's like hundreds of thousands of possible words that people can be using, but a small number of possible emojis. So it'll very quickly learn how those emojis are being used. So that's a piece of cake. So I'm not very familiar with Hindi, but I'll take an example I'm very familiar with, which is Mandarin. In Mandarin, you could have a model that's trained with Chinese characters. So there's kind of 5,000 or 6,000 Chinese characters in common use. But there's also a romanization of those characters called pinyin. And it's a bit tricky because although there's a nearly direct mapping from the character to the pinyin. I mean, there is a direct mapping. The pronunciation's not exactly direct. There isn't a direct mapping from the pinyin to the character because one pinyin corresponds to multiple characters. So the first thing to note is that if you're going to use this approach for Chinese, you would need to start with a Chinese language model. So actually, FastAI has something called a model zoo, where we're adding more and more language models for different languages, and also increasingly for different domain areas like English medical texts, or even language models for things other than NLP, like genome sequences, molecular data, musical MIDI notes, and so forth. So you would obviously start there. To then convert that, that'll be in either simplified or traditional Chinese, to then convert that into if you want to do pinyin, you could either kind of map the vocab directly, or as you'll learn, these multi-layer models, it's only the first layer that basically converts the tokens into a set of vectors. You could actually throw that away and fine-tune just the first layer of the model. So that second part is going to require a few more weeks of learning before you exactly understand how to do that and so forth. But if it's something you're interested in doing, we can talk about it on the forum, because it's a kind of a nice test of understanding.
So what about time series on tabular data? Is there an RNN model involved in tabular models?
So we're going to look at time series tabular data next week. But the short answer is, generally speaking, you don't use a RNN for time series tabular data, but instead you extract a bunch of columns for things like day of week, is it a weekend, is it a holiday, was the store open, stuff like that. And it turns out that adding those extra columns, which you can do somewhat automatically, basically gives you state-of-the-art results. There are some good uses of RNNs for time series, but not really for these kind of tabular style time series like, retail store logistics databases and stuff like that.
Right, and is there a source to learn more about the cold start problem?
I'm going to have to look that up. If you know a good resource, please mention it on the forums. Great. Okay, so that is both the break in the middle of lesson 4. It's the halfway point of the course. And it's the point at which we have now seen an example of all the key applications. And so the rest of this course is going to be digging deeper into how they actually work behind the scenes, more of the theory, more of how the source code is written, and so forth. So it's a good time to have a nice break. Come back, and furthermore, it's my birthday today, so it's really, a special moment. So let's have a break and come back at 8:05. So Microsoft Excel. This is one of my favorite ways to explore data and understand models. I'll make sure I put this in the repo. And actually, this one we can probably largely do in Google Sheets. I've tried to move as much as I can over the last few weeks into Google Sheets, but I just keep finding it's just such a terrible product. So, please try to find a copy of Microsoft Excel, because there's nothing close. I've tried everything. Anyway, spreadsheets get a bad rap from people that basically don't know how to use them, just like people who, spend their lives on Excel and then they start using Python and they're like, what the hell is this stupid thing? I mean, it takes thousands of hours to get really good at spreadsheets, but a few dozen hours to get competent at them. And once you're competent at them, you can see everything in front of you. It's all laid out. It's really great. I'll give you one spreadsheet tip today, which is if you hold down the Control key or Command key on your keyboard and press the arrow keys. Here's Control right it takes you to the end of a block of a table that you're in, and like it's by far the best way to move around the place. So there you go. In this case, you know, I want to like skip around through this table, so I can hit Control down right to get to the bottom right, Control left up to get to the top left. Just going to skip around and see what's going on. So here's anyway, so here's some data, and as we talked about, one way to look at collaborative filtering data is like this. And so what we did was we grabbed from the movie lens data the people that watched the most movies and the movies that were the most watched, and just filtered the data set down to those 15. And as you can see, when you do it that way, it's not sparse anymore. There's just a small number of, here we are, there's a small number of gaps, right? So this is something that we can now build a model with. And so how can we build a model? Well, like what we want to do is we want to create something which can predict for user 293, will they like movie 49, for example. Right? So we've got to come up with some way of, you know, some function that can represent that decision. And so here's a simple possible approach. And so we're going to take this idea of doing some matrix multiplications. So I've created here a random matrix. So here's one matrix of random numbers. And I've created here another matrix of random numbers. More specifically, for each movie, I've created 5 random numbers. And for each user, I've created 5 random numbers. And so we could say then that user 14, movie 27, did they like it or not? Well, the rating, what we could do would be to multiply together this vector and that vector. We could do a dot product, right? And here's a dot product, right? And so then we can basically do that for every possible thing in here. We've got the dot product. And, you know, thanks to spreadsheets, we can just do that in one place and copy it over, and it fills in the whole thing for us. Why would we do it this way? Well, this is the basic starting point of a neural net, isn't it? A basic starting point of a neural net is that you take the matrix multiplication of 2 matrices, and that's what your first layer always is. And so we just have to come up with some way of saying, like, well, what are 2 matrices that we can multiply? And so clearly, you know, you need a matrix for a user, you know, or a vector for a user, a matrix for all the users, and a vector for a movie, or a matrix for all the movies, and multiply them together, and you get some numbers, right? Like, so they don't mean anything yet, they're just random, right? But we can now use gradient descent to try to make these numbers and these numbers give us results that are closer to what we wanted. So how do we do that? Well, we've set this up now as a linear model, right? So the next thing we need is a loss function. So we can calculate our loss function by saying, well, okay, movie 3 for user ID 14 should have been a rating of 3. With this random matrices, it's actually a rating of 0.91. So we can find the sum of squared errors would be 3 minus 0.91 squared. And then we can add them up. So there's actually a sum squared in Excel already, sum x minus y squared. So we can use just sum x minus y squared function, passing in those two ranges, and then divide by the count to get the mean. So here is a number that is the mean, well, it's actually the square root of the mean squared error. So like sometimes you'll see people talk about MSE, so that's the mean squared error. Sometimes you'll see RMSE, that's the root mean squared error. So since I've got a square root at the front, this is the square root mean squared error. So we have a loss. So now all we need to do is use gradient descent to try to modify our weight matrices to make that loss smaller. So Excel will do that for me. I haven't got them installed. So it's probably worth knowing how to do that. So we have to install add-ins. Oh, solver's there. Okay. I must have obviously forgotten where it was. Oh yeah. Okay. So the gradient descent solver in Excel is called solver, and it just does normal gradient descent. So you just go data, solver. You'll need to make sure that in your settings that you've enabled the solver extension. It comes with Excel. And all you need to do is say, which cell represents my loss function? So there it is, V41, right? So where is your loss function stored? Which cells contain your variables, right? And so you can see here I've got H19 to V23, which is up here, and B25 to F39, which is over there. And then you can just say, okay, set your loss function to a minimum by changing those cells and solve. And you'll see it starts at 2.81, and you can see the numbers going down. And so all that's doing is using gradient descent exactly the same way that we did when we did it manually in the notebook the other day. Okay, but it's rather than solving the mean squared error for A at B in the A at X in the Python, instead it is solving the loss function here, which is the mean squared error of the dot product of each of those vectors by each of these vectors. And so there it goes. So we'll let that run for a little while and see what happens. But basically in Micro, here is a simple way of creating a neural network, which is really, in this case, it's like just a single linear layer with gradient descent to solve a collaborative filtering problem. So let's go back and see what we do over here. So over here, we used get collab learner. Okay, so the function that was called in the notebook was get collab learner. And so as you dig deeper into deep learning, one of the really good ways to dig deeper into deep learning is to dig into the FastAI source code and see what's going on. And so if you're going to be able to do that, you need to know how to use your editor well enough to dig through the source code, right? And basically there's two main things you need to know how to do. One is to jump to a particular symbol, like a particular class or function by its name. And the other is that when you're looking at a particular symbol, to be able to jump to its implementation. So for example, in this case, I want to find get collab learner. So in most editors, including the one I use, Vim, you can set it up so that you can kind of hit tab or something and it jumps through all the possible completions, and you can hit enter and it jumps straight to the definition for you, right? So here is the definition of get collab learner. And as you can see, it's pretty small, as these things tend to be. And the keys, in this case, it kind of wraps a data frame and automatically creates a data bunch for you because it's so simple. But the key thing it does then is to create a model of a particular kind, which is an embedding.bias model, passing in the various things you asked for. So you want to find out in your editor how you jump to the definition of that, which in Vim, you just hit control right square bracket. And here is the definition of embedding.bias. And so now we have everything on screen at once, and as you can see, there's not much going on. So the models that are being created for you by FastAI are actually PyTorch models. And a PyTorch model is called an nn.module. That's the name in PyTorch of their models. It's a little more nuanced than that, but that's a good starting point for now. And when a PyTorch nn.module is run, when you calculate the value, the result of that layer or neural net or whatever, specifically, it always calls a method for you called forward. So it's in here that you get to find out how this thing's actually calculated. When the model is built at the start, it calls this thing called __init __. And as I think we've briefly mentioned before, in Python, people tend to call this dunder init, __init. So dunder init is how we create the model, and forward is how we run the model. One thing, if you're watching carefully, you might notice is there's nothing here saying to how to calculate the gradients of the model, and that's because PyTorch does it for us. Okay, so you only have to tell it how to calculate the output of your model, and PyTorch will go ahead and calculate the gradients for you. And so in this case, the model contains a set of weights for a user, a set of weights for an item, a set of biases for a user, a set of biases for an item, and each one of those is coming from this thing called getEmbedding. So let's see getEmbedding. So here is the definition of getEmbedding, and all it does basically is it calls this PyTorch thing called nn.embedding. So in PyTorch, they have a lot of like standard neural network layers set up for you. So it creates an embedding, and then this thing here is, it just randomizes it. So this is something which creates normal random numbers for the embedding. So what's an embedding? An embedding, not surprisingly, is a matrix of weights. Specifically, it's a matrix of weights an embedding is a matrix of weights that looks something like this. It's a matrix of weights which you can basically look up into and grab one item out of it, right? So basically, any kind of weight matrix, and we're going to be digging into this in a lot more detail in the coming lessons, but an embedding matrix is just a weight matrix that is designed to be something that you kind of index into it as an array and grab one vector out of it, right? That's what an embedding matrix is. And so in our case, we have an embedding matrix for a user and an embedding matrix for a movie. And here, we have been taking the dot product of them, right? But if you think about it, that's not quite enough, because we're missing this idea that, like, maybe there are certain movies that everybody likes more. Maybe there are some users that just tend to like movies more, right? So I don't really just want to multiply these two vectors together, but I really want to add a single number of, like, how popular is this movie, and add a single number of, like, how much does this user like movies in general. So those are called bias terms. Remember how I said, like, there's this kind of idea of, like, bias, and the way we dealt with that in our gradient descent notebook was we added a column of ones. Okay, but what we tend to do in practice is we actually explicitly say, I want to add a bias term. So we don't just want to have prediction equals dot product of these two things. We want to say it's the dot product of those two things plus a bias term for a movie plus a bias term for a user ID. So that's basically what happens. We, when we set up the model, we set up the embedding matrix for the users and the embedding matrix for the items, and then we also set up the bias vector for the users and the bias vector for the items. And then when we calculate the model, we literally just multiply the two together. Just like we did, right? We just take that product, call it dot, right? And then we add the bias, and then, putting aside the min and max score for a moment, that's what we return. So you can see that our model is literally doing what we did here, with the tweak that we're also adding a bias, right? So it's an incredibly simple linear model. And for these kinds of collaborative filtering problems, this kind of simple linear model actually tends to work pretty well. And then there's one tweak that we do at the end, which is that in our case, we said that there's a min score of 0 and a max score of 5. And so here's something to point out. Here's something to point out. So if you have you know, a range, so you do that dot product and you add on the two biases, and that gives you, that could give you any possible number along the number line, from very negative through to very positive numbers. But we know that we always want to end up with a number between 0 and 5. Let's say that's 5. And of course this is 0. So what if we mapped that number line like so to this function? Okay, and so the shape of that function is called a sigmoid. Right, and so it's going to asymptote to 5, and it's going to asymptote to 0. And so that way, whatever number comes out of our dot product and adding the biases, if we then stick it through this function, it's never going to be higher than 5 and never going to be smaller than 0. Now, strictly speaking, that's not necessary, right? Because our parameters could learn a set of weights that gives about the right number, right? So why would we do this extra thing if it's not necessary? Well, the reason is we want to make life as easy for our model as possible. So if we actually set it up so it's impossible for it to ever predict too much or ever predict too little, then it can spend more of its weights predicting the thing we care about, which is deciding who's going to like what movie. So this is an idea we're going to keep coming back to when it comes to making neural networks work better, is it's about all these little decisions that we make to basically make it easier for the network to learn the right thing. So that's the last tweak here, which is we take the result of this dot product plus biases, we put it through a sigmoid, and so a sigmoid is just a function. It's basically 1 over 1 plus e to the x. The definition doesn't much matter, but it just has the shape that I just mentioned. And that goes between 0 and 1. And if you then multiply that by max minus min plus min, then that's going to give you something that's between min score and max score. So that means that this tiny little neural network, I mean, it's a push to call it a neural network, but it is. It's a neural network with one weight matrix and no nonlinearities. So it's kind of the world's most boring neural network with a sigmoid at the end. That's actually, well, I guess it does have a nonlinearity. The sigmoid at the end is the nonlinearity. Just it only has one layer of weights. That actually turns out to give close to state-of-the-art performance. Like I've looked up online to find out like what are the best results people have on this Movie Lens 100K database. And the results I get from this little thing are better than any of the results I can find from like the standard commercial products that you can download that are specialized for this. And the trick seems to be that adding this little sigmoid makes a big difference. And did you have a question?
There was a question about how you set up your Vim, and I've already linked to your .vimrc, but I wanted to know if you had more to say about that.
What do they want to know about Vim?
They really like your setup.
You like my setup? There's almost nothing in my setup. It's pretty bare, honestly. Yeah, I mean, whatever you're doing with your editor, you probably want it to look like this, which is like when you've got a class that you're not currently working on, it should be, this is called folded. This is called folding, right? It should be closed up so you can't see it. And so you basically want something where it's easy to close and open fold. So Vim already does all this for you. And then, as I mentioned, you also want something where you can kind of jump to the definition of things, which in Vim it's called using tags. So if I want to jump to the definition of learner, basically Vim already does all this for you. You just have to read the instructions. My vimrc is minimal. I basically hardly use any extensions or anything. Another great editor to use is VS Code, Visual Studio Code. It's free and it's awesome, and it has all the same features that you're seeing that Vim does. Basically, VS Code does all of those things as well. I quite like using Vim because I can use it on the remote machine. And play around, but you can of course just clone Git onto your the Git repo onto your local computer and open it up in VS Code to play around with it. Just don't try and look through the code just on GitHub or something. Like that's going to drive you crazy. You need to be able to open it and close it and jump back. Maybe people can create some threads on the forum for Vim tips, VS Code tips, Sublime tips, whatever. Yeah, for me, I would say, like, if you're going to pick an editor, if you want to use something on your local, I would go with VS Code today. I think it's the best. If you want to use something on the terminal side, I would go with Vim or Emacs. To me, they're clear winners. So what I wanted to close with today is to kind of take this collaborative filtering example and describe how we're going to build on top of it for the next 3 lessons to create the more complex neural networks we've been seeing. And so, roughly speaking, you know, this is the bunch of concepts that we need to learn about. Let's think about what happens when you're using a CNN or you know, whatever, a neural network to do image recognition. Basically, let's take a single pixel, right? You've got lots of pixels, but let's take a single pixel. So you've got a red, a green, and a blue pixel, okay? And so each one of those is some number between 0 and 255, or we kind of normalize them so they're, you know, floating point between, well, with the mean of 0 and a standard deviation of 1. But let's just do the 0, you know, let's say whatever they're like, do the 0 to 255 version. So there's like 10, 20, 30, whatever. Okay, we'll come back to it. So what do we do with these? Well, what we do is we basically treat that as a vector and we multiply it by a matrix, right? So this matrix, depending on how you think of the rows and the columns, let's treat the matrix as having 3 rows and then how many columns? Well, you get to pick, right? You get to pick, just like with the collaborative filtering version, I decided to pick a vector of size 5 for each of my embedding vectors, right? So that would mean that's an embedding basically of size 5, right? You can get to pick how big your weight matrix is. So let's make it size 5. Okay, so this is 3 by 5. So initially, this weight matrix contains random numbers. Remember when we looked up get embedding weight matrix just now, and there were like 2 lines. The first line was like create the matrix, and the second was fill it with random numbers. That's what we do, right? I mean, it all gets hidden behind the scenes by FastAI and PyTorch, but that's all it's doing. So it's creating a matrix of random numbers when you set it up, and the number of rows has to be 3 to match the input, and the number of columns can be as big as you like. And so after you multiply the vector, the input vector, by that weight matrix, you're going to end up with a vector of size 5. So people often ask, like, how much linear algebra do I need to know to be able to do deep learning? This is the amount you need, right? So, and if you're not familiar with this, that's fine. You need to know about matrix products. Okay, you don't need to know a lot about them. You just need to know, like, computationally, what are they? What do they do? And you've got to be very comfortable with, like, if a matrix of size blah times a matrix of size blah gives a matrix of size blah. Like, how do the dimensions match up? So if you have 3, and then remember in NumPy and PyTorch we use @ times 3 by 5 gives a vector of size 5. Okay. And then what happens next? It goes through an activation function, such as ReLU, which is just max 0, x, and spits out a new vector, which is, of course, going to be exactly the same size, because no activation function changes the size, right? It only changes the contents, so that's still of size 5. What happens next? We multiply it by another matrix. And again, it can be any number of columns, but the number of rows has to map nicely. So it's going to be 5 by whatever. 1, 2, 4. So maybe this one has, 5, say by 10. And so that's going to give some output, which will be size 10. And again, we put that through ReLU. And again, that gives us something of the same size. Okay. And then we can put that through another matrix. Actually, just to make this a bit clearer, you'll see why in a moment. I'm going to use 8, not 10. Just so that these... Let's say we're doing digit recognition, right? So there are 10 possible digits. So my last weight matrix has to be 10 in size, because then that's going to mean my final output is a vector of 10 in size. And do you remember if we're doing like digit recognition, what happens? We take our actuals, right, which is 10 in size, and like if the number that we're trying to predict was the number 3, that's the thing we're trying to predict, then that means that there is a 3, 0, 0, 0 in the third position. Right? So what happens is our neural net runs along, right, starting with our input and going weight matrix, ReLU, weight matrix, ReLU, weight matrix, final output, and then we compare these two together to see how close they are, how close they match using some loss function. We'll learn about all the loss functions that we use next week. For now, the only one we've learned is mean squared error. And yeah, we compare the actual, you can think of them as probabilities for each of the 10 to the actual each of the 10 to get a loss. And then we find the gradients of every one of the weight matrices with respect to that, and we update the weight matrices. So the main thing I wanted to show right now is the terminology we use, because it's really important. These things contain numbers. Specifically, they initially are matrices containing random numbers. And we can refer to these yellow things as, in PyTorch, they're called parameters. Sometimes we'll refer to them as weights, although weights is slightly less accurate because there can also be biases, right? But, you know, we kind of use the terms a little bit interchangeably, but strictly speaking, we should call them parameters. And then after each of those matrix products, that calculates a vector of numbers. So here are some numbers that are calculated by, let's use this one. Here are some numbers that are calculated by a weight matrix, multiply. And then there are some other sets of numbers that are calculated as the result of a ReLU, as a result of the activation function. Okay. Either one are called activations. So activations and parameters both refer to numbers, right? They are numbers. But parameters are numbers that are stored. They're used to make a calculation. Activations are the result of a calculation. They're numbers that are calculated. Right? So they're the two key things you need to remember. So use these terms, right? And use them correctly and accurately, right? And if you read these terms, they mean these very specific things. So don't mix them up in your head. And remember, they're nothing weird and magical. They're very simple things. An activation is the result of either a matrix multiply or an activation function. Okay? And a parameter are the numbers inside the weights, inside the matrices that we multiply by. Okay? That's it. And then there are some special layers. So every one of these things that does a calculation, all of these things that does a calculation, are all called layers. They're the layers of our neural net. So every layer results in a set of activations because there's a calculation that results in a set of results. Okay? There's a special layer at the start, which is called the input layer. And then at the end, you just have a set of activations. Okay? And we can refer to those special, I mean, they're not special mathematically, but they're semantically special. We can call those the outputs. Right? So the important point to realize here is the outputs of a neural net are not actually like mathematically special. They're just the activations of a layer. And so what we did in our collaborative filtering example, we did something interesting. We actually added an additional activation function right at the very end. Right? We added an extra activation function, which was sigmoid. And specifically, it was a scaled sigmoid between 0 and 5, right? And that's really common, right? It's very common to have an activation function as your last layer, and it's almost never going to be a ReLU because it's very unlikely that what you actually want is something that that truncates at 0. It's very often going to be a sigmoid or something similar because it's very likely that actually what you want is something that's between two values, okay, and kind of scaled in that way. So that's nearly it, right? So we've got inputs, weights, activations, activation functions, which we sometimes call nonlinearities, output, and then the function that compares those two things together, right, is called the loss function, which so far we've used MSE. Yeah, okay, and that's enough for today. So what we're going to do, next week is we're going to kind of add in a few more extra bits, which is we're going to learn the loss function that's used for classification, which is called cross entropy. We're going to use the activation function that's used for single label classification, which is called softmax. And we're also going to learn exactly what happens when we do fine-tuning in terms of how these layers actually, what happens with unfreeze and what happens when we create transfer learning. So thanks everybody. Looking forward to seeing you next week.